Hello, can you hear me?
Yes, we can. Hello. Hello.
Okay, I think you both have my screen and you can hear me. Is it okay? Hello, can you hear me?
Yes, okay. Yes, we can. Hello. Hello.
Okay, that's great. And let's start. Dear all, good morning and warm welcome to all the keynote speakers, delegates, and all our well-wishers for this grand event. I am Mahia Mohammadi, moderator at this virtual session on behalf of Scholars Conferences. It gives me immense pleasure to have laser and photonics, and I thank you for finding time in your busy schedule to be here today. Today marks the major activity in the brief existence of the Scholars Conference, a moment where we are interacting, sharing experiences, and reflecting on various areas. This virtual session is a remarkable event which brings together professors, researchers, and students in making the virtual session a perfect platform to share experience, foster collaboration, and across the globe. In order to boost the quality of this virtual or mute your microphone to help keep us to minimum, make music background noise. When your microphone is not muted, avoid activities of background noise. When your microphone position camera sure is focus and your mic at eye level if possible. Doing create a more direct sense of engagement with other participants. Limit distractions on the meeting or minimizing running app and muting your avoid multitasking. You refrain from replying and wait on the PowerPoint until after the meeting ends. Prepare materials in advance. If you will be sharing content during the meeting, make sure you have the files and links ready to go before the meeting begins. Now, based on our schedule, I will now briefly introduce the following keynote speakers. It's my pleasure to call upon Angyang Yu from Zhejiang University, China, to deliver his keynote Dispersive Vortex Metal Fibers. And actually, I want to apologize in advance if I pronounce your names incorrectly. Dr. Yu, we are waiting for your speech. Dr. Yu, can you hear me?
Hello?
Hello?
Yes. Hi. I only see my face on the screen.
Yeah, we're waiting for Dr. Yu to present his talk. I will message him to inform him.
Oh,
We're waiting right now. Okay, until now I want to present Dr. Yu. Yang Yu received the bachelor master degree in 2012.
Good morning. The topic of my presentation today is highly dispersive vortex modes in optical fiber. My presentation is divided into 4 parts as follows, which contains the background and the work we study. The background and the applications is the first part we are going to talk. Space divergent multiplication technology is the promising approach to overcome the input power limit of standard single-mode fiber. SDM can be implemented using multi-color fibers or multi-mode fibers. In multi-color fibers, each fiber core carries a different channel, and those separate channels can themselves be multiplexed in wavelengths and polarization. In multi-mode fiber, the channels are carried by different modes. It is even possible to design fiber with multiple cores carrying multiple modes. With multi-mode fibers, SDM can be performed using LP modes or OM modes. Auto-angular momentum beams characterized by the helical phase profile are arousing an extensive attention due to the exposure relative between OM modes with different topological charges. The number of beams carrying OM is theoretically unlimited. OM state could be used as a different dimension to create an additional set of data carriers in an SDM system. This picture shows the various phase structure, intensity, and phase distribution of OM modes of different orders. OM multiplication does not rely on the wavelengths or polarization, indicating that OM could be used in addition to WDM and PDM techniques to improve system capacity. Light-carrying OM modes has supported widespread interest across a range of scientific and technological disciplines. The applications of OM has been extended to the fields of classical and quantum communication, optical trapping, sensor, and laser material processing. Here is the OM applied in the optical communication from OM-free phase optical communication. in 2012 to OM UAV relay optical communications in 2017. In multi-mode steps in this fiber, unwanted radially higher order modes can easily be excited. Those posing a strict restriction to the mode coupling because of the helical phase profile. OM modes generally have downslot intensity distributions to support OAM modes. Ring fiber with an annular high refractive index profile has been proven to be a preferable waveguiding medium for stable propagation of OM modes. The index profile of ring fiber can be properly designed to restrain the generation of unwanted radially higher order modes, and this potentially reduce the crosstalk induced theory mode excitement. Impress work, a means of increasing network throughput by using fiber modes that carry opto-angular momentum is reported. Over 1.1 kilometers of a specially designed optical fiber that minimizes modes coupling is achieved 400 gigabits per second data transmission using 4 angular momentum modes at a single wavelength and 1.6 terabits per second using 2 OM modes over 10 wavelengths. Chromatic dispersion is widely used for various applications in free space and the optical fiber system, such as temporal cloaking, ultrafast optical oscilloscope to enable delays and optical correlation. Some applications desire a flattened null or high dispersion over a broad band, while others need to eliminate the CD effect, especially in optical fiber communication systems. CD could have a significant impact on the transmitted signal quality, and this limits the information transmission capacity. One of the effective ways to mitigate the CD-induced penalty is to use the dispersion compensatory fiber, which can compensate for relative dispersion. Over the past few decades, highly dispersive fiber with different structure and materials has been reported, but they this will talk about structure and the principle of highly dispersive fiber. Highly dispersive fiber were originally designed for the fundamental modes HE 1.1, as shown in the image above. The intensity of the HE 1.1 mode is concentrated in the fiber center, and its phase is uniformly distributed. The typical structure of the highly dispersive fiber for the fundamental HE 1.1 mode features a high refractive index core and a cascaded concentric ring. Here, the high index core coincides with the fundamental mode's intensity distribution, which facilitates the model confinements. The cross section and the refractive index profile of the fiber are illustrated in Figure 2. Due to the mode couple between high index regions, the model field is distributed obviously with varied wavelengths, and the dispersion decrease drastically. This process will be further described in detail below. Due to the undefined phase at the center, the beam carrying OM mode has a darker central spot, which manifests as a ring shaft intensity distribution as depicted in Figure 1, with a similar annular index distribution. Ring core fiber have been experimented and proven to be able to transmit OM modes stably over long distance, also inspired by the traditional high dispersive fiber which compensated of the fundamental fiber etching mode. We propose a double ring core fiber for OM modes with large elective dispersion. The schematic depiction and the index distribution are shown in figure 2. Here R1 defines the operation of the symmetry shown figure 2. Here R1 defines the operation of the inner ring H1 and H2 reveals the width of the two high index ring regions. D is the relative operation of the two rings, and the cladding of the fiber has a constant radius 16 to 0.5 micron. Plenty of techniques has been reported for ring core fiber fabrication. The process of the double ring core fiber for propagating OM modes with negative dispersion is illustrated in figure 3. This structure has great scalability by further cascading multiple concentric high index rings into an optic fiber. As shown in the first image, with the adjusted waveguide parameters, the N1 curve of the OM mode in the inner ring decreases faster with the wavelengths than N2 of the same order OM mode in the outer ring. Therefore, as depicted in figure 1, N1 and N2 can cross at a target wavelength, and the concave function of NA is Hebbi's positive second driven with the maximum value at lambda zero, where the slope of NA changes intensely, leading to a highly negative dispersion at lambda zero. In the second image, the coupling process can be observed from the evolution of the model intensity distribution with wavelengths in the double ring fiber as indicated in the third image. For clarity, the intensity at different wavelengths are normalized respectively. When the vortex beam carry OM is launched into the fiber, the model is mainly confined in the high index ring near the core at the wavelength shorter than lambda zero. As the wavelengths increase to the close point lambda zero, a strong optic coupling occurs between the inner ring and the outer ring. The intensity distribution spreads out from the inner ring to the outer ring as the wavelength further increases. The mode is mostly confined in the outer ring. The variation of modes properties during the coupling process will be discussed in the next section. Next, I will introduce the property of OM mode in HDCRF. 14% doped silicon and short glass have been reported as alternative materials for the double ring core fiber with improved index contrast. The fiber based on short glass can support higher order OM mode. In this study, we select the pure germanium dioxide and silicon as the material of high index rings and subtract to exhibit the property of OM modes supported in the double ring core fiber. Plasma chemical vapor deposition followed by drying is a promising method to produce the proposed fiber. Another alternative manufacture method is extruding alternately stacked glass discs through a circular aperture. We summarized the double ring core fiber with different materials and structure parameters for various OM modes, as shown in the table. A four-vector finite elements method is used to simulate the characteristics of the OM modes. This image illustrates the simulated intensity and phase distribution of OM 1. modes supported in the desired fiber at the most dispersive wavelengths. Moreover, higher order OM modes need more azimuthal or radial space. When the topologic charge L1 is greater than L2, the needed radius of two high-index rings supporting OM mode with L1 are larger than those supporting OM mode with L2. Figure 1 illustrated that the effective index and intensity distributions vary with wavelengths for the OM1 100.1 mode supported in the inner ring, outer ring, and the fiber with two rings. And figure 2 illustrates that the above the effective index to the negative power of two difference between the adjacent IG mode ensure the separation between IG mode. When the wavelength is shorter than lambda 0, the mode is mainly confined in the inner high index ring and the power ratio is far more than 1. Approaching the close point lambda 0, an intense optical coupling occurs, which forms the symmetric and anti-symmetric modes. The mode field moves towards the high index ring. The effective mode is rapidly raised, and the ratio of power reduced to 1. The dispersion curve has a sharply negative value at the effective index above the wavelength lambda 0. The effective index profile of the two rings play a dominant role in the dispersion curve, including the duration and the value of the minimum. Figure 1 illustrates the dispersion curve of the OM1 100.1 mode in the double ring core fiber with two high index rings. Move away from the core in a step of 0.5 micron, while the relative location and the width of the two rings are constant values when the two concentric high index rings move 1 micron simultaneously. In the radio duration, lambda 0 is redshifted 65.6 nanometers, and there is an increment in minimum dispersion from minus 14,517 to minus 20,895. In the case of this ring correlation change, the effective refraction index curves for the OM1 100.1 mode guided independently in the two rings simultaneously raise, and the decrement with wavelengths in their respective index slow down. However, slope of the index in the inner high index ring varies more, which means that the slope difference between the two high index rings decreases. Therefore, lambda 0 moves and the extreme of the depression increase. Figure 2 depicts the dependency of CD on the signals of two high index rings. When H1 and H2 increase at the same time, the effective refraction index curves of the OM 100.1 mode supported independently in the inner and the outer rings elevate and turn the to be flatter, while the slope of the outer ring increases more. Therefore, the slope difference between the two rings increase and the closing wavelength changes. OM 65.1 mode approaches the limit of the mode older than 5% of the fiber can support it. The geometric variable of the higher doped fiber can be further optimized to achieve large elective dispersion. As the more fraction increases, there is an increment in the loss and a higher requirement for optical fiber manufacturing, which cannot be neglected in fiber material selection. In this section, we will introduce the intention of HDCF for OM mode. Ordinary crystal fiber featuring with periodically arranged air holes along the fiber radius imparts flexible control of optical properties to relatively high refractive index region and the air hole cladding. The refractive index of the two high index region can be further tailored by varying the arrangement of air holes or dumping high refractive index materials. By removing the air hole ring and reducing the diameters or another one, the equivalent refractive index of two ring region is higher than the cladding. To dump the high index ring, the hot air core in the center and the air hole rings into claddings. We also propose and design a traveling core fiber with two dispersion windows, the transfer section and the index profile of the proposed fiber at 1515 nanometers and depicted in the right picture. The desired fiber is composed of three high refractive index rings with different germanium doping concentration. The left picture shows the concentration of the lective dispersion generation process and the separation curve of OM 1.1 mode with different launching locations as the light enter the fiber from the different ring. The fiber can provide a large dispersion for OM 1.1 mode at corresponding wavelengths. The top figure depicts the intensity and the phase distribution of the OM 1.1 mode supported in the desired fiber. The intensity distribution of the OM 1.1 mode with different wavelengths at the case 1 and 2 in top figure corresponds to the launch location marked with the blue and red arrow in the last slide. Here is the properties of the OM 1.1 mode in the desired fiber, including effective refractive index, effective mode arrow, and the chromatic dispersion are displayed in following picture with optimized parameters. The composite index curve of the OM mode supported in the desired fiber has a sharp slope change at lambda 1 and lambda 2 are shown in figure A. The effective mode arrow is at a lower level as depicted in figure B. As the wavelength increase to lambda 1, a stronger optical coupling is established between R1 and R2. The model field distribution starts to spread out from R1 to R2, which induces to the rapid increase of the effective model arrow. The impact of the malfunction of GO2 in R2 is analyzed, and the result is summarized in the slide with the M2 increase. The dispersion curve of OM 1.1 mode with different launch locations both move to the short wavelengths, and the minimum value decreases while the wavelength separation between lambda 1 and lambda 2 reduce. To dump the high index rings, a hollow air core in the center and the air hole rings into cladding. Optic fiber with the concentric ring core for highly dispersive OM modes are semantically displayed, including the orange principle and the specific fiber structures based on the triple wrinkle fiber, the number of working windows could be further increased by fiber with more concentric ring. Coarse photonic crystal fiber provide more freedom to the fiber design and more precise control of dispersion. Expanding the dispersion bandwidth is the next direction worth study. Thank you for listening.
Thank you so much for your talk. It's time I want the audience to ask the question. Is there any question? So it seems no one has question. So it's time that I call upon Clifford Arnold from Colorado speech on the photon as a vertical axis pendulum. Dr. Arnold, with your talk. Technology in 1968 in the Silicon Research and Development Laboratory at Texas Instruments, where the first MOSFET integrated circuits were designed. Mr. Arnold developed program programs for on-chip circuit performance analysis. Dr. Arnold, I have your screen.
Hello, Dr. Cliff. Can you unmute yourself?
Dr. Arnold, I have your screen.
Hello, Dr. Cliff. Can you unmute yourself?
Are you hearing me now?
Arnold, I have your screen.
Are you hearing me now?
Yes, I can hear you.
Good morning.
Good morning.
There we are. I have slide on the screen. This will be a very unusual
Yeah,
presentation. Are you hearing me?
But it's your, yes, I'm hearing you, but I see your head.
Yeah, Dr. Cliff, can you share your screen, your presentation slides? We are unable to see your presentation.
Okay, so what do you want to do?
In the footer, there is a share screen. So click on the shared screen and open your PPT, presentation slides. We are able to see your Yahoo mailbox. So instead of that, can you show your slides, presentation slides?
Okay, opening my mailbox now.
Not the mailbox.
Yeah.
You open the slides.
Dr. Arnold, at the beginning, it works good.
Yeah. Can you share your
We
screen?
had your presentation.
Okay, so
So once
what
you click on
do I
the
need to
share
push at this moment?
Just bring your presentation and click on share screen. And after that, choose your presentation in the new window.
Yes. I have done that. Is it working now?
Yeah. Just keep it in presentation mode. Press F5.
So it's good. I can start talking.
Yeah, keep it in presentation.
Yes, of course.
1 second. Can you show it in presentation mode?
I don't understand your question, David.
Okay, you can start.
Thank you.
You can press F5 and it will be for all screen.
Okay, I did that and got nothing.
On the top, you can see from beginning, below the file button.
I'm on slide number 1 on my screen. I'm sharing that with you.
Yeah, you can press it, doctor. No problem.
Okay, let me start. I first got the idea to explain the composition of the electron in 1972 when I had a flash of inspiration that said 2 photons coming together could form an electron. I didn't realize at that time the details of the photon, and I began to study or look into the idea that 2 photons could become an electron. As I progressed through the research over the years, and we're talking about 1972 to about 15 years ago, very little progress. Libraries, the material in the libraries is pretty useless. Magazines were scarce and usually out of date. I finally waited 5 more years and the internet got good enough with information that it became useful to research almost anything, including the idea that an electron could be made of 2 photons. And as I looked at various presentations for the photon, I found out that there was still nothing particularly available to explain the photon itself. So as I progressed, I began to investigate the idea of using a pendulum as a photon. The reasons for that, using a vertical axis pendulum, the electric field can be shown as projecting up and down from the photon and reversing every half cycle. So what is up becomes down, what's down becomes up, and the outer rim of the photon becomes the magnetic closed loop ring of magnetism. So we have the 2 forces, electromagnetic, shown in a very different way than is portrayed in most photonic explanations. And as I worked my way through the idea of it being a vertical axis photon, I realized the rest of the world might be interested in this form of photon, since there was virtually no other information available about the construction of the photon. So that's why I'm at a photonics conference to present that information. I'm looking at my screen. I'd like to show a slide that shows that a little better. I'll go straight to my, this is what James Clerk Maxwell had to say about light in general. He did not describe the photon and was not even aware that light might be composed of photons. It was 20 years after he died that Max Planck did his work that indicated there may be a quantum theory involved here. So what we have from James Clerk Maxwell is the idea that light consists in transverse undulations of the same medium, which is the cause of electric and magnetic phenomenon. In other words, James Clerk Maxwell believed that light traveled through space using what was thought to be ether at the time and may still be, but ether has never been discovered directly. So for whatever reason, the electromagnetic photon is able to transfer itself or passes through space, but still no ether. So I assume, as Maxwell did, that there is an ether of some form or something that acts like the ether, and that's how the photon actually still is getting through empty space. So with that idea in mind, I have a description now. I hope you have on your screen on the right side two different photons, one which is fully twisted such that we have a full blue arrow vector pointing up, and below it a red vector pointing down, and around the middle a twisted electric magnetic not field, I don't want to call it a field, but the ring that goes around the middle is what is the rim of the vertical axis photon. And the bottom half of the same picture shows the reverse situation after the photon is rotated 90 degrees in the vertical. And we then have positive going up, the magnetic ring around the middle, and negative going down. And this is the alternate states that it goes through every cycle. So that's why this particular kind of photon works, or pendulum works so well, because it comes with an axis that is the electric field, and the rim, which is the magnetic closed loop scalar. So that's the problem with what is normally shown as a photon. I'll get one here now. On the right side of your screen at the moment, you see what has been passed as the photon in the past. And of course, it's not even close to representing a physical entity, a form of particle that the photon actually is, which I believe is the vertical axis photon pendulum. So when we look at, is my mouse showing on your presentation? Let me go ahead then. We see in red on this slide that I'm looking at now what is believed to be the electric field strength. And that corresponds to, if we look over on the left side, the amount of twist that we see in the axis of the photon. The magnetic scalar is represented in rotation of degrees. In other words, as the ring twists back and forth in its vertical axis of operation, we see the magnetic scalar growing to the full twist and then going back to zero again. As I looked at this representation of the photon, the problem seemed to be that we had 2 points where the energy of the photon was portrayed as zero, which of course we do not believe. So there was a missing representation of the kinetic energy of the photon that needed to be added, which I added and called it time flux energy. So that's how I corrected this electromagnetic representation of the photon. Let's go back now to the top of my slideshow and read the words. Actually, the photon is an invisible subatomic particle which may be modeled as a vertical axis torsional pendulum, the torsion being maintained in the actual electric field and twisted. And that's how the energy is manifested to the rest of the universe. We see the electric field first being minus and then plus, which if we go to the standard model of the elementary particles, we find the photon is listed there. And it has three characteristics as stated by the physicists. With a mass of 0, the mass of the photon probably is not 0, a charge of 0, and we know that the photon actually has an AC charge, which goes to what I call a full +1, and then to a full -1, and then back to a full +1 again every cycle. So it's the standard model does not represent the photon very well, even in its characteristics. The spin is probably still 1. So we want to get back now to the idea of asking, what is the velocity of the photon? And if the photon has, in fact, 0 mass, there seems to be no reason that the photon would be limited to any speed. But if the photon has mass, then it would be limited to the speed of light, which is actually the asymptotic speed of light, which it can never reach any more than Einstein told us that anyone else could reach the actual speed of light. The best you can do is get very close to it, and by that time your mass has grown hugely, and you just can never get there. So that is my belief, that the photon has a mass, even though it's extremely tiny. Best guess in the middle of this slide we're looking at now, photon mass could be as low as 1 × e⁻⁻⁵, could even be lower, -51, -52. But I have slides which show the actual energy of our photon spread from on the left. In this slide, we're looking at the mass of photons in the broadcast range, anywhere from 3 megahertz on up to 30 gigahertz. Those would be the mass range is in the -43 to -40 kilograms. In the center picture here, we have, this is log paper. We have the energy and the mass, of light itself, which is shown as a rainbow bar, to be in the range of -36 to -33 on this particular graph. And we see where light falls in there, and the wavelength is in meters in all of these cases. On the right side, we see the gamma ray section of the electromagnetic spectrum, and we find that at this point we can take 2 of the photons with a mass half of that of the electron, and if we can somehow get them in orbit with each other, we will have something which has the mass of the electron, but it's in the form of 2 photons. So that was where I was headed when I started studying the photon closer. Today, we don't want to talk so much about how those electrons might have been formed using 2 photons. I have a website at masquerade.com, which explains this in much greater detail. I have a movie there of That's an hour long. People should take a look at that. It explains how you can use 2 photons to make an electron. So getting back to the photon, the question was, if it has mass, then it would seem impossible to exceed the speed of light. And in fact, that's why the speed of light is what it is because the photon has mass. So I'm saying that's a proof of mass. Everything, including light, has an asymptotic speed limit. It's why photons travel precisely at the speed of light. And this alone should be simple and convincing proof, right? The velocity of photonic energy transmission through empty space is usually believed to be at the speed of light. And in calculus, we know that there are asymptotes. And in our case, there's an asymptotic speed of light that is limiting even the photon to the speed that it travels. And that's what's been measured as and believed to be the speed of light, which in fact it is the speed of light, but it's not the asymptotic speed of light. So if we proceed here now, we've got, pardon me, if photons do have mass, then they will be limited. We can ask Dr. Einstein. He gave us an equation for the mass of anything that's being accelerated towards the speed of light, which I believe the photon is actually self-propelled, like a bubble in a swimming pool. The photon has a center in it which has no media in it. So it's like a bubble, and it's the media itself which propels the photon to the speed of light, or very near to it. It's actually the speed of light, but not the asymptotic speed of light. So let's keep going with that idea. If we agree that the photon does have mass, I've already stated it's in the 10 to the minus 50, minus 51 perhaps range. So we have the proof of mass, and let's keep going on through my slides again. It's certain that it cannot reach the asymptotic speed of light. So if we keep going down my slideshow, let's ask the next question. At this point, we believe the photon has mass. So what is the photon, particle, or wave? And I'm watching my time here, and I don't want to run out of time, but I want to talk about the photon as a particle or a wave. And again, the photon has been classified as in the standard model as a particle. I believe that particle the mass may not be 0. The charge average is 0, but has an AC value that's not 0. The spin is probably 1. There's a recent experiment with a quantum double slit mechanical maze that proves photons are not waves. I don't know how many of you are familiar with this photon double slit experiment, but the gist of the experiment is that they're using multiple dark filters to limit the number of photons which arrive at the double slits down to where they can actually count them one at a time. These photons come through the slit and mysteriously have low probability strike zones and high probability strike zones, even though there is no way that there's any sort of wave interference by other photons. In other words, the photons are coming through the slits, one or the other, simultaneously or within some amount of time from each other, which can be in the seconds, literally. But they still follow certain paths to the screen. And the reason for that is not because of wave interference, because we have no wave. All we have is a stream of particles. This has been shown to be true with electrons and even ions. They will come through these slits one at a time, and they will follow specific paths to the screen without ever getting on the low probability paths. Niels Bohr and Werner Heisenberg agreed with this back in 1925, somewhere in between 25, 27. They said, this is a quantum mechanical space that's been created in this experiment. So the experiment itself, using these tiny slits, we know that you can use a pinpoint hole in something and it will act like a lens, meaning there will be certain paths that light can travel, and there are certain paths light cannot travel. There's no way to predict when we build this maze that the photons are expected to pass through what their actual path will be. They have found that if you shine a light, a laser light through this maze, that you will get this pattern. And let's go to the next slide. You will get the stripes. You will get the hit zones, strike zones, and between those strike zones, you will get places that photons seldom ever strike. This is without any interference whatsoever. So the question is, what is interfering with it? And the answer is, it's the maze itself that has created this pattern and not any kind of interference between photons. So this not only proves that the photon is not a wave, but it shows us that these particle strikes where they land follow the probability curves that Heisenberg and Bohr predicted back in the early 20s or middle 20s. So using this idea, we can safely say that the photon is a particle. Quickly now, it's my theory, and again, this is found in masquerade.com on the internet. The photon is a building block of all subatomic particles of mass and matter. So if the photon itself, it has mass, that would be the best reason for all the subatomic particles also exhibiting not just mass, but all the other characteristics of the photon. We're talking about electric charge, magnetism. As we think about the photon as a particle, that's one of the best ways to think about it. So back to the next slide. I'm trying to hurry here. My time is running short. We know, I believe, that this graphic on the right is completely in error. I believe that the electric field should be going above and below in blue. If we're going to represent red with positive, then we should have an alternate sine wave below it. And this blue line, which is called the magnetic scalar on my screen here, would be circular and traveling along the black line, the center line here. Oops, I don't want to edit. So as we look at the actual photon on the left as being this pendulum, that's what we should be thinking of as a photon. So when we compare this graphic on the left and this slide, and I hope we're seeing the same thing on the screen at the same time. If you look on the right side, the photon is, the electric field is growing in the negative direction at the same time it's growing in the positive direction. This is along the axis of the photon as it travels across the screen. This is not growing and staying there. We have one point in time, we have the next point in time, any point in time. This shows us what the photon voltage or electric field will look like, but it doesn't stay. It immediately keeps changing as it moves from right to left in our screen. So electric fields are very transient in nature. We're talking about 10 to the minus 15th nanoseconds as being the amount of time one of these cycles would exist if it were an electron. So let's keep going now. I don't know how to stop at this point. One more thing I will show you. On the left side of this screen, we have the negative and positive electric field shown as the photon progresses from left to right across the screen. If we arrived at a polarization filter in mid-screen, which was able to twist the photon in its rotation and polarization at exactly the right amount so that it did exactly one full twist per cycle of the photon, we would see an amazing thing. We would always see one side of the photon being either negative or positive, no longer alternating as it does on the left side of this screen, and also allowing us to build an electron. If we could get this photon to be going in a circle, if you circle the opposite direction, you build what is called a positron. If you take two of these photons and alternate them opposite directions, you build a neutrino. That's why you can build particles, electrons, positrons, and neutrinos using the very same two photons. So that's should be a point of interest to all of you people who have been dealing with photons all your life, who've used it in your business like I did for 50 years. We now know that the photon is a very much more busy thing in the universe. In fact, it is the building block of all subatomic particles. So I just saw a video recently that the magnetic ring of the photon can be used to create the force that holds the proton together. But because it's alternating plus and minus very rapidly, at some point as things start to get closer, it reverses the force on the two particles and they actually repel each other. So they become locked, quarks do, at a very short distance in the nanometers. And it's because of the electric component of the photon. So with that thought in mind, let's go to the next slide. And quickly, what we saw in Einstein's experiment when a photon came very closely passing the sun, on the right side of our screen here. Are we on the same screen?
Excuse me. I don't want to interrupt you, but I would be appreciate if you can finish your great presentation to meet the schedule. Thank you so much.
Okay.
So
I can save the rest for another. I can save the rest for another day. There's only one point to be made here. We see a T and a second T in this, and the length of the space where the T is written is different. And that's all I have to say about that. If we, I hope.
How many time do you to finish?
If the people at the conference can look through the list of photon characteristics, I should not go through those now. So at this point, if we're ready to stop, I can stop. Thank you.
Let me check. I think you can finish it, but bit fastest, please.
Yes, is there a question?
Lee Farnell, good afternoon. I would like to ask you, didn't you try to find building blocks which photons are made of. Because it is very good idea. It is something very close for my investigation. Maybe my works are not known very good. I will present Michelson-Morley experiment later, but actually my work is much bigger and includes gravity nature and the space structure. Okay, maybe it's difficult to believe, but actually in my idea, the photon also is not building block. Building block is smaller, but just believe that it's not ether theory. It is very mechanical and colonical theory. But taking into account building blocks where the photon consists of, these building blocks, we can explain the nature of vacuum, gravity, and also Higgs field and Higgs boson. It sounds strange probably, but I will try to appropriate this later, and probably it has some reason, some sense. So didn't you think about the building block photon consists of? Smaller building block.
Yes, I think I understand. It sounds like you have been working on a similar idea. You're writing a book, is that correct? Are you writing a book?
I didn't hear the question.
Okay. If we could share email at some point, my email is my name, Cliff.
Okay, we can discuss it. Probably, yes.
_ Arnell@yahoo.com.
Okay, thank you, because
That would
we are
be
out of
good
time.
to share this information.
Thank you.
Yes.
Is there any question?
I'm stopping my share.
Thank you so much for your talk.
Thank you for allowing me to present this. It's been a long time coming.
I just have another 10 minutes to present if you.
Another question?
No. Can you hear me?
Yes. Now I am not.
I just another.
So Dr. Cliff, you can finish off your presentation, not to worry about the time. You can finish off your presentation.
It would be nice to be able to read the question either in text to me or on the screen.
Okay. Let's.
Okay. Dr. Cliff, can you finish off your presentation?
Yes. I feel like I'm out of time.
Not a problem, not to worry. We'll give another 10 minutes of time, like you can present it. You can finish it. Can you share your screen again?
I'll come back to the very end of my presentation. I have a slide. Are you seeing the slide that I just selected? Photon transit time per cycle. Are you seeing that on your screen?
Yes, I see this slide on my screen.
Okay. The reason this is so interesting is because it shows us the speed of light is anything but constant. The speed of light is only constant in the open air where it was measured on planet Earth. And anytime the light gets into glass, any kind of crystal, the speed of light will appear to be reduced. But the energy of the photon stays the same. And the way you determine that, again, is using Planck's constant, where you have one cycle per second in my graphic here, whether it's inside or outside of the crystal that's shown in the middle. So even though the peaks are only half as far apart, making it look like the photon may have actually increased in frequency inside the crystal. In fact, inside the crystal, the frequency is still only one cycle per second of travel. So time and space become interlocked there. We have a space that's only half as great as it was outside the crystal, but we still have the light traversing it one cycle per second. It turns out if we get very far away from the sun out in interstellar space, we also relieve the pressure that gravity of the sun is putting on everything, not just at the surface of the sun, as Einstein presumed, but at greater distances from the sun. When we get out into vast interstellar space, we may find that a cycle of photonic energy is much longer. What this really means is it's not near as far to the nearest star as we believe it to be if we use the speed of light that we know to be true on Earth. The speed of light could be the distance that light travels per second might be very much greater, which would allow interstellar space travel to happen very much easier than we've ever imagined. So I offer that as my closing thought about what could be going on out there in interstellar space that would allow us or anyone else to pass through that space at a very much higher speed, distance, I should say, per second. So that's why I have this graph. So actual speed is reduced when we're increased density, but it may actually be the opposite in interstellar space. So there's a very important point that I have had to make to explain gravity itself. When a photon is curving around the sun, and I've changed slides to the motorboat. When a photon curves around the sun, it produces a compression of time on the inside of the curve and a decompression of time outside the curve of the photon. So we have the effect, exactly as Dr. Einstein described, of gravity. And that's what gravity actually is photons curving. So if we think of all of our subatomic particles making up our body, every last one of those particles is made of photons, which are curving around each other in very tight binary orbits. They're producing in the middle of the hole, the center here, a massless black hole, I call it. And on the outside, so if the photon finds itself in a gravitational field such as the Earth, as the photon moves around in orbit of a particle, it will explain the equivalence principle. Every last molecule, every last subatomic particle in any given piece of mass, because it's made of these photons, which are always in motion, extremely high speed of light, nearly, we have the effect is to cause the photon in its curving motion to move closer towards the center of any gravitational field that it finds itself in. So if you have a way to screen capture, this would be a great screen to capture because it explains gravity. Very simply, it's due to the curving of the photons. The photons themselves are compressing time, and that's what gravity appears to do. And it's more than appears to do, it's what actually, I believe, has happened. That's why I call Masquerade the theory of everything, because it explains electric phenomenon, it explains the magnetic phenomenon, it explains the gravitational phenomenon. If you imagine this wave that's left behind this boat traveling out through space, you'll see that it is, in fact, a gravitational wave. And that wave is caused again by curving photons. So again, the photon is the building block, not just the subatomic particles, it's also the provider of gravity as we know it. So I should conclude with that idea. I liked what Dr. Einstein said 100 years ago. He said, reality is merely an illusion, albeit a persistent one. It was thought that Dr. Einstein thought that perhaps mass might be composed of photons. He never wrote any papers about it. But there were hints of conversations that hinted that he liked that idea. So thank you very much.
Thank you so much for your time. Is there any question? Question? Does anyone have any question?
This moment has been a long time coming for me, and I thank you all for listening.
Thank you so much for your great talk.
Okay.
It's time. I now take this immense pleasure of invite Vladimir Rumyakin, NetTech Institute for Physics and Engineering, deliver keynote speech, quantized light matter coupling in cavities containing rate type. Rumyansev is chair department of theory of complex system dynamic properties of Galkin, Donetsk Institute for Physics and Engineering. Donetsk Institute of Engineering. So it seems that it's not available right now. So I call upon Mikhail Trubelsky from Lomonosov Moscow State University, Russia, to deliver his keynote speech on singularities in pointing vector field at resonant light scattering by meso and nanoscale particles.
Okay, thank you. Greetings to everybody. Do you see my screen?
Yeah, I can see your screen. I can hear you.
Great. So, may I start?
Yeah, that's great. We're waiting.
The sound
for you.
and the vision is okay. So, okay, great.
Yeah, everything is okay. You can start.
Thank you very much. I would like to thank the organizer for the opportunity to give this talk at this conference. And I would like to encourage the audience to interrupt me and put your questions, or if you don't like to interrupt me, you can put your questions after the end of my talk. I would be pleased to answer them. And actually, we have plenty of new results related to this topic, but most of them are related to rather sophisticated analysis based on the problem symmetry and other technicalities, which probably are not interested to the broad audience of this conference. So then, once again, I encourage those who are interested to put me specific questions in private, and that to drop me a message, and I will be pleased to discuss. Allow me briefly introduce myself. My name is Michael Trubelsky, and my affiliation is Lomonosov Moscow State University. This is my university. And this is the eldest and the maybe largest university in Russia. It has more than 250 years history. And I'm pleased to, it's a great honor for me to present this institution at this conference. Now about the subject matter of my talk. Singular optics is a very new and promising branch of optical sciences, but most of the results related to this subject matter are connected with rather sophisticated experimental devices where singularities in optical fields are created with the help of rather complicated devices, usually with nanoscale size. In contrast to that, there are plenty of phenomena which where the singularities are created on their own accord, spontaneously. And I would like to focus on these effects. So specifically, the effects related to the resonant light scattering by small particles and spontaneous formation of singularities of the pointing vector field at the subwavelength scale. As I already mentioned, the problem symmetry plays a very important role in the problem. Therefore, I will split my talk on two parts. One is devoted to the light scattering by a sphere, and another by light scattering by a cylinder. These two simple shapes are selected because both admit exact solution of the diffraction problem. Despite, nonetheless, it is convenient to illustrate the results, but the results are quite generic, and they are valid for actually any material body and any singularities spontaneously appeared at light scattering. So here I present the results of the exact, this is, by the way, this is an analytical result, not a numerical calculation. This is an exact solution of light scattering problem by a sphere known as Milorentz solution. The sphere is shown as blue circle. The radiation, the plane electromagnetic, linearly polarized electromagnetic wave propagates from below to upper part of the panels, and the color corresponds to the absolute value of the Poynting vector, normalized on the intensity of the incident electromagnetic wave. And the white lines are the streamlines of the Poynting vector field. We are close, all details are indicated below. And this is what I should stress. This is a substantially subwavelength case, so that the radius of the particle is much smaller than the wavelengths of the incident radiation. And we are close to the point of the dipole, electric dipole resonance, which occurs at the permittivity equals to minus 2.2229. Despite the particle is small and seemingly should obey the Rayleigh scattering law, this is not the case. Because of a small dissipation, this is a non-dissipative limit actually, in the vicinity of the resonance, the Rayleigh approximation becomes erroneous because the main role is played by the radiative damping, which is not energy losses related to the radiation of the induced oscillation of the localized plasmons, which are not encountered in the Rayleigh theory. So we could see a number of singular points, and the number and the position and the type of these singular points vary with the variation of the very weak variation actually of the permittivity, or if we're talking about the real experimental situation, the frequency of the incident wave. What is important here? Here we could see the centers of the localized plasmons, which I already mentioned. And what is important is what we called a funnel. So you could see this area bounded by red separatrix, and the energy from downstream, from a large area downstream from the inlet of this funnel is collected and then shrinks and is contracted and conveyed to the immediate vicinity of the particle, of the scattering particle. Because of that, we have a huge concentration of the electromagnetic energy at the vicinity of the particle and inside the particle at the substantial subwavelength sizes. You could see that looking at this color bar. So the enhancement of the electromagnetic field here, and for this plot, it's about 240 times, and it will be increase as we approach the exact point of the resonance, as you could see here. I draw your attention to the two optical vortices, number 5 and number 6, which are created spontaneously because of the properties of this light scattering problem. So then here we are closer to the resonant point, and the intensity increases again. Different plots have different color scale, and so on and so forth. So singular points. In the singular points, we have streamlines which intersect or merge. Because the streamlines are the lines where the vector pointing at every point of them, the vector pointing is tangential to the streamline. If two streamlines or more streamlines merge or intersect, we do not have any definite direction of the pointing vector at this point. And the only opportunity for us to fulfill the vector nature of the pointing vector in this case is to suppose that it vanishes. So then from this simple argument, we could see that the pointing vector should vanish at any singularity. Then let us discuss the foci. So we could see two optical vortices in the previous slides, and similarly, it contradicts to the energy conservation, because if the energy is transported to the, if it is a stable focus, then the energy is transported to it. If it is unstable, it emerges from the singular point, and similarly, it contradicts to the energy conservation. So how to save the day? The day is saved because we have actually a three-dimensional space. And it is clearly seen in this three-dimensional picture. There are two optical vortices, and we could see that while the energy is released from this point because of this energy flow, it is transported to this from the transversal direction. So then the energy which is delivered to this point eventually goes to infinity, and because of that, the energy conservation law is fulfilled. So this is the illustration of what I've just said. So then we can classify the singular points in the pointing vector field. If we remember that the pointing vector is the vector product of electric biomagnetic times a magnetic field. So then there are three options for the pointing vector to vanish. Either the electric field is vanishes at the zero at the singular point, or magnetic field is zero at the singular point. These two cases we will call field-induced singularities, or a standing wave is formed, and in this case, neither E or nor H equal to zero, but because of the counter-propagating wave, the energy flow is zero. We will see that all three cases are realized. So as an example, I present here the same pictures shown before, but the left picture is exactly the same as was shown. This is the plot of the pointing vector field. And we could see a number of singular points which are points 1, 2, 3, and 6. 1, 2, 3, and 6 are saddles, and points 4 and 5 are foci. And this is the equatorial plane the cross section of the pattern by the equatorial plane, and the electric field is parallel to the plane of the feeder. So then the magnetic field is perpendicular to it. And then what I did, I superimposed this streamline pattern with the plot for the modulus of the electric and magnetic fields. I draw your attention, this is the logarithmic scale. So we could see that for the electric field, none of the singular points correspond to zeros of the electric fields. It does not vanish at any singular point. In contrast, the magnetic field vanishes at foci, but does not vanish at the saddles. It means that we have standing waves here, and we have field-induced singularities there. Here we also have all saddle points correspond to the standing waves. And I stress that the scale of this picture is much smaller than the wavelengths, so that the area of the localization of this standing wave is small, much smaller than the wavelengths of the incident radiation. So we made plenty of calculations, and all of them exhibit this phenomena, which we cannot prove rigorously, but we observed it, as I said, many times. So if we have a field-induced singularities, and if this singularity lies in an invariant plane, as an equatorial plane in the previous picture, and if the incident wave electric field is parallel to this plane, then the singularity field-induced singularities are related to the vanishing of the magnetic field. Opposite, if the singularity is situated in the invariant plane parallel to the magnetic field, then the singularity field-induced singularities against electric field-induced singularities, so electric field vanishes. So we have a supplementary field which vanishes supplementary to the field line in the invariant plane. How to describe these singular points? The equation is very simple. If we, because the vector pointing is tangential at any streamline to the streamline itself, so then if we suppose that the streamline is described by a parametric equation, R as a function of t is not a real time, it's real time, it's just a parameter. So then the velocity of this trajectory, the R over dt, should be parallel to the pointing vector at this point. And the coefficient of proportionality always can be turned to unity because of the rescaling, proper rescaling of the parameter t. Then this is a generic equation for the streamlines of the pointing vector field. And then we are interested in the singularities lying in an invariant plane. Up to now, this is the only type of singularities obtained in this problem. Maybe other singularities exist, but they have not been discovered. So then we can expand the pointing vector field about the singularity. And if we do this expansion, then we obtain the following very simple set of expressions where the notation is indicated here. This is just linear. We took into account that in the very point of singularity, the vector field vanishes because of the reasons I discussed above. So the expansion begins from the linear terms. And this is the linear terms, the very general set of expansions. And for the y-axis, we have only this expression because owing to the symmetry at y equals 0, sy should vanish identically. So then we do not have other terms here. This should be supplemented by the energy conservation, which says that the divergence of the Poynting vector equals the dissipative losses. And if we calculate the divergence from the left equation, we will get that the sum of diagonal elements of this matrix should be equal to 2, which is in this approximation is a constant. If we take into account that at optical frequency, the permeability is identical unity, so then the dissipation is related only to the imaginary part of permittivity and to the electric field solely. So then for H-induced singularities, we have this expression, which is actually a constant in this approximation. And for electric field-induced singularity, we must suppose that this Q is 0. So from these simple arguments, we can arrive at the conclusion that the dissipation affects H-type singularities much stronger than that for E-type of singularities. So then let us move to a cylinder. To a cylinder, we have a single out direction, which is singled out by the direction of the axis of the cylinder. So then there are two, we consider just two, we have considered the general case, but it is too cumbersome and complicated. Then I selected just two simple cases, so-called TE or TM polarization of the incident wave, the corresponding orientation of the wave vector and the fields of H and E are indicated in the figure. And I also restrict myself only by the normal incident when the wave vector is perpendicular to the axis of the cylinder. Then the same expansion as above gives us this simple reduced system of equations. And it appears that because of the reduction of the dimensions, that we have only two-dimensional picture here, because the problem is symmetric with against any translation along the cylinder axis. So it occurs that it imposes very strict restrictions on the types of the possible singular points. So this actually this is the classification of singularities which could happen and in this case, and you could see that there are very few types of singularities which are admitted in the case of the cylinder. To illustrate this general reasoning, I produce two pictures. Actually, maybe this is only one picture, but one panel consisted of several pictures. This is a cylinder with TE and TM polarization. So in this picture, the electric field is situated in the plane of the figure. And in this case, the magnetic field is situated in the plane of the figure. According to what I said, because this is the actual calculation for germanium irradiated in a vacuum, this is the wavelength of the incident radiation, and this is the actual permittivity of germanium at this wavelength. We have certain weak dissipation, and according to this figure, if we have non-zero dissipation, we have only two types of three types of singular point, either a focus or a saddle or a node. So here we have a saddle. It looks like a center, but it's because the dissipation is weak. If we zoom this area, it's indicated here, we will see a spiral, and with the pitch gradually tends to 0 when the spiral tends to the singularity. This is the case for the TE polarization, and this is exactly the same for TM polarization, but the pitch of the the pitch of the spiral is much smaller in this case. Pay attention to the scale here and there. So this is a illustration of the general principle which I said. The dissipation affects the TE type, the E type, excuse me. The polarization affects the H field induced singularities much stronger than E field induced singularities. So that's basically the main concepts of what can be done phenomenologically for the classification and explanation of different singular points in the Poynting vector field. And the conclusion is that at any singular point, the Poynting vector should vanish. In a three-dimensional problem, optical vortices are field-induced singularities, while saddles are polarization-induced singularities. The former are related to the vanishing of the one of the electric or magnetic field, and the latter are related to the formation of a standing wave. If a field-induced singularity lies in an invariant plane, which is parallel to the plane of the oscillation of vector E, the singularity is H field-induced. If the invariant plane is parallel to the plane of the vector H oscillation, then the singularity is E field-induced. Dissipation affects H field-induced singularities much stronger than E field-induced singularities. And in TDU problem, the condition divergent S equals 0 reduces the types of possible non-degenerate singularities only to saddles and centers. And in the case of non-zero dissipation, neither saddle nor centers are possible, and three other types of singularities can be observed. In 3D problems, optical vortices in non-dissipative media have a focus saddle structure. And importantly, to satisfy the energy conservation law for a stable focus, the saddle is unstable and vice versa. That already we have discussed in three-dimensional pictures. This is the first publications related to these results and the funding. Thank you very much for your kind attention. I am ready to answer the questions, if any.
Thank you so much for your talk. Is there any question?
My pleasure.
So it seems there is no question. So it seems there is no question. Thank you so much for your talk.
Okay, thank you. Thank you very much for your kind attention again.
Thanks. Now I call upon Dr. Nicholas Malvander. His talk about how to use quantum effects to inspire with as a simple of Dr. Malvander. Okay, I just informed that Anas Otoman joined the meeting, so please let me first call upon Anas Otoman from Taiba University. A to deliver the Physics Department of Taiwan, Arabia. He received the master's degree from the University of Alberta from Canada in physics. Okay.
Hello.
Hi.
Hi. My voice is clear. Thank you for introducing me.
You're welcome. Yeah, it's so. Hi. You're welcome. Yeah, it's so clear.
Okay. So let me share the screen. Okay. Is it clear now?
Yeah, it is so clear. You can start.
Okay. Thank you. So, hi, welcome all. My topic today is about phase distributions of higher order derivative coherent state, DCS. So these are the outlines. Introduction, a quantized single mode field can be described by the Fock states. That is, if we have no excitations, we denote it as zero state vacuum, one excitation, one photon, one state, and so on. The Hamiltonian, which describe this this kind of field, is the harmonic oscillator, and is denoted here, and A is the annihilation operator, and A Dagger is the creation operator, and they satisfy the famous commutator relation. Then we know photons, they can arrive in different status. They can arrive in a pure state that is just specific number of photons, 0 or 1 or 2 or so on, or they may arrive as superposition of different excitations, or maybe mixture, a sample as denoted here in the middle. Okay, one of the famous states in quantum optics is coherent state with CS. It is well known that the closest quantum state to classical fields is the coherent state. It can be defined in different mathematical ways. One of them is being the eigenstate of the annihilation operator, and it is denoted here alpha state, CS, and it can be expanded on the Fock states as summation of different for different weights of Fock states. It has many properties that are very close to plane wave in classical physics. One of these properties, it has a minimum fluctuations for all values of alpha. That is the quadrature fluctuations in X and Y. If we multiply them, we will get always the minimum value, which correspond to the vacuum value as well. And each one of them is also in the, not in the minimum value, but in the vacuum value. It also can be defined as the displacement operator acting on the vacuum. This operation will generate the CS state. Many different states can be assumed or can be defined based on the coherent state. For example, just if we superpose two CS states, we will obtain different state with different categories, different features, truncated coherent state, not to sum to infinity, but to finite number state, filtered state. That is, we take one of the Fock superpositions out of the summation, or we can define other state being the photon added or subtracted coherent state, that we add many excitations, M excitations, or we subtract M excitations from the CS. And much more states can be defined based on these. Okay, let's turn to something else and then come back again to CS states. Let's now see this regular superposition. The regular superposition of two states can be achieved by adding up the two states and performing the normalization. Simple example is vacuum and one photon state, qubit state, if we say, or maybe we wish to add with different weights, alpha, beta, such that this state is always normalized. We define another technique to superpose. We name it the near superposition. The near superposition is a superposing technique that can be applied to continuous variable states, such as coherent state, which has a continuous variable. It is like the state is superposed to itself. It is defined as, let's see the definition. This definition represents the near superposition. This X state is a continuous variable state, and this is the same state, but with different or just slightly different parameter than the X state. So if we allow this delta X to go to 0, one might imagine that this side will cancel with the other term, but this is not happening because of the limit, and the normalization will keep it to be finite, not to annihilate each other. This small term, we name it the source of the near superposition, and the variable of the state is X as denoted. One of the interesting features about this technique is that it doesn't remove the information of the source's phase. So even after we apply, let's see, go back, even if after we apply the amplitude of the source to go to 0, still the phase of the source is not going to 0. It's not annihilated. It's present on the final expression. It can be defined alternatively. It can be defined, for example, to put the source on the second one instead of the first, or maybe divide the source between the two superposed states. They are all equivalent, even if we defined it in other ways. Performing the near superposition to CS state gives, now we are interested here to perform this technique on the CS state and see what it gives. If after calculating the resultant state, it gives this expression. We see first it has itself here, the coherent state. It is here as well in this second term. and it is superposed to its derivative. So derivative plus the coherent state with some weights depending on the phases of the alpha and the source's phase. Two interesting limits. If we allow the source phase minus the variable phase to be 0, we will obtain the derivative of the coherent state. You can see it here clearly from the expression. If we make delta theta 1 minus theta equals 0, this term will vanish, and we will only be with the first term. Another interesting limit is pi over 2 limit. That is, we make these phases differences equals pi over 2. We obtain superposition, or clear superposition with the derivative and the CS state itself. Today we are interested on the derivative limit, but let's see first what all these gives us. First, if we look at the photonic distribution, for the derivative limit, we see we have 2 peaks, and in the middle we have zero probability to obtain certain number of photons. If we allow more differences, this zero probability starts to gain some probability, and until we reach pi over 2, it has very similar distribution to boson distribution. It's not the same. It's actually, we proved in other research that it is always sub-bosonian distribution, but it has similar shape. Okay, let's talk about now other properties. Sub-bosonian distribution. It refers to photons being more likely separated than, or less actually separated than the boson distribution of the CS in the phenomenon that has not a classical counterpart. We use Q-Mendel to measure this feature. Q-Mendel is a good representation of classifying the distributions. If it equals, if it's positive, the statistics of the state is always super bosonian. If it's 0, it is bosonian statistics. If it's negative, it is sub-bosonian distribution. So we apply it to our state, and we see here the results for the phase differences of pi over 2 or pi over 3 or even pi over 4. They always being sub-bosonians. They have this non-classical feature which has no classical counterpart, as we said. However, when we have less phase differences, 0 or pi over 2 or pi over 8 or something like that, it is just in the beginning of alpha. We have it sub-bosonian, but after that it becomes the super-bosonian. Another measurement, the Wigner function. It is a distribution over phase space that provides information on whether a state can be described classically. If the Wigner function exhibits negative values at any point, the state must be non-classical. So it's distribution over the phase space, and if it has negative values, of course, if it's probability distribution, it shouldn't have any negative values. But if it has here, then that indication this state is not classical state. It cannot be generated in a classical manner. We should use quantum optics to understand this kind of state. And of course, that's why this distribution is widely called quasi probability distribution, not probability. So when delta theta is 0, we see here have negative values. We have negative values here in the middle. If we increase this phase differences, the negative values decreases as well until we reach to a significant amount of increasing, like 2 pi over 9 here. The negative value is vanishing. All the values are now positive. And for pi over 2, for example, we don't have any negative values. That doesn't mean for sure it is always non-classical, but this one of the measurements indicates that our delta theta 0 is indeed negative, is indeed non-classical. Okay, so based on these observations, we want to explore more about the near superposition. So we define the higher order of near state, that is to apply the near state more than one time. So this is the definition of the near state. Now let's call it the first order near state. The second order is to take the first order and apply the same technique to it. That is the variable of x, make it x plus delta x2 minus the same state, and so on for the higher orders. If we assume the structure of the state to be two functions, one of them is in the absolute value of the variable and the other one with the complex variable itself, then for the first order, we can prove that any state of this structure can be given as this, only substitute, and you will have the near state of the first order, and the second order similarly, but with longer expression. It has this structure. If we want to obtain the third order, it will much longer expression than this. It's actually the terms grow exponentially. The first term has 2 terms, the second has 4 terms, and the third has 8 terms, and so on for the other orders. Now, in the derivative limit, that is to make all the source phases are equal the phase of the variable, the state simply, all this complexity turns just to be the derivative of the state itself with the absolute value of the variable with some normalization constants. We name this state the derivative state. So now we apply to the coherent states. So in the coherent state, the normalization constant is found to be this. And we showed also it can be represented alternatively based on the operators as shown. We name this operator acting on the vacuum by the seed state. Why seed state? Because the displacement state is the displacement operator is known to by its name. It displaces the state. In the Wigner distribution, it displaces whatever the shape of the state displaces. We just make it farther away from where originally it is. So the seed state is really here captured the main feature of the derivative DCS states. Let's see first their linear product. Here are the first expansion of the first fourth order the zeros order is just the coherent state. It's just the vacuum displacing the vacuum. 1 is displacing the 1 photon. 2 is superposition of 2 and 0. 3 and 1. 4 is 4 superposition of 4 and 2 and 0 with specific weights. The linear product we see in the middle here, the diagonal line, the red diagonal line, it is 1. They are, if dn equals dm, they are always normalized as expected. And any diagonal line, it eventually either yield to be, or in the limit, they always give either 1 or 0 or -1. Always for all combination dm of any value of m or n. As here I tried to show, any diagonal line, if it's here in purple, that means it's -1. If it's green, it's 0. If it's red, it is 1. So in the limit, any diagonal line will tend to be to have one of these values depending on its alignment, of course. If we look at the photonic distribution, this is the boson of M0. M1, we saw it earlier. It has 1 gap. M2, it has 2 gaps. M3 has 3 gaps, and so on for the higher orders. This is the expectation value of number of photons. Let's look at the sub-bosonian statistics, the Q-Mendel parameter. We see as well here in the beginning of the or the small value of alpha, we have negative values, but after that they all super-bosonian statistics. Let's look to other feature, squeezing. A state is considered to be squeezed if one of its uncertainty quadrature, position or momentum is less than the minimum value, which is quarter. The squeezing can be studied using the linear squeezing parameter. If this parameter is negative, then the state is squeezed. Even if we try to measure vacuum, we always have fluctuations. This is from quantum nature, but it appears that we can reduce the fluctuations either of the position or the momentum if the state is squeezed. But of course, we cannot reduce both of them at the same time, but we can reduce one of them at a time. So if we looked at the squeezing properties, we see no negative values for all the DCS state. So it has no squeezing, but that makes us to look to higher order of squeezing or amplitude squared squeezing. It is associated with more localized and pronounced squeezing effect. It can be defined as this. Again, if it's negative, it has this amplitude squared squeezing. If it's not, if it's positive, then it hasn't this feature. So fairly here we see it has negative values at some regions. Here when alpha is 0, that is the seed state. It has negative values for some phases. And other phases, it has always positive values. Even if we increase alpha, here alpha, the value of alpha with the phase of 0, which has the maximum higher squeezing, we see, yes, in the small alpha, we have also the amplitude squared squeezing. Okay, let's now go to studying the phase distributions of these states. First, quantum phase distribution. It provides information about the quantum phase it is defined as, that is, we apply this phase state on our density matrix, and what we obtain for when alpha is 0, we name it here beta. When beta is 0, we see it forms two peaks and very well separated, as we can see here in the purple, for example, M10. We see here one peak and another peak here. And this is interesting that in the beginning, we thought that it might gives us a number of peaks depending on the order, but no, what appears is we always have two peaks, and these two peaks are more spilled, more separated, more distinct as the order is increased. Even here, after we increase the alpha or beta here is 2, we see the same feature appears, but the two regions are now less separated than the 0, but still they have 0 region between them as the order is high enough. We also looked at the Hesme function. It represents much information about probability distribution of the state in the phase space. It's defined as shown. When M0, it's just basically the Gaussian distribution of coherent state. As we increase the order, the same phenomena here appears. The two regions forms. You can see clearly there is two regions are being more separated as the order is increased. Here all alpha is 0. That is for the seed state. So that makes us wonder if this separation, is it really statistical, a sample like a mixture? Is it really will give us non-classicality? So that makes us look at the Wigner distribution, but in the next slide, angular Q phase function here also gives the same indication of the two regions. Then we looked at the Wigner function, and interestingly, as the order increases, we see also the two regions are forming, but here with very clear negative values with this forming. So here we see here negative values denoted in the black. But as the separation increases, as these negative values are increases as well, and they form really interesting shape. That of course means that this phase separation is far from being described classically. It is clearly non-classical phenomena that we need quantum mechanics to describe it. So conclusion, the DCS is non-classical and has unusual properties. The phase distribution forms two separate regions by increasing the order M. This has some similarities with cat states, the famous Schrödinger cat states. The unusual form of the Wigner function could help improve the quality of sensing different measurements. This is, for example, we here study the derivative limit, and the possibilities of other choices are open areas. Publications related to this topic. This is the last one, the characteristics of higher order derivative coherent states. It published in 2022. And here other related publications related to this topic. Many thanks to Professor David Yevik from University of Waterloo, Canada, for his outstanding collaboration and remarks. Taiba University in Saudi Arabia is also acknowledged for financially supporting this work. Thank you very much for listening. Any questions?
Thank you so much for your talk. Is there any question? So it seems there is no question. Thank you so much for your great talk. Now, I would like to call upon Dr. Nick. Now, I would like to call his to spin their part. Nick Hill's last function. Dr. Malvankar, we're waiting for your touch. Now I would like to invite Shiro Ryo from Meiji University, Japan, after break, and he will. Now I would like the speakers for 10 minutes, and after that, our meeting will continue. Thank you so much for your
Good afternoon, ladies and gentlemen. My name is Shiro Ryu of Meiji University, Japan. I'm chairing this session. So the next talk is made by Yuri Stefanis Yant of the University of Southern Queensland, Australia. The title of the talk is Scalar Description of Three-Dimensional Flows of Incompressible Fluid. So please, Yuri, please prepare your presentation.
Hello, give me 2 seconds. Just a second, I will prepare. It's a bit unexpectedly to me. Do you see my screen?
Yes.
All right, I can start. Thank you very much for invitation for this conference. This is my joint talk with my colleagues Yevsey Yakubovich, who unfortunately passed away last year. In this talk, we will present a scalar description of three-dimensional flows of incompressible viscous fluid. So usually when we consider a basic set of hydrodynamic equations, we consider that there is a Navier-Stokes equation for three components vector field, which is a velocity component. And also when we consider incompressible fluid, there is one more equation, which represents incompressibility condition and mass conservation in a such situation. Of course, we have to add boundary and initial conditions to set this such a set of equations. But anyway, it's interesting to find any exact solutions for this set of hydrodynamic equations. And as we know, currently only in rare cases this set of equations can be solved. What can help in this case? Usually there are two approaches which allows us to simplify this set of equations and present the equation in one scalar variable. In particular, if we consider a potential flow such that the velocity can be presented as a gradient of velocity potential phi, then the basic equation simplifies, and we can consider that Laplacian phi which equals to 0, which is a linear equation. And then we can derive from the basic set of equations, neglecting viscosity, we can arrive so-called Cauchy-Lagrange integral in such a form. Of course, in such a case, when we have only one unknown scalar function, the set of equations simplifies significantly, and there are several exact solutions to this equation, to this set of equations. But in such a case, when we consider potential flow, the vorticity is 0. And it is not quite good because in real fluid, due to viscosity, vorticity is not 0. Another interesting case is when we consider a two-dimensional flow when the velocity has only two components, u and v, which depend on two spatial coordinates, x and y. So in this case, the incompressibility condition gives us such a simple equation, and this equation can be satisfied if we introduce psi function, stream function. So in this case, this equation automatically satisfies. And from the basic set of equations, even for the viscous fluid, we can obtain one equation for the scalar stream function. And so stream function should satisfy this equation where J is a Jacobian of two functions, as shown here. And in this case, as I mentioned already, there is vorticity, only one component of vorticity, which is perpendicular to X and Y plane. This is very well known, but when we consider more complicated flows, we have to think how to introduce correctly a stream function. And it depends which kind of flow we consider. For example, in cylindrical coordinates, in general, velocity field has three components, but taking into account incompressibility equation, we can present the divergence of u in such a form. And then it depends. If the velocity flow depends only on radial and azimuthal coordinate, then we can eliminate this equation. It satisfies automatically after introduction stream function in such a way, and then we will have an equation for the stream function. Here it is shown, and there is a vorticity, only one component of vorticity. And another case, if velocity field depends only on z and r, again we can introduce stream function with the help of these two equations, and then the basic equation reduces to the equation for the vorticity. Only one component of vorticity exists, and we obtain such an equation for vorticity. In many other cases, we can see that vorticity can be introduced if the velocity field depends of two coordinates only, but it takes some efforts to find a correct representation of a stream function. Then when we have a condition of incompressibility, this means that velocity field u is a solenoidal vector field. So in other words, such velocity field can be introduced, can be denoted as a curl of some complementary vector field A, where vector field A is so-called vector potential. Vector potential, in this case, after introduction of a such vector potential, this equation satisfies automatically, but now we have some degree of freedom because the vector potential is not defined uniquely. In other words, we can add to the vector potential a gradient of any scalar function. In this case, anyway, curl of gradient is 0, and we have such calibration. Then, using this ambiguity, we can exclude one of the components of the vector field A. We can choose function f such that one of the components equals to 0. And so, without loss of generality, we can assume that the vector potential has only two components. So this means that with the help of two component vector potential, we can describe any arbitrary three component vector field. This is very well known. The velocity vector in terms of the vector potential can be presented in such a way, and so we can see that indeed velocity vector depends only on two scalar functions. And if we calculate the vorticity, in this case, vorticity has all three components. So, as I mentioned already, without loss of generality, we can describe any velocity field by with only two scalar functions. This is quite general equations and quite general approach. Then, if we consider a particular case when vector potential has only one component, in this case, velocity vector simplifies and it has only two components. We can see from this equation if one of the components equals to 0, so this can be simplified. Then we obtain such a velocity field. And in this case, this scalar function a of x is nothing but a stream function. So there is quite so-called scientific approach to determine a stream function for any flow. The vorticity in this case can be calculated, and it has basically only one component because two other components are trivial. And in the case when they do not depend on x coordinate, we obtain only one component, which is perpendicular to y and z plane. So in this case, vorticity can be presented in terms of stream function with the help of this formula. Now, let us consider another case. And this is a new idea. What if we assume that components of vector potential are related somehow with each other? We assumed that vector potential is a solenoidal vector. If we make such assumption, this means that between the components of this vector has such connection, such differential link between them. And so again, if we have such an equation, this means that we always can introduce an auxiliary function theta, which is similar to a stream function, and introducing function theta in such a way, we satisfy this equation automatically. But then we have to satisfy all other components of hydrodynamic equations. First of all, we can present a velocity field in terms of this scalar function theta. So we can see that velocity field in this case is three components, three-dimensional, the three components, and vorticity field in such a way, in such a case, has only two components. So this approach is a little bit more general because in this case we can describe with only one scalar function, we can describe three-component velocity field and two-component vorticity field. Now we have to construct the equations, the equation which function theta should satisfy. So to this end, let us consider a hydrodynamic equations, in particular Navier-Stokes equation, but in the Helmholtz representation. So if we take curl of the Navier-Stokes equation, we obtain such an equation which is very well known as the Helmholtz equation, where omega is the vorticity. And then if we substitute here velocity and vorticity field as they are introduced here, so after that we obtain three component of these equations, three scalar equations, which is shown here, where delta perpendicular stands for a Laplacian in x and y plane. And also we have here delta, which is a three-dimensional Laplacian. So function theta should satisfy these three equations, but these equations can be satisfied. If we look at the last equation, we can see that this equation actually can be presented as a Jacobian of two functions. This function, Laplacian perpendicular of theta, and the total Laplacian, the full Laplacian theta, and Jacobian equals to 0. So this equation is equivalent to such Jacobian representation. But it's very well known if the Jacobian of two functions equals to 0, this means that these two functions are related somehow with a scalar function. So we can assume that one of the components of Jacobian, delta theta, is some arbitrary function of another component. And so this equation can be presented in such a way where h of x is an arbitrary function. At this moment, it is more convenient to introduce a function phi, which we call a quasi-potential. So function phi is simply z derivative of theta, as shown here. So after that, after introduction to such a function, we obtain that the last equation can be presented in such a way where arbitrary function h depends on the derivative of this quasi-potential. But we have also two other equations. So this one gives quasi-potential, and we have these two equations. It is easy to show with simple manipulations that these two equations reduce to only one equation for quasi-potential, this one, where p is an arbitrary function of z and t. So to solve the hydrodynamic equations, we have to find a solution of two equations. One of them is this equation for quasi-potential, which contains arbitrary function h, and there is another equation for the quasi-potential, which contains arbitrary function p. So we have enough degree of freedom to obtain a solution of these two equations for one function phi. Then, if we know function phi, we can present a velocity field, which is a three-component velocity field, and vorticity field, which has only two components, as shown here. And by the way, it is understandable why we call function phi quasi-potential, because if we choose in particular this arbitrary function h identically equal to 0, we obtain that phi is just a real hydrodynamic potential, and in this case vorticity automatically equals to 0 as required. And then I'm reminding again that we have to solve this set of two equations, of simultaneous equations, and then of course these equations must be compatible, and the condition of compatibility of two equations reduces to such fairly complex and nonlinear equations. So it is much easier to consider these two equations independently and try to find solutions of this set of equations rather than trying to find a solution of this complicated equation. So we can then manipulate with the functions p and h and try to obtain solutions of hydrodynamic equations. In particular, if we choose that p is 0, and if we consider in viscid fluid nu is 0, then we obtain such a set of two equations for non-viscid fluid. In this set of equations, instead of arbitrary function p, we obtain arbitrary function q, which is arbitrary function of x, y, and t. Then, using the basic set of equations, we can derive from the primitive equations, from the Navier-Stokes equation, we can derive a generalized Cauchy-Lagrange integral, which looks like this now, but it is very interesting that this Cauchy-Lagrange integral depends arbitrary function r of z and t. This arbitrary function is related to function p. So there is such a simple relationship. So actually we have the same arbitrary function p and arbitrary function h. But what is interesting that this Cauchy-Lagrange integral is applicable to the whole volume of the fluid. And it is applicable also to viscous fluid, where phi here is a potential of external fields. For example, this can be considered as a potential of electric field or potential of a gravity field, whatever. So we have such an integral. And in the particular cases, this integral, if we set h equals to 0 and r equal to 0, we obtain Cauchy-Lagrange integral for the potential fluid. So we can see that the general Cauchy-Lagrange integral reduces to such an integral where function r can be absorbed into definition of the hydrodynamic potential. So we can compare the analytical forms of Cauchy-Lagrange integral for in-viscid fluid with the generalized Cauchy-Lagrange integral for viscous fluid and non-stationary fluid, non-stationary motion of a fluid, where phi can be a function of time and spatial coordinates. So in this generalized Cauchy-Lagrange integral, we have this additional term, and function r now depends not only on time, but it depends also on spatial coordinate. So we know that in the case of a vertical flows, there is a so-called Bernoulli integral, and Bernoulli integral can be presented in such a way. And so this Bernoulli integral, when we consider two-component fluid, can be presented in terms of stream function in such a way. So now again we can compare this well-known integral for the stream function in the case of two-component velocity field with the generalized Cauchy-Lagrange integral for non-stationary fluid, because a Bernoulli integral can be derived only for stationary in-viscid flows like this one. So we can see that this generalized Cauchy-Lagrange integral reduces both to the Bernoulli integral and to the in-viscid Cauchy-Lagrange integral for the potential flow. Now we can consider a particular case when this arbitrary function h is just a linear function of its argument, where lambda is some constant. So in this case, we have, instead of Laplacian equation, we have such an equation. And also we need to solve another equation for the quasi-potential. We can see that if we introduce new variable zeta, which relates to z through this relationship, we obtain that the first equation can be presented as Laplacian equation, and we have also another equation like this one. But we should not be confused, because in this case, despite of this simple Laplacian equation, the velocity components in this case, the velocity components are not simply gradient of this quasi-potential. So for such a linear case, we can also obtain, we can simplify the Cauchy-Lagrange equation, Cauchy-Lagrange integral, which can be presented in a such equation. And as I mentioned already, when we introduce a new variable zeta, the velocity, despite phi satisfies Laplace equation, but velocity field depends on three components, and it is not simply a gradient of function phi. It depends also on this factor. But when lambda is 0, in this case, it reduces indeed to the potential flow. But this is a trivial case. When lambda is 0, vorticity is also 0, and we have a usual potential flow. But in general, when lambda is not 0, we obtain such an interesting velocity and vorticity components, and we can see that vorticity now has two components, and velocity has 3 components. Then the pressure can be presented in terms of these 2 arbitrary functions R and Q. And so we have such an equation for the pressure where phi, I'm reminding again, this is a potential, given potential of external fields. Here I can present a few examples. The first example is so-called Invisky-Kolmogorov law, when we have a periodic structure for the velocity field, such cells of velocity components. For the vorticity field, we have corresponding carpet structure, and for the pressure, we have such a representation. And looking at this figure, we can see that one column or one row of this field can be presented within a pipe, within such plane pipe. And so it is possible to obtain a solution for the vorticity, for the velocity, vorticity, and pressure as a periodic solution in a long pipe. Then there is one more example where quasi-potential can be presented in such a way as a function of x, y, and z. And then this is in general non-stationary fluid flow, where this exponent alpha depends on the viscosity parameter nu. Nu is the kinematic viscosity of a fluid, and k is arbitrary parameter. So velocity.
Excuse me.
Yes.
We are running short of times.
Okay, so I'm finishing.
Yes,
so
okay.
The velocity field can be presented like this one, and it has all 3 components, I, J, and K, and vorticity field can be presented in such a way with 2 components. So basically that's it. I can show only some figures for the vorticity and for the particle trajectory in such a complicated field. So there is a room for the generalization and finding new exact solutions of hydrodynamic equations, which can have 2 vorticity components. So that's it, and I'm ready to answer your questions. Here you can see publications on the topic.
Okay, thank you very much. And then other any questions or comments on his talk? Nothing.
Okay.
No
Everything
question.
is
Okay,
clear.
thank you very much for great
Thank
talk.
you. Yeah, thank you. Bye-bye.
Thank you very much. Bye-bye. So next presenter is Monica Sinha, IIT Jodhpur, India. The title of the talk is Strange Stars, Beta Model of Compact Stars with Recent Astrophysical Observations. So please prepare for presentation.
Is my screen visible?
Yes, go to the presentation mode.
Okay. Is it okay?
Okay, thank you.
Okay. So good afternoon, everybody. Title of my talk is Strange Stars, the better model of compact stars with recent astrophysical observations. The collaborators for this works with me is my PhD student Anil Kumar and my ex-PhD student Vivek Barua Thapa. So the unique laboratory in the universe for highly dense matter is astrophysical compact object. Compact stellar object is the end product in the stellar evolution of massive stars of mass greater than around 8 solar mass. After the exhaustion of the fuel for nuclear fusion, the stars contract up to an average density of around 10 to the power 14 gram per centimeter cube due to the immense gravity. And at this stage, their mass is around 1 to 2 solar mass. However, their radius is very small around 10 kilometers. So as these objects are very compact in size, they are known as compact stars. In 1971, A.R. Bodmer gave the theory of collapsed nuclei. He argued that the collapsed nuclei may have less binding energy than the ordinary nuclei. In his definition, the collapsed nucleus is a system with much smaller radius compared to an ordinary nucleus with the same number of nucleons. In his opinion, the existing theory of QCD does not prohibit the existence of collapsed nuclei. Yet we cannot see such kind of things in our surroundings. The reason behind this may be that the potential barrier between the ordinary nucleus and the collapsed nucleus is such that the lifetime of ordinary nucleus is greater than the age of the universe. In 1984, Edward Witten independently suggested that early universe may have undergone a first-order phase transition from high-temperature, highly dense quark phase to low-temperature, dilute hadronic phase. He explored the possibility of existence of strange quark matter at zero pressure and zero temperature. While it is generally believed that laboratory production of strange quark matter may be difficult, it is agreed that dense astrophysical objects are favorable environment for strange quark matter. However, we observe up and down quarks confined within the nucleus, which we see within the nucleons, which we see in plenty of abundances in our surroundings. That means that the confined up-down quark matter is not the stable ground state of matter. So that means that the energy per particle of deconfined quark matter with only up and down quarks is greater than the energy per particles of confined up and down quarks, that is baryon. However, the minimum energy per particle for deconfined up, down and strange quark matter at certain high density is less than the binding energy of ordinary matter. This makes the deconfined strange quark matter true ground state of matter at high density. Here we see the curves for energy per particle with number density for both up-down quark matter and up-down strange quark matter. We see that the minimum energy per baryon for up-down quark matter is greater than the energy per baryon for most stable element iron. However, when the density of up and down deconfined quark matter is increased, the Fermi momenta of up and down quarks also increase. So after some density, the Fermi momenta of an up and down quark exceeds the rest mass of the strange quarks. So at that density, the strange quarks appear, lowering the energy per particle of that matter. So in this way, the deconfined strange quark matter appears with less energy per particle compared to even the most stable element iron. Consequently, at high density, the deconfined up, down and strange quark matter is true ground state of matter. Hence, the people talk about compact objects composed of this kind of deconfined strange quark matter, which is known as strange stars. We explored the properties of strange stars from the recent astrophysical observations. The preliminary idea of strange quark matter was understood by MIT bag model. This is the simplest model of deconfined strange quark matter. In this model, the quarks are assumed to be confined within a bag which separates the quarks from the vacuum. And quarks inside the bags are assumed to be free. So the thermodynamic potential omega for the matter is the sum of all the thermodynamic potentials of all the quarks plus the back pressure B. And the energy density and pressure of the matter with this back model are given by these expressions. Now with this model, as the quark matter is self-bound, the quark stars are much more compact than the normal hadronic star, ordinary hadronic star. However, in this model, the maximum attainable mass of the strange star cannot approach the observed lower limit of maximum mass for the compact objects. Not only that, from the point of view of QCD also, the idea of free quarks inside the bag is also not very correct. So later on, the interaction between the quarks were incorporated in this model with the coupling parameter A4, and the non-perturbative nature of non-perturbative nature of the QCD was incorporated by was included inside the effective back pressure B effective, and this is known as the modified back model. Another way to include the interaction between the quarks is by vector back model. In this model, the model can be expressed by Lagrangian density, which is shown here. In this model, the quarks interact among themselves via a vector particle, which is denoted here by V mu, and the coupling interaction between the quarks is parameterized by the coupling parameter GQ2V, and the vector particles may interact among themselves via the self-interaction, which is shown here by the last term. All the parameters of these two models, vector back model and the modified back model, can be determined from the criteria of stability window. The criteria of stability window demands that the energy per particle for UDS quark matter should be less than the binding energy of iron 56, but the energy per particle for up-down quark matter should be greater than the iron 56. So from this criteria, the parameter space for these two models have been shown here by these two tables. So this is from the QCD point of view, and from astrophysical point of view, this parameter space can be further narrowed down from the astrophysical observations. Here the mass radius curves for modified back model are shown. So we see that the decreasing value of A4, the coupling parameter A4, stiffens the matter. This is very natural because with the increase of the attractive potential, that means that with the increasing value of A4, the matter softens, and matter softens with the less value of back pressure. So the stiffens. So the softest matter, which satisfies all the mass radius relations, is with the A4 maximum attractive potential A4.9 and the lower values of back pressure B. In the vector back model, we have seen that if the repulsive vector interaction is less than GV is equal to 0.3, then the matter is too soft to attain the observed lower limit of maximum mass. With maximum vector interaction with GV is equal to 0.3, the matter is so stiff that maximum attainable mass falls within the observed limit for entire allowed range of back pressure. However, even with GV is equal to 0.3, if the vector particle interaction with strange quark decreases with XP is equal to 0.4, then The matter softens and the mass radius relations are satisfied only with lower values of the back constant. If we increase the back constant with less strange quark interaction, then the matter becomes too soft to satisfy the observed mass radius relations. We also see that the repulsive self-interaction between the vector particles stiffens the matter further. Next, we come to the constants coming from the recent gravitational wave observations. Till today, 2 gravitational wave detection events have been observed, which emerge from the binary neutron-star mergers. They are listed here. From neutron-star merger events, the mutual tidal deformability of the participating stars can be estimated, from which the matter properties, especially the softness of matter, can be constant. For the event GW 190425, the upper limit of the tidal deformability of the participating stars is to be 600, and the mass range for the participating stars are from 1.6 to 1.87 and from 1.46 to 1.69. With the stars in these mass ranges, the theoretical calculated mutual tidal deformability will have calculated, and we see that with the stiffest equation of state for both the models come under the observed maximum limit for 600. So that means the matter with stiffest equation of state theoretically gives the tidal deformability value less than the maximum limit of 600 with modified back model and vector back model, both the models. So that means that this observation does not constrain the theoretical model further. For the event GW 170817, the maximum bound for mutual tidal deformability is 900, either 900 or 720 from 2 different calculations, and the lower bound of the tidal deformability, mutual tidal deformability, is 400. And the mass range for the participating stars is from 2.73 to 2.78. For this equation of state, also we have calculated theoretically. For this event also we have calculated theoretically the tidal deformability from both the models, from modified back model and vector back model. With stiffest parameter set in modified back model, in vector back model, the mutual tidal deformability, with modified back model, the mutual tidal deformability is far above the maximum limit, observed maximum limit of the tidal deformability. And with more attractive coupling with A4 is equal to 0.8, we see that the theoretically calculated tidal deformability marginally satisfies the observed upper limit of tidal deformability. But with the softest matter, that theoretically calculated tidal deformability come under the maximum limit. For vector back model, also we see that the stiffest matter is too stiff to produce the mutual tidal deformability under observed maximum limit. So from these observations, the parameter space is narrowed down to the softest boundary of the matter which satisfies the mass radius relation for both the models. From this observational upper limit of mutual tidal deformability, the radius of the participating stars may be estimated, because if we plot the mutual tidal deformability with the radius of one of the participating stars for different models of the matter, then we see that tight correlation between the points for both the events. So here this upper curve shows the event GW 170817 and the lower curve shows the event GW 190425. So here we see that for the maximum limit to be lambda tilde to be 900 for the event GW 170817, the upper limit of radius of the participating star will be 12.04 kilometer, and for the upper bound of the mutual tidal deformability lambda is equal to 720, the upper limit of radius of the participating star will be 11.62 kilometer. And from the lower bound of the tidal deformability of 400, that lower bound of the radius of the participating star will be 10.57 kilometer. And from the GW 190425 event, with the upper limit of mutual tidal deformability 600, the maximum limit of the radius of the participating star will be 13.41 kilometer. From gravitational wave observation, it is also estimated that the upper limit of tidal deformability of canonical 1.4 solar mass star to be 800 or 580 from different calculations. We plot the tidal deformability of a single star with its mass. So from here also we see that when the matter is the softest, the matter model is the softest, then it satisfies both the limit for both vector wave model and modified wave model. Theoretically also we can constant the tidal deformability of 1.4 solar mass star from the upper bound of mutual tidal deformability lambda tilde, because if we plot the lambda tilde, the mutual tidal deformability with lambda for 1.4 solar mass star for different models, different parameterizations and models, then also we see a tight correlation between them. So from upper bound of lambda tilde to be 900, the upper bound of lambda 1.4 is 800, and for lambda tilde to be upper limit of lambda tilde to be 720, the lambda 1.4 is 634. And from the lower bound of lambda tilde to be 400, the lower limit of lambda 1.4 is 346.
Excuse me, time is limited. Do you need some time more?
Just one slide.
Okay, thank you.
With this range of 1.4 solar mass tidal deformability, we find the range of compactness of a 1.4 solar mass star. This is the plot of 1.4 solar mass tidal deformability with compactness of the star for different models or parameterizations. Here also we see tight correlation between the points for different parameterizations and different models. So from here also we can estimate the range of the compactness for 1.4 solar mass star from 1.75 to 1.99. So this gives very narrow range of compactness of 1.4 solar mass star. So in summary, we have studied the compact star properties in light of the recent gravitational observations. At higher density, the matter composition may be of exotic nature, that means deconfined strange quark matter. We considered here modified back model and vector back model for including the interquark interactions. With these two models, we fix the parameters of the models from the astrophysical observations, including gravitational wave observations. And not only that, we can predict the properties of individual stars from this study. Thank you.
Okay, thank you very much. Any comments or questions from the floors? It seems there is nothing. Okay, thank you very much for your great talk.
Thank you. Bye.
The next talk is made by Dr. Nikki Marvankova in place of Manpen Wu. The title of the talk is The Study of Weld Information and Defects of Horizontal Oscillating Laser TIG Hybrid Welding.
Do you all
Okay.
see my slides?
Yeah,
Yeah.
could you start now?
Yeah, so my title is very different than you read. So I study bacteria which can transfer electrons outside their body. And I'm a physicist by training. I'm a professor at Yale. And I'm working on how the quantum effects play a role in the way these bacteria grow and survive. So the title of my talk is How do bacteria use quantum effects to breathe and respire without oxygen, using these structures which we call protein nanowires, which we have found to act as a quantum materials. So this is the first picture I'm showing you of this protein nanowire. Do you see my pointer, or do you want me to highlight a pointer? Okay. So what we discovered, these bacteria have these hair-like appendages on their surface, and they have a chain of heme molecule, just like how we have hemoglobin in our body, which makes our blood red. Where these bacteria have this chain of this heme that basically moves electron in this nanowire. And the other aspect of my lab is to work on how can we image these electrons and the forces exerted by the cells on the surfaces. And using this knowledge, can we figure out how electrons move in the system? What is the underlying physics of these models? So let me first start by showing that why are these microbial nanowires are important. So the model bacteria we study in the lab is called Geobacter. Geo is earth, and this is one of the most common bacteria found in all the soils and sediments all around the planet. And this bacteria uses these wires to directly bind to minerals in the soil as electron acceptors. So just like how we use oxygen to breathe, these bacteria are using these rocks to breathe. And in order to breathe, they have to basically get rid of electrons left behind during metabolism. And in our case, we just use oxygen, whereas these bacteria grow where there is no oxygen. So they use these wires to transfer electron. But what makes this so surprising is the electrons move at a ultra fast rates, less than 100 femtosecond in these wires. And they move also over distances of micrometers, which had not been seen before in a biomolecular system. And this is where we need to invoke new physics and the principles of quantum mechanics to explain this electron transfer, which has been the focus of my research. In addition to this fundamental importance, these bacteria are very important for our environment. So they are important for our cycling of mineral, to get rid of toxic compounds from the environment, corrosion, and also conversion of waste product into methane or electricity. And these processes occurs at rates and distances which we just cannot explain by classical models of diffusion. And this is where we have to invoke nanowire. And finally, these nanowires are also important to make a new kind of living electronic materials. So these materials have a power where we can use them to build materials which can self-repair and defect-free. and we can assemble them just using bacteria. So let me tell you how are we going after this. So we use bacteria as a factory to make electronic and photonic materials, and we can make them at a very fast scale because these bacteria are able to make them at equivalent to 5 seconds to make 1 gigabyte chips. These materials are flexible, they can self-repair and replicate or self-assemble. And these are different applications we are targeting in the laboratory. So we are focusing on how can we use nanowire to sequence a DNA, to use computing, light harvesting, or even the sensor. So this bacteria can convert glucose or humidity into electricity using this nanowire. And we are focused on understanding how does that work and how bacteria use these wires. So the focus is like to answer this main central question, that how can we connect living systems to electronics, both efficiently and also at a large scale, because there's existing methods, which are based on silicon electronics are either imprecise, slow, or expensive. And this is really a critical question for all kind of health monitoring, such as if you want to monitor the blood glucose or oxygen in your body, or if you want to sense the environment like pH or carbon dioxide, to synthesize materials or to produce energy. Whenever we want to use living systems, we need to hook them up with electronics. And what we think is these bacteria found a solution billions of years ago. So these bacteria have evolved these nanowires to basically connect to the outside environment electronically so that they can transfer electrons to minerals in the soil and keep breathing, keep respiring. And they do that by polymerizing these cytochromes into these nanowire system. So on the left, I'm showing you an image of the bacteria. It's an electron microscopy image. And the things you see in the red are actually the, so these red filaments are the, let me get the pointer. So these are these hair-like filaments on the surface of the bacteria, which allow them to move electron. And we are using these nanowires as a building block to make different materials. So today I will talk about 2 different nanowires we have found in our laboratory. One behave more like a semiconductor, whereas other behave more like a metal. And we are using them to build these different kind of nanowires, like a self-repairing materials. And what's really attractive about them is they combine all these different properties in one material. So they can self-repair, or they can non-toxic, flexible. They're intrinsically functional, so you don't need to coat them with other material. They work under very extreme environments, such as very low pH, acidic, aqueous environment at high temperature. We can make them at low cost and high yield. And also because they're made of protein, they are biodegradable. So let me quickly tell you how we discovered them. So in early 2000, it was discovered by Derek Lovely lab that if you grow these bacteria under conditions where they need to exhale these electrons out, when you grow them on mineral like iron oxide, they specifically start making this filament. And my own work was in a biofilm when these bacteria form these communities of called biofilm. I was able to show that they have a very high electron conductivity comparable to conducting polymer. However, these nanowires were thought to be made up of a completely different protein called pili, because cytochromes were not known to form these filaments at that time. So recently, my laboratory was able to study this pili, where we actually demonstrate that these bacteria do not show pili on their surface under the condition called extracellular electron transfer, or EET. And if you overexpress them under some artificial condition, then we can use a technique called cryo-electron microscopy to solve their structure. And when we saw the structure, we found that they are made up of 2 different proteins called this pili-N and a pili-C, which one I'm showing you in yellow and other in blue, and they come together and form a filament. And their structure is more similar to something called a secretion pili, which are involved in pushing the proteins out. And these villi have a very low electron conductivity. So if you measure their electric current as a function of a voltage, they show a low conductivity, which is consistent with their structure that they do not have any path for electrons to go. So the aromatic amino acids are too far in this villi to move electrons efficiently. Compared to the cytochrome nanowires I discussed before. So then the question is, how do they bacteria can transfer electron, and what are these nanowires are made up of? So my student Patrick developed a method where he was able to basically build a battery out of bacteria, where he can grow a biofilm under a condition where they overproduce a lot of this nanowire. And the reason they do that, because these bacteria are growing on top of each other, and they're basically are forced to transfer electrons over 100 times their size. So if you think of, in human terms, we cannot breathe oxygen, which is like 100 times, farther from us, but somehow the bacteria can use, their electron acceptor over size, and this requires them to produce a lot of this cytochrome. And that's why they look very red in color, just like, our blood looks red in color because it has a lot of heme molecule. Just like this bacteria are also very, very red in color. So using this method, we were able to take this bacteria, separate it. Yes. Yeah. And separate these wires, and then measure the electron transfer, purify them using a technique called size excision chromatography, and use them to pure this nanowire, and use that method. And this really allowed us to study these nanowires very accurately by getting a pure protein. And we were able to use that in collaboration with Fenbing Wang from Ada Gelman group and Alan Hogbam group, where we use this cryo-electron microscopy technique to discover that these nanowires are made up of a cytochrome protein, which form this continuous chain that allows them to move electron. And they look just like our, phone charger or any other wire, where the hemes form a continuous chain, and the protein just wraps around, surrounding them to move electrons. So you can think of this protein as an insulation to move them around this wire. And these heme molecules are very close to each other. So they are stacked within van der Waals distance, like a 3.5 angstrom, that allows a very efficient electron transfer path through the electron. So this bacteria makes over 100 kinds of, cytochrome molecule, but the one we discovered to form nanowire is the only one essential for bacteria to grow in the natural environment, which makes sense that this is the cytochrome they need to make nanowire. But there is another cytochrome these bacteria need when they grow on electrode to generate electricity. And we were able to show that this cytochrome also makes nanowire, and it has 1,000 times higher conductivity than the one important in natural environment. And this is because here the hemes form a linear chain, and they form a much efficient way to move electrons along these wires. And how does this wires explain how can this bacteria go? So this bacteria need a lot of volume around them in order to grow, and having this wire can allow them to move electrons all along their distance. And that is what allows them to, meet their metabolic need to move electrons. My student Aldo found that these nanowires are actually require pili protein to push this nanowire out. So here I'm showing you a protein gel where EC is extracellular protein, which are outside the bacteria, and PP is inside the bacteria, the periplasm. And the wild type bacteria shows this OMCS nanowire outside. But if you delete the gene which makes this pili, then this protein gets stuck inside the bacteria. And that is true for the other protein, which also makes nanowire. And if you replace this native pili with some other pili, again, we see the same defect. So what this work suggested that this pili actually act like a piston to push these nanowires out, just like how other bacteria use this pili as a piston to release molecules like a toxin. And this is the model now we are testing, where the pili is acting like a piston to push these nanowires out, and the electrons actually move through these cytochrome molecules to polymerize, and these pili are actually carrying these cytochrome towards them to move the electron. And now we are testing this model with several additional experiments. So I want to show you that in addition to move electron, these bacteria can also use cytochrome to store electrons. Just like how we use lungs to store oxygen, these bacteria can use these cytochromes to actually store electron with capacitance very comparable to synthetic supercapacitor material. So here we had used different, genetically engineered strains with different amount of cytochrome. And the blue is the capacitance I calculated using, each heme as a 1 electron storage unit. And the red is the capacitance I measured. And the green is how many cytochrome heme these bacteria have. And you can see there is a simple correlation between the more hemes you have shown in green, you get higher capacitance. And it agrees very well with the capacitance I calculated using this simple model. So what are we doing now is using different probes to control these electrons in this nanowire. With the ultimate goal is, can we use that to control the growth of the bacteria and how fast these nanowires are going? So we have used different probes like electric field, changing pH, shining light, and also cool them. And in each case, we see 100 to 1,000-fold increase in conductivity. And in the interest of time, I'm just going to show you a couple of results we have found. First is cooling. So typically, if you cool any material, which is not a metal, you will see a large decrease in conductivity. Whereas the way we do this measurement is we separate these filaments from the bacteria, and we put them on a device with like a multiple gold electrode, so that we can measure the intrinsic or a true conductivity of the system. And when we do that, we found that the conductivity actually increases 300-fold instead of getting suppressed. And this effect was because of the hydrogen bond. So if you deuterate them, we don't see this increase. And my student Peter was able to develop a model by demonstrating that as we cool them, there is a change in the hydrogen bonding network, which is shown here in different color, from pink to a green color. And that actually makes the hemes much planar, and that increases their electric field shown by the arrow, and that changes the heme reduction potential, and that could explain the increase in conductivity. And my postdoc Matthew is now using different models to understand this better, and we see that the models are just not able to explain the experiment. So we see 1,000,000-fold difference in conductivity shown in the dotted line than all the different models we have been using so far. So there are a couple of computational studies which have suggested that maybe we need to invoke quantum effects to explain this high conductivity. And now we are evaluating these different models to use the role of quantum effect. And to directly probe that effect, we use photo excitation. So my student Catherine, she grew the biofilm on the electrode, and in collaboration with my former postdoc Jans, they were able to show that these bacteria are showing photoconductivity. So as you shine the light, there is an increase in their conductivity, which persists for hours. And my colleague Sibeli Burialchin was able to show at individual nanowire, there is a 100-fold increase in conductivity as you shine the light. And Jans was able to use transient absorption spectroscopy to show that these nanowires move electron at ultra fast rate within few hundred femtosecond, something we just cannot explain using classical physics model. And the Matthew did calculation to show that the electron transfer rate is around 100 femtoseconds per second, close to what it's measured experimentally, where electrons can just delocalize between these heme. And now we are studying this process in more detail. What's exciting is these nanovirus are just not limited to one bacteria. We found that they are present in many different bacteria, which are important for our climate, including bacteria which eat up all the methane in the environment so that the temperature will not rise. And we have found that these bacteria also use these wires to exchange electrons among each other. So here we had taken two different bacteria, like a green and a red, and we found that they can actually exchange electrons among each other via this nanowire. And now we are evaluating whether this process is also important in how these microbes produce or consume methane via this nanowire. So I want to summarize that this Geobacter makes these pili filament which have a low conductivity, and they are actually are inside the bacteria, and they serve as a piston to secrete this nanowire. And if you apply electric field to biofilm, it switches bacterial production to 1,000-fold more conductive nanowire. And both these nanowire genes are widespread, suggesting many different bacteria could be using this wire. And with that, I want to thank all the students who did the work. And this is a very interdisciplinary work, so I'm very grateful to have students from very different backgrounds and my collaborators and funding agencies. And thank you for your attention.
Okay, thank you very much for your nice talk. Any questions or comments on his talk? Well, I have a question.
Yeah.
For your nanowires, how about the uniformity?
So that's a great question. So how uniform these nanowires are? So each nanowire is basically identical to other nanowires. So in order to get these structures of this cryo-electron microscopy, we need to collect over 100,000 images of nanowires. And each of those nanowires show nearly identical structure. So we don't see any variation from one nanowire to another nanowire. So somehow nature has really perfected this machinery, and they make them at a very high precision, rate. Does that answer your question, Dr.
Yes,
Ria?
so nanowires made by bacteria performs like the machine-made nanowires. I understand it correctly?
Yeah, they perform better than machine-made because there is very high fidelity. So there is no defect, there is no mistake in making nanowire.
I see. Okay, thank you. Any other questions from the floors? It seems there is nothing. Okay, thank you very much for a great
Thank
talk.
you so much. I very much appreciate.
Okay, next talk is made by Sidjem Göksek Sarak, Akdeniz University, Antalya, Turkey. And the title of the talk is Possible Effects of Cell Phone Radiation on Brain from Behavior to Molecules. Could you prepare to present? Okay, could you go to the presentation?
Hello everyone.
Yeah, could you go to the presentation mode?
Yeah. Did you see my screen?
Yeah, it's okay, thank you.
Okay, hello again. I'm Çiğdem Gökçek Saraç from Akdeniz University Department of Biomedical Engineering, Ankara, Turkey. So today I'm gonna explain one of our research that's investigating the possible effects of cell phone radiation on brain, especially from the aspects of behavior and the molecules. So as we all know, the brain is the complex organ, complex part of the human body actually, that controls the memory, emotion, motor skills, breathing, temperature, hunger, and every process actually that regulates our body. And it is the anatomical basis of thinking, feeling, wanting, pursuing, as well as learning and memory. And one of the important brain structure is the hippocampus, and hippocampus in the mammalian brain is very important for the research area in cognitive neuroscience. So in cognitive neuroscience, there are two terms. One of them is learning and other one is the memory. And learning and memory are closely related concepts. Memory is essential to learning, but it also depends on learning because the information stored in one's memory creates the basis for linking new knowledge by associations. And there are different types of memory. For example, explicit memory, implicit memory, semantic memory, episodic memory, and so on. And the central cholinergic system in the brain plays an important role performing the hippocampus-dependent behavioral tasks in which learning and memory performances are evaluated. And acetylcholine is the first neurotransmitter discovered, and it is the most crucial neurotransmitter involved in the mediation of cholinergic neurotransmission as well as the regulation of the cognitive functions. And there are especially three major central cholinergic biomarkers that are responsible for the biosynthesis, transportation, and the degradation of the acetylcholine, which are called cholinacyltransferase, vesicular acetylcholine transporter, and acetylcholine esterase respectively. And that is why in the present study, we focused on these biological markers. And behavioral neuroscience, actually, it is the area studying the biological basis of the behavior. It's the area try to answer how the brain affects the behavior. And this area is the study of neural basis of behavior, or how the brain managed to produce certain actions and sensations. And there are most common behavioral tasks, as you see from this figure. Morse-Water maze, radial arm maze, Barnes maze, Y maze, and T maze are the most behavioral tasks is used for the area of the behavioral neuroscience. And one of the another important task is the object location test, which we used in the present study. The object location test is used to examine both short-term and spatial memory of rats. And it consists of three stages: habituation, training, and the retention phase. And in the retention phase, as you see from the figure, one of the objects has been relocated and rats were allowed to explore the objects for 5 minutes. And here, subjects are expected to spend more time exploring the relocated objects. And the rats' behavior were monitored by the video camera system. Etovision is the popular video camera system for that area, fixed at the ceiling. And in another important maze is the Y maze. It is again widely used to assess the both short-term and spatial memory of the rats. And in the Y maze, testing occurs in the Y-shaped maze, as you see in the figure, with three black identical plastic arms. And during the first sessions of the experiment, one arm called as novel arm, and it was completely closed. And rats were allowed to explore the other two arms for 15 minutes. And after a delay, all arms were reopened and rats were allowed to freely explore the three arms for 5 minutes. And during the second sessions, subjects with intact spatial memory are expected to make the first turn into the novel arm and spend more time exploring this arm. And again, the behavior of the rats were monitored by the camera system. And as you know, more than 3 billion people worldwide utilizing the cell phones. And during the talking mode, cell phones are kept near the user's head. And therefore, electromagnetic radiation, EMR, can penetrate 4 to 6 centimeters deep into the human brain. And alongside the benefits of these new technologies in the communication industry, whether the EMR raised by cell phones has any adverse effects on brain functions, especially on cognition and behavior, is still a hot topic of the investigations. And till date, there is a little knowledge about the effects of radiofrequency electromagnetic radiation on cholinergic functions in rats. Therefore, in the present study, our objective was to investigate the possible dose-dependent effects of 2.1 GHz RF-EMR exposure on both rats' behavior and hippocampal levels of main cholinergic biomarkers. And for the subjects, we used 3-month-old albino male Wistar rats. We have 3 groups. First group is sham-exposed group. The same procedure was applied to the sham-exposed group, except that the generator was turned off. And group 2 and group 3, which were exposed to 2.1 GHz, different doses of RF-EMR for 2-hour day for 1 week. And this is the RF-EMR exposure figure. RF generator, which produced the 2.1 GHz RF radiation, is used during the study. And during the exposure, rats were placed in a plexiglass tubes, and each rat was restrained in a radially positioned tube with their snouts that were located at 2 different distances, 8 centimeter and 4 centimeter respectively. And the coaxial cable has been used to provide a connection between the RF generator and the antenna, and electric field strengths measured in the signal conditions have been recorded as 45 volt per meter and 65 volt per meter for D1 and D2 distance respectively. And then we carried out dosimetry simulations using the FIT-based simulations program called CST Microwave Studio. And for the molecular aspects, we use quantitative real-time PCR technique to use the mRNA to determine the actually mRNA expression levels of these genes. And for the determination of the protein expression, we use the Western blotting technique. And for the statistics, we use SPSS software package program. And when we come to the results, first results was from the SAR measurements. So in the present study, the rat model used in the simulations has consisted of the voxels. The voxels, we can define voxel as the smallest unit of the 3-dimensional objects. And in this way, the interaction between the incident electromagnetic wave and the biological tissue can be explained. And this figure represents the whole body average induced SAR values for 10 gram average tissue at 2.1 GHz, where the distance is 4 centimeter and 8 centimeter respectively. And the maximum exposures have been observed at the closest point of the model to the antenna and the head region of the body. And the simulated average whole body SAR values for 45 and 65 volt per meter were 0.47 and 2.17 volt per kilogram respectively. And as seen in the table 1, as the electrical field strengths increase, the simulated SAR values for 10 gram average tissue also increase. When we come to the object location results, as you see from figure, the exploration time of the relocated objects and the total number of touches to the relocated object is significantly lower in 65 volt per meter groups as compared to other groups. When we come to the Y-maze results, the collected data showed both total exploration time and the total frequency of entries to the novel arm were significantly lower in 65 volt per meter group than compared to sham and 45 volt per meter group. So what can be the reason for these results? we thought that the reason why 2.0 GHz 65 volt per meter RFEMR group RATS performances in both YMAS and the object location task is worse than the other experimental groups, maybe due to the stronger effect of the 65 volt per meter dose of 2.1 GHz RFEMR, where the RATS units were located at the nearest distance, here in 4 centimeter from the monopole antenna. So when we look at the mRNA exploration, again, the mRNA levels of all these genes, acetylcholinesterase, cholinesterase, and the vesicular acetylcholine transporter, is significantly lower in 65 volt per meter groups. And also for the Western blot experiments, when we look at the protein expressions of those proteins, we again find that this protein expression is significantly lower in 65 volt per meter group compared to the other groups. So when we come to the conclusion, as you see from all these results, the stronger effect of 65 volt per meter dose of 2.1 GHz RFEMR, where the units were located at the 4 centimeter away from the antenna, has been observed on both RAS behavior and hippocampal levels of main cholinergic biomarkers. And again, the simulated SAR values were found higher at 65 volt per meter electric field strength, where both behavioral and molecular effects were observed more. And for the first time, we report here there can be a dose-dependent effects of short-term exposure to 2.1 GHz RFEMR on both RATS behavior and the levels of main cholinergic biomarkers in male visceral rats. But to understand the mechanisms by which RFEMR from cellular phones influence the functions of the central cholinergic system and other main systems in the brain, functions in the mammalian brain, further researches are needed to get the solid conclusions. So those are the publications from this topic. And this is my project team. We have interdisciplinary research from different departments, Faculty of Medicine, Faculty of Engineering, and Faculty of Science. And this work was supported by the Scientific Research Project Coordination Unit of Akdeniz University, Turkey. Thank you for your listening. If you have any question, I will be happy to answer.
Thank you very much. Any questions from the floor? I see no question. I have one question. How about the conclusion of your research? Medical people think that your research, from your research results, this is harmful to the human being body?
For the disease researchers?
Yes.
Actually, for example, we have ongoing research related to Alzheimer's disease and Parkinson's disease, and now we are trying to find the possible effects of pulse electromagnetic fields different from the RFEMR, and this is ongoing study. It's still continue, but it can help. For example, pulse electromagnetic field helps the cancer treatment, especially for brain cancer. But we haven't got any study for RFEMR exposure for the disease, especially.
Okay, thank you. Any other questions? I see no question. Okay, thank you very much. We have a nice talk.
You're welcome. Thank you.
Okay, next talk from Maria Meireles is cancelled, and the next talk is made by Ovi Kasvian, Kiev, Ukraine. The title of the talk is Michelson-Morley Experiment.
Good afternoon, colleagues. Can you hear me?
Yes, could you prepare your presentation?
So I will share my screen. Share screen.
Okay,
I
please
switch
go
off
ahead.
Camera. Oh, it's okay. So, good afternoon, colleagues. My name is Oleg Kasyan. I'm from Ukraine, and I would like to present you the new interpretation of the zero result of the Michelson-Morley experiment. This experiment is rather interesting because it's like a background of the relativistic theory. And in 1900, Lord Kelvin said that physics as a scientist probably is finished, as a science probably is finished. And there is just a small cloud at the horizon, and it was the zero result of this experiment, Michelson-Morley experiment. 5 years later, the relativistic theory appeared, and now we have another physics with another clouds at the horizon, I think. Michelson and Morley experiment is widely known physical experiment which was realized in 1887 by two scientists, Michelson and Morley. It was optical experiment, and actually it was called to show the influence of the universe ether for the optical processes what was up to date for that time. It was unexpected for the scientists, but Michelson and Morley obtained the zero result, and it's not a secret that it was the beginning of the relativistic epoch. The picture of some next slides are demonstrative and were taken from the opened sources. So the idea of experiment seems to be very easy. Interferometer consists of the source of the light, left one, semi-transparent mirror or splitter in the center, MS, two usual mirrors, M1 and M2, and detector. The beam of coherent light from the source is divided into two beams by the splitter in the center, and these beams go to the mirror 1 and mirror 2 and back by the different ways. After, they collect together in the center MS and go to the detector for the interference picture observation. Actually, everything wasn't so easy. The real interferometer in the 1887 was made of stone, was very heavy, and was swimming into the pool of the liquid mercury to avoid any vibration. Additionally, some other methods were used to avoid any external influences. As we can see at the current slide, the scheme of the interferometer was a little bit more difficult. To obtain longer arms of the interferometer, it's a distance of the beam, Michelson and Morley used some additional mirrors. We can see some mirrors at every corner of the desk. It led them to obtain the real length of arms about 12 meters, while the size of the stone was about 2 meters. So the approximate view of every beam spreading was at least shown at the left picture, and the final picture of the interference was obtained. So the interferometer was calibrated. Additionally, we will have a look at the current scheme of the experiment. In this theoretical case, we have the laser source of the light splitter in the center, two mirrors, 1 and 2, and at exactly the same distances, L1 and L2, and the detector with the interference picture. Now, we can see that the different distance of prolongation of the waves L1 and L2 must give the changes at the detector. And in the dynamical case, for example, if we rotate this big table, the red and white lines picture should give us something like a movie. Change white, white, red, or black, white. It's not difficult to show that due to the scheme, the dynamical length of the vertical and horizontal arms of the interferometer seem to be prolonged due to the appropriate coefficients rounded in red. The coefficient of longitudinal prolongation is bigger, the first degree, and the coefficient of the transverse prolongation is smaller under the root. it's clear that the different prolongations of the ways of the light spreading OMO and ONO, from here OMO vertical or OMO horizontal arm, into OM prime O prime and ON prime O prime should give us the shift of the interference picture lines in the if the interferometer turned. But as it is known, no shift of the lines were fixed in 1887. And probably it was problem with accuracy. No, later this experiment was repeated for plenty times up to date and with very high accuracy, but the result was the same. Hitherto, 4 ideas of this result explanation are known. 2 of them, which are not actual present day, are dealt with full or partial ether K, what was up to date for that time. The modern explanation uses, of course, the relativistic formulas. But actually, one more very interesting idea was proposed by Fitzgerald and Lawrence. It's the longitudinal contraction of the moving object. Mathematically, this idea is very similar to the modern relativistic explanation, but dealt with the influence of the universe, ether, and also not actual now. Of course, it's not a surprise that both ideas have similar mathematical formulas. As far as appropriate coefficients of the light spreading distance prolongation should be compensated anyway in that or another theory, they should be compensated. More than 100 years ago, the Lawrence-Fitzgerald idea seemed to be very perspective, but it had one problem. It seems that this approach doesn't have any physical sense, and scientific believed that it was just a mathematical trick or the ad hoc idea. Actually, the Einstein theory contains some manipulations with the space and time, also seems to be artificial. But anyway, at least one of these theories had to win, and we know that it was relativistic theory. The most intriguing moment of the current article is the possibility to explain the real physical contraction of the moving material object in the frame of the classical physics without any ethers or something like this. And the Michelson-Morley experiment mathematical formulas take the central place in this explanation. To explain the idea of the real contraction of the moving objects, the nature of the mass should be imaginated at first. So the method looks like the matrix of the nodal points, atoms or molecules, which are packed in accordance to the nature of the defined substance. These points are not connected mechanically in the volume of the matrix, but some forces do not let them to get disconnected or shrink. There are only 2 axioms which are necessary at the beginning for explaining of the mass existence. First, 2 nodal points are able to exist at the defined distance without any mechanical interaction only in the case if 2 or more oppositely orientated forces are compensated. Second, corresponding to all modern theories, any force has defined and limited velocity c, speed of light. The fact of the mass existence shows that starting from the distance L more than xe, the pulling force F2 prime is higher than pushing force F1 prime because mass exists. And 2 nodal points tend to bundle together. But in the point of equilibrium E, L is xe, F is fe, these 2 forces compensate each other, the moving process stops, and it's the conditions of the mass existence. Actually, we don't discuss now the nature of these forces, it doesn't matter. Now, the mathematical transformations of the Michelson-Morley experiment should be reminded. They show that the increasing of the length between nodal points, atoms or molecules, can be mechanical the real ABA or ACA distance increasing while V is 0, and dynamical, the transformations of ABA and ACA distances into the AB prime A prime and AC prime A prime accordingly, while V is more than 0. But both of them methods finally lead to the same result, the increasing of the distance of the electromagnetic interaction. So if the distance of interaction ACA or ABA between 2 points is increased mechanically while V is 0, the conditions of the system will be shifted and the system will tend to reach the equilibrium condition again. In this case, the equilibrium will be reached at the same distance ACA, and we will have the same size ACA. AC and ACA forward and backward. But if the distance of the interaction is increased dynamically from ACA to AC prime A prime, the equilibrium will be shifted without any mechanical increasing of the distance ACA, the size. But anyway, the system will tend to reach the point of equilibrium. So the real distance, real size ACA and ABA will be decreased automatically for the same coefficient. As it was noted above, the mathematical transformations used in description of the Michelson-Morley experiment explain the zero result of the experiment without any additional theories or ad hoc ideas. As it is seen, the moving of the mass of the interferometer gives the dynamical prolongation of the interaction distance between the nodal points of the mass. But the equilibrium of the system is possible just at the distance of the interaction ABA and ACA, but not at the mechanical distance ABA and ACA. In this case, the process of the mass formation will stop at the distance less than ABA or ACA. It will be equilibrium, new equilibrium, and the real mechanical size of the object becomes smaller for the appropriate coefficient with root and without root. As far as to stay in the point of equilibrium, the distance of interaction in the system AB prime A prime and AC prime A prime must be constant. In another way, we will not have equilibrium. It means that the real mechanical distance between atoms in the moving interferometer are smaller, but taking into account the dynamical prolongation of the distance of the light spreading, the permanent value of the distance will be obtained. The data given above shows that the paradox of the dynamical science contraction can be explained easily explained exclusively from the point of view of the classical physics. In the contrast to the Lorentz Fitzgerald idea, the contraction, of course, will behave both towards the longitudinal and transverse sizes, but for the appropriate coefficient and without any ether influence. The current idea shows that the distance of the interaction in the processes similar to Michelson-Morley experiment will be always permanent as far as the corresponding coefficient of the size contraction and the dynamical light spreading distance prolongation will always compensate each other. In the other word, it means that if the interaction between two nodal points, atom or molecules, related with the velocity of the electromagnetic interaction c, the distance between these 2 points measured using optical method like the Michelson-Morley experiment will be always permanent, and the shift of the interference lines will be never fixed. That is what we can see during last 130 already years, that there is no shift of interference picture is observed. Thank you for attention. That's all.
Okay, thank you very much.
Maybe you have a question.
Any questions or comments? No questions or comments?
Thank you very much for attention.
Okay, I See no questions. Thank you very much for your nice talk. Okay, we are a little bit ahead of the schedule, but the next section will start at 2:20 p.m. So we will have a short break and we will restart at 2:20. Thank you very much. Hello. We will restart the session from now on. The next talk is made by Mazhar Hossain from Karnataka University, Dharwad, India. The title of the talk is Photoelectric Effect. So could you go ahead, please? Could you share your presentation now? We can't see your presentation. Also, your voice is muted, so could you hear me? Could you hear me? Mr. Hussein? How can we proceed, David? Oh. Can you hear me? Okay, I can see your presentation.
So, hello, my name is
Yeah, okay,
Mazhar
go,
Hussain.
go to presentation mode, please. Can you switch to the presentation mode?
So, hello, my name is Mazhar Hussain. That when a light of suitable frequency falls on a metal surface, it will eject the electron from the metal surface. Phenomena was given by the Heinrich Hertz and of his first. When this light particles falls on the metal surface, they will eject the electron from the metal surface.
Excuse me for saying that. We can see your presentation now. Network connection is unstable, I think. Could you share your presentation now?
So this phenomena is, oh my God. So Einstein basically used Planck's quantum theory. So this is the basic idea of photoelectric effect. See, when light rays falls on the metal surface, this light rays eject the electrons from the metal surface. This is the phenomenon of photoelectric effect. So according to Einstein, light is made up of discrete units of elementary particles called photons. When these photons falls on the metal surface, they eject the electron from the metal surface. Einstein's equation of photoelectric effect is given by this equation. H nu is the Planck's quantum equation. Phi naught is the work function. After liberating from the metal surface, the electron will eject out with the maximum kinetic energy. If we rearrange this equation, the equation becomes H nu minus H nu naught is equal to half MEB whole square. I will just tell you is that just notice at that equation half MEB whole square which Einstein has written. Energy of the photon absorbed by is used in liberating the electron to just eject out from the metal surface, called work function. After liberating from the metal surface, the electron will use with the maximum kinetic energy. Now here the game changes. Can we explain the photoelectric effect by using the law of conservation of momentum? Please notice, according to me, my theory, light is made up of this photon. The momentum of the each single is absorbed by a
Mr. Hussein, I can't hear your voice now. Everybody just wait for a moment.
h nu by c minus h nu naught by c is equal to MEBE. We will get comparing the Einstein's equation of photoelectric effect in terms of law of conservation of momentum, V by C minus h nu naught by C is equal to half MEB whole by C. And the new equation of the photoelectric effect the right hand side is given by MEBE. Comparing these two equations, new equation of the photoelectric effect, we will get half MEBE whole square by C is equal to MEBE. The equation becomes like this.
I think Mr. Hassan's network connection is very unstable. So if he come back again, we will restart his presentation. So okay. Next, next available speaker is Swagata Samanta. Just a moment. Okay, we'll proceed to the next available speakers. So, Swagata Samanta from the SRM University, AP India. Are you ready to present?
Yeah, yes.
Okay, so please prepare the presentation.
Yeah,
The
I'm sharing the
the-
screen. I'm sharing the screen.
The title of the talk is SU8 Polymer Waveguides for Photonic Integrated Circuit Applications. So please share your slides. So go to presentation mode and could you start now?
Yes, just a second. Yeah. Is my screen visible?
Yes, okay.
Okay.
Please go ahead.
Okay. So, greetings everyone. Today I'm going to talk on SU8 polymer waveguides for photonic integrated circuit applications. So, what is this SU8 and why we are using it? So, SU8 is basically a low cost epoxy based negative resist. Okay. So it has a high refractive index contrast and is optically transparent both in the visible region as well as the telecommunication wavelength of 1.3 to 1.6 micron. So it can be used for waveguide and microstructure fabrication. The fabrication process is also easy. That means what? It is simpler. The fabrication process is very simple. So in case of on-chip optical interconnects, the use of this AC weight is more useful than silicon. Because what happens is that the refractive index of AC weight is less than that of the silicon. That's why what happens is that there will be faster distribution of optical signals at different nodes of chip. Okay, so as we know that in every photonic integrated circuit, the optical waveguide is the main building block. So first of all, we have designed and analyzed the single mode waveguide, AC weight waveguide. Okay, so this is the schematic of the AC weight waveguide. Here, this T is the oxide thickness, H and W are the thickness and width of the wire, that is the core, and this N1, NB, and NC are the diffractive indices of this core, oxide, and clad, respectively. Now, here this Y is the direction of propagation, Z is the depth direction, and X is the lateral direction. Now, the analysis of this waveguide is accomplished by using effective index plus matrix method. Now, this is a two-step method. In the first step, what we are doing, we are using effective index method for the vertical refractive index profile, that is around the Z direction. And then in the second step, we are using transfer matrix method. Okay, the resulted lateral index profile, what we are getting from this EIF, we will apply TMM on that. That means transfer matrix method. Now, first of all, what we will do, we will apply boundary conditions at each interface in the depth direction. That means across this Z direction. Then we will get the modal dispersion equation. Now, if we solve this dispersion equation numerically, we will get different thicknesses and effective refractive indices. Now, this is the plot for these thicknesses of AC weight wire and this effective refractive indices. So we have plotted for both this TE and TM mode. Now, from this, you can see that the waveguide operates in single mode operation within this 0.43 to 1.72 micron. That means within this region. Okay, this is for TE mode, and for TM mode, this 0.564 to 1.853. Now, we have also validated our results using EINN by using the commercially available FDTD software. Okay, and we can see that the results match very well. And this M here stands for the mode, that is M0, M1, M2, M3. We have considered first four modes, that is for the fundamental mode, and first harmonic, second harmonic, and third harmonic. And we have chosen the thickness to be 1.35. Now, next, as I have already told, this transfer matrix method. So that we have applied to determine the propagation characteristics of the guided mode. Now, here what happens, in this process, what happens, we have added a hypothetical layer. Okay, what we consider a hypothetical layer or the added layer, whatever you can say. So whose refractive index is at least the maximum refractive index of this guiding layer. Now, we are considering incidence of plane wave on this structure at different angles of incidence. Now, if the angle of incidence exceeds the critical angle, then what happens is that a leaky guided mode can be excited in this guiding layer. So, provided that the distance between this added layer and this guiding layer is not too small. Now, here what happens, we will get Lorentzian shaped resonant peaks at certain values of propagation constant. Now, the values at which we get the propagation constant is the real one. While the FWHM, that means the full width of maxima, will give the imaginary one. Okay, so this is the computed propagation constants for different widths of the AC weight waveguide. We have used by effective index matrix method, and also we have compared our results with FDTD for both TE and TM mode. This is for TE mode and this is for TM mode. Now, from here we can see that the AC weight waveguide that operates in single mode within this 0.06 to 0.67 micron for the TE mode, and for TM mode it's 0.08 to 0.73 micron. Now, our chosen width, sorry, this will be width. So our chosen width will be 0.6 micron. Next, we move on to the fabrication. So design has been done with our design parameters. We have moved for the fabrication. First of all, we had fabricated by using this direct laser writing technique. So these are the fabrication steps. And we have analyzed the sample by using both optical microscope and scanning electron microscope. This is the optical microscopic view of the waveguide edge, and this is the SEM view. So we have got this waveguide thickness to be 1.35 micron and width 5.3 micron. So we can see that the waveguide supports single mode operation in the vertical direction, as we can see from our design value. We can compare it and we can see it. So next is, this is the setup for the waveguide output recording. A semiconductor laser source of emitting 1.55 micron wavelength is coupled to this waveguide through single mode optical fiber, and through this high precision 5-axis micropositioner. Okay, and the output is recorded by using this IR camera and 20x objective. We can see that in the monitor. This is the mode image of the cladded AC waveguide. Now, if we change the position of this waveguide, that means like this, we can change this inclination and the position. So after that, we can find that this mode image, that see here there are a number of modes, right? It's not single mode. Okay, so after changing this inclination and position, then we are able to reduce this mode image. So here you can see it. Okay. And if we change the clad, this we have used for clad as air, but if we change the clad as PDMS, then we will get this single mode waveguide. You can see here, it's the single mode waveguide. Only the fundamental mode is given. And we have compared our fabricated results with the designed one. So this is our designed one. This is for when we have taken clad as air, and this when we have taken clad as PDMS. We can see that the results match very well. Okay. Next is the loss measurement. We have used this setup, this lock-in amplifier, chopper, and detector. This arrangement we have taken for this loss measurement, that is the total insertion loss measurement. So here we have what we need is that we have put this wafer or the device under test, whatever you can say. So then we measured our output, and also we removed this wafer and we again measured it. That means the fiber output we have measured. Then we can calculate the loss by using this formula, where PO and PI are this waveguide output and fiber output. Okay, and this is the graph for total loss for varying waveguide length. So here we have best fitted it with a linear fit equation with equation y equal to mx plus c. Here this c, that is the constant, is the coupling loss, and this slope, that is the propagation loss, and the total loss, that is this y, is the insertion loss. Okay, so for clad as air, we got the propagation loss to be 0.51 dB per millimeter, and for clad as PDMS, it's 0.3 dB per millimeter. Now, the coupling loss is 2.18 dB for clad as air and 4.11 dB for clad as PDMS. Now we know that age preparation is very important. Like, so that's why we have polished it. So we have taken a waveguide of 13.5 millimeter and we have undergone polishing. So we got that this coupling loss, we have seen that the coupling loss is reduced to 2.23 dB after polishing. So you can see here, this is the total insertion loss. Before polishing, it was 8.23 dB, and after polishing, it became 6.28 dB. That means the total coupling loss, it reduced to 2.22 dB after polishing. Next, we have also fabricated the AC waveguides by optical lithography using chrome mask. This is the fabrication step. This is the SEM view of the AC waveguide edge. This is the top view, and this is the tilted view at 20 degree. So we find that the waveguide width is 3.5 micron and the waveguide thickness is 2 micron. This is the mode image. You can see that it's a single mode AC waveguide. The propagation loss here we find for TE mode it's 0.84 dB per millimeter, and for TF mode is 0.77 dB per millimeter. So after that, what we did, so we have our the fabricated AC waveguide ready. So by using that, we have developed some of the on-chip photonic devices. So here I am going to discuss with you some of them. So I will discuss with you the optical coupler, microring resonator, and if time permits, I will show you this photonic crystal structure on waveguide. So this optical coupler design. So we have considered three structures. Like we have first considered this 2 straight waveguides, as you can see here, 2 straight waveguides, and then we have taken 1 straight one waveguide, and then we have taken 2 curve waveguides, directional coupler. Okay. So basically, why we are using this one is that in order to couple light in, suppose in microring resonator, or if we want to fabricate any directional coupler which is based on low crosstalk optical switches. So for those things, we can use this optical couplers. So now to analyze actually these two are differential equations for codirectional coupling between the waveguides. Now in order to analyze the coupling between the curved waveguides, we have converted these two equations to a single nonlinear Descartes equation. So, and as we know that critical coupling length is a very important parameter in case of this optical couplers and all. So, first of all, what we did is that we found out this critical coupling length by using the matrix method. Okay, so first of all, we are considering the 2 straight waveguides. Okay, so here you can see this is the 2 straight waveguides, and there is a distance that is, you can say, separation or gap. Okay, that is G gap. So here we have shown you this propagation constant versus the excitation efficiency for 2 straight waveguides. Here the separation, that means this gap is 0.4 micron, and this is for 0.6 micron. This is 5 micron, 0.4 micron separation, and this is 0.5 micron separation. Both we have taken for TE mode, and we have also calculated for TM mode, but here we have just shown it for TE mode. Now, from here, we got 2 resonant peaks. You can see that 2 Lorentzian shaped peaks we can see. One is for this asymmetric one, and another is for the symmetric one. Okay, now from here we can calculate this critical coupling length by using this formula, because we are having this one, this is for beta S and this is beta A. So easily we can calculate this critical coupling length. So here we have shown the graph. This is the graph for coupling length versus separation between the 2 straight waveguides for the TE mode and TM mode. Here also we have compared our results with commercially available FDTD software, and here we can see that it's the results match very well. So now what we have to consider is that what we will choose, the S0 and S1. That means what? S1 is what? This is the S1. That means the maximum distance between the waveguides. Okay, we have to choose it very wisely, because we have to choose it such that there exists no coupling between the 2 waveguides. Okay, so our chosen one is 1 micron, and chosen S0 is 0.5 micron. Okay, so G2, that is this output optical wave. So that's sine square C, and C is the total or overall coupling coefficient. So from that, we can get this one, propagation distance versus this relative optical power of this output optical wave for TE mode. And this is for 1 straight and 1 curved waveguides, and this is for 2 curved straight waveguides. We can see that 100% power transfer occurs when we are taking this radius of 56 micron for this 1 straight and 1 curved waveguides, and when we are taking 2 curved straight waveguides, then that is a radius will be 115 micron. Now we have fabricated it by using chrome mask and by using this optical lithography. So this is the mask and sample preparation. This is the SEM view of the coupled region of the 2 straight waveguide directional coupler. So here, as we have discussed before, this waveguide width is 3.5 micron and waveguide thickness is 2 micron. And this gap here, you can see this gap here is the 0.6 micron. Now, this is the setup for coupling length measurement. Now, here what we did is that we have taken a straight waveguide as the reference one. Okay, and we considered that these optical loss of the straight waveguide and this directional coupler will be same, because we are using the same wafer and in the same run. We have fabricated it in the same run. That's why we have considered that one. So, however, what happens is that there might be like 100% power transfer may not occur. So that power will be here. So for this reason, what will happen? Some excess loss will be present. So we can calculate this excess loss by using this formula. Okay, and as we know this kappa, that is this we know by using this pi by 2 LC, where LC we have already told is the critical coupling length. By using this one, we can easily calculate this excess loss, because it's PO by PI will equal to sin squared kappa L. So here, after this measurement, we found that when we are taking separation as 0.6 micron, so this experimental value for both TE and TM mode are nearly equal. But when you are taking separation as 1 micron, you can see there is a difference between this experimental value and the theoretical value. So it's because of the fact that, see here, as separation increases, this coupling length increases exponentially. So this is the reason here. So next, what we did, we have developed this microring resonator. So it's another device by using this single mode AC waveguide. So this is the schematic of the microring resonator. So here, this is the input port, this is the through port, and this is the drop port, and this is the add port. Okay, so here, first of all, what we did, in order to design the microring resonator, we have to design a single mode AC waveguide. We have done that using effective index-based matrix method. Then we have to determine the coupling between this ring and this bus waveguide. Okay, so after that, we will compute this bending loss of this bent AC waveguides. We did that by using a conformal mapping technique along with the transfer matrix method. So with this, these are our input parameters. So with this input parameters, we found this is the transmission characteristics, what we obtained with this input parameters. So we can see that a deep notch is there in this through port. It's minus 87.98 dB. The free spectral range is 16.79 nanometer. Q factor is 30,312, and the extinction ratio is 13.745 dB. We have also studied the temperature sensitivity of this microring resonator. This is the transmission characteristics due to the change in temperature. So from here we can see that, see here, more this temperature deviates from room temperature, that is 0 Kelvin. So more this spectrum shifts towards left. Okay, that means blue shift is occurring. Okay, now this is obvious because of this negative thermo-optic coefficient of the SU8 polymer. Okay, now here you can see with change in temperature, there is a change in refractive index. Okay, and thus there is a change, and thus, sorry. Okay. So here you can see that with this change in temperature, there is a change in refractive index. Okay, so this can be used as a temperature sensor also. Okay, so automatically what will happen? This wavelength will also change. So we can use it as a refractive index sensor or a temperature sensor. Okay, so again, this is the fabricated result. This is the microring resonator, and this is this we have shown this bending portion we have shown. The width is here 3.5 micron. This gap here, it's 0.5 micron, and the radius is 15 micron. And okay, so this is the setup for through port and drop port response, and this is for through port what we have obtained, and this is the drop port response. Okay, so this we obtained by using this setup. So both each of this through port and drop port, we have scanned it by using a monochromator and this detector, and lock-in amplifier chopper is used in order to improve the signal to noise ratio of this measured data. Okay, and this is the through port response of this fabricated resonator. This is for TM mode and this is for TE mode. This is the normalized one. From here we can see that for TM mode, the free spectral range, that means the this one, okay, distance between the adjacent resonant peaks, that is 19.24 nanometer, while our designed one was 16.34 nanometer. For TE mode, the fabricated value of this FSR is 16 nanometer, while the design value is 16.76 nanometer. The extinction ratio is 10.5 dB, and for the designed one, fabricated one, and the designed one is 13.75 dB. And Q factor, what we obtained is a bit is very less as compared to the design value. It is because of the fact that this straight whatever waveguides we have used is not strictly single mode, and we have used this monochromator, which is having bandwidth that band pass what we are having or resolution that is only 0.6 micron. That's why. So here this microring resonator, this can be used as an optical band pass filter around this 1563 nanometer transmitting wavelength. So I will also show how we have developed this photonic crystal structure on SU8 wire waveguide. So here, first of all, what we did, we have fabricated this SU8 wire waveguide, first of all, using optical lithography by chrome mask, using that chrome mask. And then we have used focused and beam lithography in order to make this photonic crystal. So these are the fabrication steps. And these are the fabrication parameters, what we have used, beam spot size, medium depth, hole diameter, periodicity, all these things. So this is the fabricated photonic crystal on this wire waveguide. So roughness we obtained is 33.1 nanometer as we got from this AFM measurement. And so here we find that there are two band gaps here, band stop regions. So in spite of this polarization, okay, so we can use it as a polarization independent band stop region also. So, and if we can use it in between 0.703 micron to 1.692 micron, so it can be used as a band pass filter, and that's polarization independent. So these are my collaborators and my supervisors, my colleagues and all, which with whom I am working. So I want to acknowledge them. So thank you.
Thank you very much for your presentation. Any questions or comments for the floor? No questions? I have one question.
Yes, yes.
Your waveguide have some degree of polarization sensitivity.
Yes.
Polarization dependent loss?
That with optical loss you are saying?
Yeah.
Yes. See, for just a second. See, total loss will be coupling loss as well as the propagation loss. Okay. So this coupling loss, that will be constant. Okay. If you are taking a particular wavelength and a particular suppose a waveguide is there of here we have taken 13.5 millimeter. So if we fix that waveguide length, so propagation loss will be fixed. So what we can change is that coupling loss we can change. So that's why we did the polishing and we reduce this coupling loss. So without coupling loss, it was like 8.23 dB, this total insertion loss. And after polishing, we got it 6.28 dB, the total insertion loss. So that means, as I have already told, the propagation loss is already, constant for a fixed waveguide length. So that means what the coupling loss is reduced. So
I mean, polarization dependent loss, loss difference between TE and TM modes.
Yes. There will be a difference, but here what we did that we have taken like whatever parameters we have taken. No, we have first of all we have taken that polarization independent. We have made it. So for different one, we have taken a polarizer. Okay, Glan-Thomson polarizer. So we have find out this insertion loss for TE mode. Then again for that TM mode. So nearly for TE mode, it's less. Well,
near equal. Yes. Oh, okay, thank you.
Yes, it's less. Okay. For TE mode.
Other questions? Nothing. Okay, thank you very much for a great talk.
Okay, thank you.
So next speaker is Respek Usmanmatov from Kyrgyz State Technical University after Radsatkov, Kyrgyzstan. Mr. Subhamatov, could you prepare your presentation? Mr. Subhamatov, can you hear me?
Good. Okay. Mr. David. Okay, I start. Okay. Meeting chair. But I cannot withdraw my slides. Where is it? Can I do it? I cannot. Do it. No. Leave code. I cannot start. Direct message.
You need time. Do you need the time to prepare your presentation?
No, I cannot withdraw my slides from my from screen. I don't know how to do it. I have on a black screen and do you listen me, Mr. David? Mr. David. Mr. David. Me. How can I don't know. Context. Unbelievable. No, I cannot communicate with you.
Yeah, hello, Rajbek. Yeah, can you hear me?
I cannot withdraw my slides from.
Yeah, can you please click on the bottom? There is a share screen option. Can you please see that at the bottom?
Which icon?
Yes, in Zoom meeting only. At the bottom middle. At the bottom middle, there is a share screen option. Can you please click on that and share your screen?
I'll see. I don't have such a
Yeah.
mute. Stop video. Which icon I should click?
Are you
screen share?
Yes.
Yes, I've screen share, contact, that's it. No.
Yes, if you click on share screen, then you can share your screen to us. Please click on that.
Share, optimize, share sounds. It's this one. No, it's not mine.
Yes, it's
Wait.
visible to us now.
It's yours. Choose from a list of type filter. No, it's not this one. Is this my general information?
Yes, it's visible to us. Can you please open your PPT?
Which should open?
Your screen is visible to us. Can you please open your presentation and continue with your presentation? And please give your talk.
Oh, well, okay. Okay, do you see my slides?
Yes.
Okay, I will start. Sorry, ladies and gentlemen,
Okay,
no,
can you
no,
please
no.
open your presentation?
Yeah, your
Yeah.
presentation
My
is
presentation,
you
my
can
presentation,
share. You can share your
theory of,
presentation. We can't see.
yes, I see.
We can't see your presentation.
You see?
Oh, no,
No?
no.
I see
Please-
my presentation.
Please share your PowerPoint file.
Okay, wait. Which icon I should click?
Could you retry?
Screen sharing, no. Yes, I can. You ask screen sharing or what? Which icon I should?
Yeah,
You
different
share,
screens
maybe.
shared. Different screens shared now. So please share your PowerPoint.
Oh, wait. I don't see. Share. Do you see my slides?
Okay. So go to
Okay.
presentation mode. Yes.
Do you see my slides?
Yeah. Okay.
Okay. Let's see. Sorry for my inconvenience. So my presentation, theory of gyroscopic system for rotating object. Just short introduction. Simplest gyroscope, because I see our conference mixed psychologists, biologists, chemists, and other physicists. So it is this topic is for engineers and physicists. Oh, sorry, for physicists. I derived gyroscope theory that researchers of entire world could derive during 300 years. It is funny to say, but it's reality. Simplest gyroscope is a top toy. You see this top toy. Researchers of time beginning from the industrial revolutions tried to solve gyroscopic effect. Rotating top toy demonstrates some unusual behavior, unusual motions, and unusual action of the forces or torques. And only one mathematician, Leonard Euler, described one gyroscopic effect that called the change in angular momentum, this precession torque. But his solutions is not serious. The weight of his solution is around less than 10% from entire total force and torques acting on spinning object, or less than 10%. It's very important. I show you. I will omit some slides. No need. No, wait. I should demonstrate. Go this way. This one. So my solutions. When I was students, I have seen the lectures did know solutions of for the gyroscope. When I was student, it was 6 years ago. And from those time, my background is manufacturing engineering, but I'm not physicist. And occasionally around 6 or 7 years ago, my dean, I worked in overseas universities, proposed me to teach course machine dynamics. And I remember that machine dynamics has chapter gyroscope. And I looked through all publications and see no motion, no progress over the 60 years from when I was students, and solved the gyroscope theory during a couple of weeks. I was disappointed by all scientists, entire world, that they couldn't solve this very simple problem, gyroscope theory. Look, I demonstrated that any kind of object, what's the rotating disk, spinning disk, if you apply torque, this rotating disk or spinning disk will produce not one inertial torques with changing momentum, but 8 inertial torques acting around 2 axes, and all of them produced by the distributed masses. So this sketch solutions of Leonard Euler, the change angular momentum of his equation or this formula or expressions, torque of angular momentum, product of mass moment inertia. Omega is angular velocity of disk, and omega x angular velocity of rotation of the disk around axis or x. These Euler solutions forces or torques derived by the rotating masses give several new torques. First of all, centrifugal forces. Rotating mass element generates centrifugal force, which component, axial component, after integration, gives inertial torques acting around axis of x. This equation, this formula, this expression, same as a change angular momentum, but except this digit coefficient, which express geometry of the disk. Rotating object can be different shapes, different geometry, and sphere, for example, sphere, they have different digit number, but this is only for the flat disk, spinning disk. This rotating mass, element mass, generate inertial force acting around axis of x and around axis of y, same value. You will integrate this component and you will get this. I will show you this. This inertial torques acting around axis of y. This is precession torque, the general precession torque. This same for expressions. After that, except this Coriolis force, there is a centrifugal Coriolis force. Coriolis force around x or x. These expressions is totally, I show you. You see, around each axis act 4 torques, 2 torques, centrifugal forces, 1 resistance, 1 precession, Coriolis force, and Euler torque, change angular momentum is around at 9.3%. Nothing. Other torques were unknown for the researchers. Unknown. So after this, it is no problem. Now I can show action of all torques. That shows you this low torque, this arrow, generate 2 resistance torques, centrifugal force, Coriolis forces. At the time, this torque generate precession torque acting around x or y. This is a centrifugal force and change angular momentum. These acting torques at the same time generate resistance torques acting around axis or y and axis or x. Around each axis works 8 inertial torques to get, 4 torques. Around 2 axes, 8 inertial torques, not 1. 8 inertial torques. You see, 8 inertial torques. This is discovery. Okay. I will miss this expressions. I'll give the other one. It's not so interesting. It's a pure geometry. This one, except action of inertial forces. Inertial forces on gyroscope express principle of energy, mechanical energy conservation, mechanical energy conservation. I'll prove that around each axis, kinetic energy of acting torques, they are equal. They are equal because all torques interrelated by one loop system of inertial torques with background, or as well with feedback. With feedback, I show you. And dependency of angular velocity of the action inertial torques expressed by these expressions around angular symmetry x and around element or y. Okay, I tested these expressions, and you will see. I'll back. Sorry. It's very interesting. This one. I will back. You see, a ratio of these 2 velocities is around angular velocity around x or y, around 100 times more than angular velocity omega x. And it was tested on laboratory gyroscope. So around axis, if we turn outer gimbal on small angle. It's around less than 1 degree, less than 1 degree, 1 degree. So inner gimbal turn on 90 degrees immediately. It was unknown. It was known, but researchers couldn't explain why there's some such result. I demonstrated everything correct. Okay. Other one. So I told you that previous expressions were for the disk, but for the spinning sphere, there's another expressions, because engineering, there's a lot of some designs, rotating design, different geometry, conical object, another forces, another torques expressions mean. I'll show the other one as a ratio. This one expressions of the centrifugal torque, expression Coriolis torque, for the propeller different torque. So all of them acting on rotating object, but engineers and physicists, they don't use these forces, and they design airplanes, propeller, ships propeller. They don't use action of this inertial torque, but just now they can use and compute exactly a more reliable components, reliable results. I'll show you. Wait, I will miss this one. Except this one, just still now, a lot of researchers, they demonstrate, like Khotaransky professor from University of Australia, also in past centuries, Lightweight professor from London, he stated that gyroscope possesses anti-gravity effect. It's also wrong. It's because they didn't know action of the forces. I show you. You see this? A little bit later. All active forces. I proved that all active forces and derived earlier equation for the rotation of the spinning disk with offset, one side support or flexible chord. All acting forces that I derived, they were used for this equation, and this example, all geometries also, and result exactly matched with the mathematical model. Exactly this result. That it's a technical data of the stand. I show you. I show result. This one. You see different results. Test rotation around X or Y around 8 seconds. Theory around 8.5. Differences less than 4%. Less than 4%. It's a perfect matching. So everything correct. Other one. Other one. This is new. It is new. Inertial torques acting on spin on gyroscope with one side support. If researchers will block motion around X or Y or precession torque, so all inertial forces deactivated. All inertial forces except the change in angular momentum. Running gyroscope with the rotating masses with the acceleration, they don't produce force. You see, Newton's second law is not full. Practice demonstrates the masses is acceleration, but no force. It was published in some paper and journal, and physicists still don't know why we have such a result. But it's a reality. Inertial forces can deactivate, and no force, no torque. There's a mass, there's acceleration, but no force. It's another innovations. I detested the testing. I tested this at my stand that no force. Okay, other one. I will. No need to, because I give some interesting. Something interesting. It's this one. This one. This deactivation. Deactivation. So Professor Khotaransky from Sydney University and Lightweight from last century, they demonstrated anti-gravity effect. This rotating disc around 25 kilogram installed on some shaft around 1.5 meter, and by hand it's impossible. But Professor Khotaransky, he rotate around himself, and this disk lift up, and he say this is anti-gravity effect. No, it's wrong. It is not anti-gravity effect. Not anti-gravity effect. I proved this. There is equation. What equation of working around X and OY? They generate precession torque, quite very strong precession torque. This precession torque lift this. This spinning disk lift up. I received message from engineers. One American designer of rocket mask, and the engineers, they wrote me that my expressions, my formula correct. They calculated, computed, and just now they don't use numerical modeling of such as anti-gravity. No anti-gravity effect, except this one. Researchers also stated that gyroscope possess so-called non-inertial property. It's also wrong. I show you. Gyroscope possess inertia. It has inertial forces, and I show. Wait. Annotation, not the other one. Wait. Oh no. They stated that gyroscope is not inertial. HTTP talked on it. This inversion also I've solved inversion. Wait, it's very interesting. Wait. Acceleration. Somewhere. There's too much in there. I have too much. Oh, somewhere. Okay, somewhere I can find. So gyroscope is an inertial system, and wrong statement that gyroscope it is not inertial system. It's wrong. The reason that angular velocity around axis rotation actual test by researchers, they demonstrated that angular velocity is constant on the action of external torque. All angular velocity around axis is constant. They measured with some high quality timers. I don't know which one, but all of them right that stated angular velocity around axis rotation is constant. It's wrong. I have formula and proof that angular velocity is variable, but the change of angular velocity around axis too small, so it's I can say less than 10, maybe 100,000 times less, and known timers cannot measure this small change of the angular velocities. My time is ended. Yes, I finished. Okay. They have questions. This is my book. I published it as a second edition past year.
Okay, thank you very much. Any question from the floor?
Can you? They have questions. Probably should have questions. You should have questions. I'm ready to answer. If you have
any questions.
No, unfortunately, no questions.
I see no questions.
I remember.
Okay.
It's finished.
Okay, thank you very much for your presentation.
Okay, thank you.
Okay, next presenter is Maya Mohammadi from Shiraz University, Iran. Could you prepare your presentation?
Yes, hello again. Let me share my screen.
The title of the talk is Bose-Bonnet Holographic Superconductors in Lower Dimensions.
You should have my screen right now. Is it okay?
Just a moment. We cannot see your presentation.
Yeah, it's loading.
Uh-huh.
It's still loading. Yeah.
Okay, we can see them.
Yeah. That's great. Hello, everyone. I want to talk about gas funnel holographic superconductor in lower dimensions. First, I want to give a very short introduction about the holographic superconductor, and after that, I will introduce the holographic superconductor in the presence of gas funnel keep a superconductor and I summarize after the discovery of superconductor voted to find out different aspects of super find different this theory, but and we face with so holographic superconductor as a theoretical way to describe high temperature superconductor grab a lot of attention. This kind of superconductor shows similar like a second order phase transition. This theory is built on ADS-CFT duality. What is this theory? ADS normal field theory in D plus one dimension on the bottom, which is dual the order parameter on the boundary. Based on this theory, in order to describe a holographic superconductor, we need a phase transition from a black hole with no hair to a hairy one for temperatures below the critical one. Just when gravity as a higher order correction in the phase transition of gravity model has been studied in D equals and higher than 5 dimensions for a long time. But during the recent years, by introducing a new form of action, it gives us the chance to study this kind of gravity. We the definition, but I don't want to talk about the mathematical relation. So with a lot of details. So if you have a question, we define the action equation 1, and we define the metric that if we can define, we have R, which has the asymptotic, which means Newton's equation. So we can define the half-Grisham theory. Now we want to talk about the holographic S-wave superconductor in Gauss-Bonnet gravity. We define the action by considering a higher order correction. Now both on the gravity side, same as the LNA electrodynamics, which has the following. And FMU. So we choose our gauge field and scalar field same as equation. Scalar field same as we turn off the gauge. The scalar field is during the action number 4 and substituting choosing of and gauge to the equation which same as equation 7. For example, the gauge T equals 3 has a logarithm behavior, but in 4 dimension, it's in order to study the equation number 6, we find the effect by increasing the nonlinearity effect or increasing which means we faulty for conductor super both in dimension 3 and 4. And we plot the behavior session based for different values of mass, nonlinearity, and Gauss-Bonnet term. Based on these parameters, by increasing the effect of mass or nonlinearity or Gauss-Bonnet, based on the effect of mass increase, which prove the previous data, the previous results for the critical temperature, which means for a stronger effect of mass, nonlinearity, and Gauss-Bonnet term, the conductor, superconductor phase transition faced with more difficulty to happen. After that, we study the conductivity. We turn on an appropriate perturbation on the black hole background, same as equation 8, and based on this, our perturbation, the X component of the our gauge field turn to the equation of number 9, which can solve and have the equation same as number 10, which means for in d equals 3, we have a logarithmic behavior, but in a 4-dimension, Ix equals R0 plus R1 divided to R. And R0 and R1 are two gauge gravity duality in holographic setup 11. So in order to find behavior of the real and imaginary part of the activity, we follow figure 11. An imaginary part of the conductivity in the 3-dimension, same as this figure, based on our choice of nonlinearity, temperature, alpha, we will face with different form of conductivity, the real and imaginary. But indeed, in D equals to 4 in 4-dimension, in this setup, when we say 4-dimension, we mean in the 3 spatial coordinate and 1 temporal coordinate. We see the figures are so reasonable that in low frequency regime, we face with the delta behavior in the real part, while the imaginary part has a when omega and for nonlinearity, mass, and temperature, figures are different from each other, but they follow some universal behavior. We know for superconductivity setup, by decreasing the temperature, we observe a gap frequency. And this gap frequency tends to higher values by increasing the effect of alpha, B, and M, which means it's difficult to detach the Cooper with result critical temperature and condensation. But now we want to talk about holographic p-wave superconductor. Holographic p-wave superconductors are known as a high-temperature superconductor. In holographic setup, in order to introduce a holographic p-wave superconductor, we present the action same as equation 12. You know that for S-wave, we have a different form, and for p-wave, we present room mu instead of psi, which represent a vector field. So we introduce our gauge and vector field same as equation 30, and by varying equation 12 based on gauge and vector field and substituting our choice of gauge and vector field based on equation 13 to the variation equation, we find the field equation for our vector field and gauge field, which have the asymptotic behavior same as equation 14. Same as S-wave case, in order to analyze our holographic system, we follow the numerical solution by applying shooting method, and in this case by increasing the temperature. by increasing the mass, the nonlinearity, and gas van der Term, we decreasing the critical temperature and increasing the condensation value, which means in holographic P-wave superconductor, same as in S-wave case, by increasing the effect of the mass nonlinearity and Gauss van der Term, we face with the superconductor phase transition difficult. And in order to study the conductivity in this kind of superconductor, we turn on appropriate perturbation, same as equation 16. And the result equation has the following form, same as equation 17, which has the form like equation 18. Same as in S-wave case, based on our holographic superconductor, holographic setup, we can find the conductivity same as equation 19. So again, we solve the equation numerically to find the real and imaginary shape of the conductivity. We see that the behavior of the real and imaginary parts in 4 dimensions in S-wave and P-wave are similar to each other, but the behavior of different part of conductivity in 3 dimensions in S-wave and P-wave are so different from each other. So same as S-wave case in lower dimension, 2 parts of conductivity in 4 dimensions connected to each other behavior via chronic relationship, and at a high frequency regime, 2 parts tends to a constant value. By decreasing the temperature, we face with appearance of a gap frequency, which leads to higher values by increasing the effect of gas van der Term, nonlinearity, and mass, which means that we have we face with difficulty to phase transition for higher effect of Gauss van der Term nonlinearity for massive scalar or vector field. So in order to summarize, I should say that in all cases, increasing mass nonlinearity and Gauss van der Term diminishes the critical temperature and increases the condensation, which means that conductor superconductor phase transition harder to form, and we present the behavior of real and imaginary parts of conductivity due to different values of mass nonlinearity and Gauss van der Term. And we see that the graphs, the real and imaginary parts of conductivity follow some universal behavior in D equals to 4 and in a S-wave and P-wave case, but in a 3 dimension, it's far different from each other. And I want to thank the Scholar Conference to give me the opportunity to take part in this conference. I thank them so much. Thank you so much for your attention.
Okay, thank you very much for your presentations. Any questions or comments? I see no questions. Okay, thank you very much for a nice talk.
Thank you so much.
Okay, we'll proceed to the next presentation. Next presentation is made by Nouhaila Aynan from Hassan II University of Casablanca, Morocco.
Yeah, let me share my
Could you
screen.
prepare? Yeah.
Yeah.
Okay, we can see. Please go ahead.
Okay. So, good evening, everyone. First of all, let me present myself, self-greeting. I am Noaila Ina, and I am a PhD student at Hassan Toun University of Casablanca, under the supervision of Professor Binay. So, I am delighted to be here. Thank you for this opportunity. Today, I will give a presentation about advances in quantum feature mapping for efficient quantum machine learning. So this presentation is structured as follows. I will start with an introduction, which I will explain quantum machine learning, then an overview of quantum feature mapping methods, after that the results, and at the end conclusion and future work. Okay. So quantum machine learning is a research area that explores the interplay of ideas from quantum computing and machine learning. Machine learning, as you know, is like the art and science of making computers learn from data how to solve problems instead of being explicitly programmed. And quantum computing is, we can say, a description of how information is processed on a special type of machine based on the laws of quantum mechanics. So quantum machine learning is the intersection of these two fields, which has two goals. Like first one, use mathematical tools to solve the problems of quantum mechanics to improve existing machine learning algorithms, or maybe even design new algorithms. The second one is like use classical machine learning to analyze data from quantum experiments. And we have four representation of this. Like either we have classical data with classical machine, and this is the classical machine learning, or classical data with quantum devices, or quantum data with classical devices, or both are quantum. And we can say this is the real representation of quantum machine learning, because quantum devices cannot process or analyze classical data. That's why it's so important to understand the feature mapping. To better understand quantum machine learning is a comparison of machine learning with the classical one with quantum machine learning. For example, we can investigate whether quantum computers can speed up the time needed to train or evaluate a machine learning model. Of course, thanks to superposition and entanglement and interference, we can do that, just for some problems, not all. Yeah, the idea of quantum machine learning came in 2013 by Leod and his team. So to solve a problem that when the data are represented in higher and higher dimension, it is difficult for classical computers to handle such a large calculation. Even if the classical computer can do it, it will take too much time. So that's why they think of maybe we can use like quantum computers using the superposition, entanglement, and interference. So just a recap, what makes quantum machine learning quantum? First, we have the algorithm itself runs on a quantum computer or quantum simulator. By the way, this is a quantum computer. And the data it operates on is a quantum or comes from a quantum state or process. Now the approaches to quantum feature mapping. So this, let me just, okay. Yeah, this illustrates the computation as a quantum circuit. First, we have the qubits of the resistor are initialized as a state 0. Then an initial state is prepared. The step also includes loading data that is encoded in the state of the resistor. Afterwards, we have quantum gates perform unitary transformation on the state of the resistor. And finally, as indicated by measurement gates, one or more qubits are measured as the result of this computation. The overall quantum circuit is characterized by its depth, which is the number sequential executable gates, and the width, which is equal to the number of required qubits. In this presentation, we will focus more on this step, the stage preparation. We say also that data encoding. So we have different methods. We will focus on the basis encoding, QAM encoding, implicit encoding, angle encoding, shimmed decomposition, and QRAM encoding. So let's start by basis encoding. So basis encoding is a method of representing real numbers as binary numbers and then transforming them into a quantum state or on a computational basis. Like here, we have the real number for 0, then we convert, as an example, we convert it to binary form, then we use it to present the state. So using the most powerful computational tools allow us to manipulate real numbers in quantum algorithms. One of the critical advantages of basis encoding is that it enables the use of quantum algorithms for numerical computation, like the quantum Fourier transform and quantum phase estimation, such as, So it is also allows for the efficient representation of high-dimensional vectors and matrices, which is helpful in machine learning and data analysis. However, we can see that basis encoding also poses several challenges because it requires careful consideration of the precision of the binary representation, as errors can accumulate quickly with repeated operations. Additionally, it can be challenging to encode certain type of data, such as the irrational numbers or complex numbers with non-zero imaginary parts. So finding the optimal trade-off between precision and efficiency is essential when implementing basis encoding. Now, QAM encoding, quantum associative memory. It is also a powerful tool for presenting and processing data on quantum computer. So QAM encoding allows us to efficiently store and retrieve data elements in a superposition of basis encoded values in the same qubit register of the form. This means that we can simultaneously perform calculation on multiple data points using equally weighted amplitude to represent each data element in the quantum register. So it is a critical component of many algorithms and has many applications from machine learning to cryptography. And by leveraging the power of superposition and parallel processing, QAM enables us to perform complex computation much faster than classical computers. The amplitude encoding allows for representing multiple data values in a single quantum state, and also it allows the data to be represented in the amplitude of a quantum state. This means that encoding data in a quantum algorithm does not require any calculation, as the amplitude of the quantum state represents the data. We can use this technique to represent a data input vector of length like L with just the log of L qubits. This incredibly compact representation can be used in a logarithmic runtime, depending on the data being encoded. And we can use this expression. So it is important to note that when using implicit encoding, multiple measurements must be taken to estimate the output results. This is because the number of measurements required scales with the number of amplitudes, which can be costly. Now, angle encoding. Angle encoding is an efficient way of encoding data in a quantum system, because each data point is represented by a single qubit using a rotation around the y-axis of the Bloch sphere. So the resulting quantum state is separable, making it suitable for parallel operation. This encoding scheme requires only a constant number of parallel operations, regardless of how many data values need encoded. Sorry. However, the number of qubits required depends on the number of data points, which one qubit needed to encode one input vector component. So we can see that Engel encoding has been used in quantum imaging processing, quantum neural network, and as a state preparation method in various applications. Schmidt decomposition. So finding an efficient way to prepare a particle state can be challenging, especially if we need to learn more about its structure. So one way to overcome this challenge is to use this like an arbitrary state preparation method. So the circuit shows one such method, which creates an arbitrary quantum state on n qubits, resisting using the Schmidt decomposition. The Schmidt decomposition allows us to express a bipartite quantum state as a sum of product states with no negative coefficient, removing its entanglement. So to apply this method, we choose orthogonal bases for each subsystem and find the single value decomposition of the state matrix in these bases to obtain the Schmidt coefficients and the bases. So this circuit takes the Schmidt coefficients and bases of the states as input and prepares on an empty n qubit resistor. So the first part of the circuit transforms the amplitude of the first resistor to Schmidt coefficients, then a series of CNOTs gate copies this state to the second resistor, and finally unitary matrix U1 and V transform the computational basis state into the Schmidt basis state. It's worth noting that arbitrary state preparation is known to be of exponential complexity, meaning that a circuit of exponential depth may be needed in the worst case. However, this method can be helpful for creating a random state with control entanglement. Now, QRAM encoding. So let me first explain the basic functionality of a quantum random access memory, or QRAM. As we know, in classical computing, a RAM receives an address with a memory indexed and loads the data stored at the address into an output register. Similarly, a QRAM provides the same functionality, but the address and the output register are quantum register. So let's take a look here. Given an address register in a superposition of 0 and 1, 0 state and 0, 1, the QRAM creates a superposition of addresses and their data values. So in this example, QRAM loads the corresponding data values for these addresses into an empty output register, resulting in a combined state of the overall quantum system. This is powerful capability in quantum computing because it allows us to process data in parallel, leveraging quantum parallelism. And arithmetic operations such as addition or multiplication can be used as well. So it's worth noting that efficient state preparation methods are required to use QRAM effectively. So now I will share the results of our recent experiments in which we encoded classical data into quantum states using various encoding techniques. We used Qiskit and PennyLane, Qiskit from IBM and PennyLane from Xanadu to perform the experiments. And the results were here, like in this table, we have 4 classical, three classical data points encoded into quantum states using 4 different encoding techniques: basis encoding, Engel encoding, and implicit encoding, QAM encoding, as I explained in the previous slide. So let's take a closer look at the results. For the first classical data point, 5, we have encoded it into a quantum state 101 using basis encoding. The encoded quantum state is represented by the binary number 101. when we use implicit encoding, we get a quantum state that is linear combination of 0 and 1 with coefficients 0.55 and 83, 0.83 for state 1. This means that if we measure this quantum state, we are more likely to get a measurement of 1 than 0. So when we use the Engel encoding, we get a quantum state that is also a linear combination of 0 and 1, but with different coefficients. And finally, when we use the QAM encoding, we get a quantum state that is linear combination of the all like 0, 5, 6, and 7, 0, 1, 0, 1, and 1, 1, 0, and 1, 1, 1. So also like we get similar results for the second and the third classical data points using different encoding techniques. Overall, we can see that each encoding technique produces a different quantum state of the same classical data point. That QAM encoding produce a quantum state that combines both implicit and Engel encoding. So these results demonstrate the power of quantum computing in processing and encoding data and the importance of choosing the right encoding technique for a given problem. This is the circuit that I used to get this result, and also this is just a representation of this state. So in conclusion, we have seen that data encoding is a critical factor in achieving quantum advances in machine learning. So different encoding schemes have different strengths and weakness, and the choice of encoding depends on the nature of the competition involved and the resources available. We have also seen that while some encoding methods require more qubits, they may be more efficient regarding state preparation time. Other encoding methods may require fewer qubits, but could be more costly regarding state preparation time. So looking forward to the future, there are several existing in this field, research in this field. So one direction could be developing new encoding scheme that balance encoding efficiency, state preparation time, and computational demands. We could also investigate the impacts of noise and error correction on this encoding methods and how we can optimize our encoding choices in the face of these challenges. Furthermore, we could explore using quantum-inspired classical algorithms that provide some of the advantages of quantum machine learning without requiring actual quantum computers. Besides, we need to apply this feature mapping methods to real problems. So in summary, data encoding is a critical component of quantum machine learning. We have many existing for future research to optimize and enhance the performance of quantum machine learning algorithm. So thank you for your attention.
Thank you very much for your presentation. Any questions from the floor? Okay, I have one question. Do you have a real quantum computing device in your laboratory?
No, I use just the cloud from IBM and cloud from Xanadu and other companies.
Okay, so just a computer simulation?
Yeah, but I have access to quantum hardware, not a lot of qubits, just 8, and you can use it free plans.
Okay, thank you. Any questions? Okay, thank you very much for nice presentations.
Thank you so much.
Okay, now we'll move to the next presentation made by Tahani Abdelhamid from Helwan University, Egypt. Could you prepare your presentations?
Yeah, sure. 1 second. Can you see it right now?
Yes, please go ahead.
Yes. Okay, it's Tahani Abdelhamid, teaching assistant at Faculty of Science at Helwan University. I'm a master student also in my last year as a master student. I'm also a member at CERN, the Center of the European Organization of the Nuclear Research, Nuclear Physics. Today I'm gonna to give you a talk about the simulation of the pressure effect on the gas transport parameter of the CMS resistibility chamber. First of all, I think the presentation is loading, or you can see it. The outlines is the introduction, aim of the work, method and tools, results and conclusion. First of all, I wanted to give a brief explanation about the LHC, or the Large Hadron Collider. The Large Hadron Collider is the largest and most powerful particle accelerator that have ever been built. It's built at the border between Switzerland and France. It's shaped like a circle, as you see in this picture. The LHC is built to mimic the Big Bang and to discover the new particle, especially the elementary particle. There are four main experiments at the LHC, which is ALICE and the ATLAS, LHCb, and the CMS. These are the four largest experiment at the LHC. Each experiment is built to detect and discover special particles and have a special technique. So we are in Helwan University has a collaboration with the CMS, the compact main solenoid. The compact main solenoid or the CMS is the largest experiment to discover the new particle. It consists of a tracker, which is in the inner side, electromagnetic calorimeter, and hadronic calorimeter, magnet, and main detector. All of them are, as you see in this picture. The tracker is the inside, and the electromagnetic calorimeter, and here is the super magnet, and HCal and ECal here. So in the LHC at the interaction point, there are two beams of proton accelerated with high speed, nearly the speed of light. With this speed, they are collide, and at the four experiments. Due to this collision, there are a lot of particles that can appear. The elementary particle. Sorry. Here is a graph describing the motion of the particle inside the CMS. The first is the silicon tracker, which define the motion of the particle, make bending for the motion of the particle. And behind is the electromagnetic calorimeter, which can detect the electron. So the electron come to this point and be detected. Then the hadronic calorimeter, which can be detected the proton and neutron, all hadrons. And then the superconductor, which produce around 4 Tesla. And then the main detector, which is at the end of the chamber or the experiment. Here, the main detector is the target of our talk. The main detector consists of many types of detectors that can detect the main. The main is a type of the elementary particle. It's decay from the pion, and according to some decay equations, Here is the drift velocity. Each one in the experiment. Here is the drift velocity with the color, with the brown color, and the cathode strip chamber with the green, and the resistive plate chamber, the gas electron multiplier, and the improved RBCs. All the detectors are being built to detect only to can be detected the muon, and they define its position and the time of the muon when it hits with the experiment. Today I'm gonna to talk about the RBC. The RBC, the resistive plate chamber, which is a type of the gaseous detector, which is consist of two high resistive material, which is bakelite material with resistivity around 10 power 10 to 10 power 11 ohm centimeter. In between, there is the gas volume, the gas gap, and this gas gap is consist of a special type of gas mixture, which is freon and isobutane and SF6 with different percentage. On the top of the bakelite material, there is the the graphite layer, which we can use it as an electrode. We can apply the electric field on it. So when a charged particle moves inside, it makes an ionization to the gas inside the gap, and then we can collect the charged particle, the charged electron from the read out strips. This is the resistive plate chamber. So they improved the RBC. There is another type of the RBC, the improved RBC. The improved RBC has the same characteristic of the RBC with with some modifications. The modification have been done on the thickness of the bakelite and the thickness of the gap, and also the type of the readout strips. But they're still using the same gas mixture, which is freon and isobutane and SF6. So both detectors, the RBCs and the improved RBCs, are using the same gas mixture. The aim of the work is that I'm gonna to study the influence of the pressure on the gas transport parameter, and also the effect of the pressure on the primary ionization or the primary number of electrons, and the energy loss of the incidence muon inside the gas gap. And finally, I can check the Bees block theorem and check its plot at different pressure. I used from this study a simulation tool. I didn't make it experimentally. I did it by a simulation. So the simulation tool I have used is Garfield++. Garfield++ is a kind of a simulation bucket that make a simulation for the particle detector, especially for the gas and semiconductor detector. Garfield has some advantages that it can make an overlap with the Mach pulses and heat and NEPM and other kind of libraries. To understand how Garfield++ can work, according to this diagram or this histogram, here Garfield++, it has interface with many packages like Mach pulses and heat and NEPM. Mach pulses is responsible to calculate the electron transport parameter of the gas. So what we can define is the gas mixture and the pressure and temperature. And this package is calculate the electron transport parameter like the drift velocity, diffusion coefficient, and attachment coefficient, and so on. Then heat, HEED, is responsible to measure the primary ionization and the energy loss inside the gas. So we can define the gas mixture we use, and then the particle type and the energy, and then it can give us the acknowledgement of the primary number of the electron and the energy loss. Finally, the NEPM, which is a nearly exact boundary element method, which give us an indication about the electric field or the field map inside the gas gap over the electrodes. So we can define the geometry of the detector and the voltage we apply. So it can give us a field map over of the electric field over the detector. All of this can process inside the Garfield, and we can get the induced signal and also efficiency if we need further informations. So first of all, I will talk about the MacPulses. MacPulses is package. As I said, it can calculate the transport parameters such as the Townsend coefficient, diffusion and diffusion coefficient, longitudinal and the transverse, and the drift velocity. So today we can we will check these transport parameters at different pressure for the standard RBC gas mixture, which is freon and isobutane and SF6. When I draw a relation between the electric field and the drift velocity at different pressures, we get that for low pressure, which is around 0.5 atmospheric pressure, the drift velocity, there is a direct relation between the electric field and the drift velocity. So as the electric field increases, the drift velocity also increases. So by increasing the pressure, we found that the curve is shifting, decreasing. So the drift velocity is decreasing with the pressure. So for the case of the RBCs, it works around 50 kilovolt per centimeter. So at this value, we can see that with increasing the pressure, the drift velocity of the charged particle inside the gas is decreasing. Then for the Townsend coefficient, which represented the primary ionization of the charged particle inside the gas. So for the Townsend coefficient here, we can see also that there is a shift as the pressure increase from 0.5 to 2. There is a shifting, decreasing for the Townsend coefficient. So for example, as we said, at 50 kilovolt per centimeter, which is the operating voltage of the RBC, we can see that for 1.5 and 2 at 1.5 and 2 atmospheric pressure, the multiplication or the Townsend coefficient is equal to 0. So it will affect on the RBC performance. So it's not preferred to work at 1.5 and 2 atmospheric pressure. At 1, we get a value, and also at 0.5. The attachment coefficient, also has been checked at different values of the pressure. So we can see that with increasing the pressure, the attachment is shifting. It's shifting towards the high electric field. So for example, at 50 volt per centimeter, the atmospheric, when the atmospheric pressure is equal to 0.5, sorry, the attachment is equal to 0. And with increasing the pressure, the attachment also increased. And we need a small value, very limited value of the attachment. So it's preferred to work at 1 atmospheric pressure. So we can have an attachment, but with a small value, so it can represent it, it can save the chamber to be work. The longitudinal diffusion coefficient also has been detected by the simulation. And here, according to this plot, there is also shifting, decreasing for the longitudinal diffusion coefficient. And finally, also I have checked the transverse diffusion coefficient of the charged particle. And I got the same behaviors that with increasing the atmospheric pressure, the transverse diffusion coefficient was also shifting toward the increased value, toward the decreased value, sorry. Secondly, I have used the heat package, which is the high energy electrodynamics. The heat package, I have defined the type of the particle, which is muon, incident muon, with energy 2 giga electron volt, which will incident of over 1.4 millimeter gas gap. With the used gas mixture, which is freon and azobutane and SF6 with different percentage, and all the study have been done at 20 Celsius and various pressure. The energy loss at different pressure, as we see, it's a histogram of the energy loss for around 10,000 event of the main incident on the gap. So as we see, at low pressure, we get a small energy loss. So the most probable value of the energy loss has increased from 0.27 till 1.5 kilo electron volt as the pressure increased from 0.5 atmospheric pressure to 2. So with increasing the pressure, we found like a shift in the histogram according towards the high energy loss. Finally, I have checked the number of primary electron also for the incident 2 giga electron volt incident muon on the same chamber and at the same temperature, and we get that the primary number of the electron has also shifted, increasing at low atmospheric pressure. At low pressure we got that the most probable value of the primary number of the electron was 5, and when we increased the pressure from half to 2, we got that it increased by around 30 electron per atom. Finally, I have checked the Bethe-Bloch theorem, which represented the energy loss of the incident particle inside the gap, which has a relation here. I have simulated the energy loss per millimeter, and with the relation with the main energy by mega electron volt, and we got the same behavior, the same curve, but is shifted, increasing as the pressure increase. So with increasing the pressure, that we get a high energy loss per millimeter, high energy loss, and this represented the or proved the Bethe-Bloch theorem. I'm gonna to conclude this study that all the transport parameter have been changed with the pressure, the drift velocity curve and the longitudinal diffusion curve and the transverse diffusion coefficient curve have been shifting, decreasing with the increasing the pressure, and the attachment coefficient curve have been shifted toward the increase of the high electric field. Also, the number of primary electron has increased by around 30 electron when the pressure has increased from half to 2, and the most probable value of the energy loss has increased by from 0.27 to 1.5 kilo electron volt with increasing the pressure to 2 atmospheric pressure. Finally, I want to thank you. For giving me this opportunity to share my study. And also I wanted to thank my supervisors to encourage me to complete this work. Thank you so much. And any question will be more than welcome.
Thank you very much for your talk. Any questions from the floors? I see no questions. Okay, thank you very much for your wonderful talk.
Thanks.
Okay, we want to go back to the talk of Mazhar Hussain from Karnataka University, Dharwad, India. Mr. Hussain, could you prepare your presentation?
मैच करना नहीं हो रहा है, देखो स्लो हो रहा है, नहीं हो रहा है शेयर स्क्रीन। बता नेट सब है। Is my screen available?
We can see your PowerPoint file.
Okay, thank you.
Could you share your PowerPoint?
Okay. Is my voice audible? Hello.
We see your desktop,
Okay.
not PowerPoint file.
Now?
No.
Wait.
Could you share your PowerPoint file?
Now, sir?
No. We only see your desktop.
What do you want then?
We can't see your file, your presentation. We can't see. So
No. Can I start presentation now?
no, you can. We can't see your presentation file.
So can I start, sir, now?
You once again try. First unshare and then share.
Sir, can you repeat, please?
We can't see your presentation file.
Okay, sir. Okay. Now I'm starting. So my name is Mazhar Hussain. I'm from India.
Oh,
I have done
okay.
some.
We can't see your file. You can
Okay,
see your
okay, sir.
presentation.
Okay, sir. Okay.
Only we see your desktop.
Okay. Okay, sir. I'm starting, sir. Now I'm starting. And once again, I'm starting. Thank you very much for giving me a wonderful opportunity. I'm very much thankful to the scholars conferences for giving me a brief introduction of photoelectric effect. So let me start. What is photoelectric effect? When light shines on a metal surface, it will eject the electron from the metal surface. This phenomena is called photoelectric effect.
Mazhar, can you hear me?
Yes, yes.
We are unable to see your presentation. First, open the PPT.
Oh, you are unable to see.
Just double click the presentation. Open your PowerPoint slides. Where are you? The share screen is there now. Just open there.
Ah,
Dr. Mazhar, what you are browsing? Can you please open your PowerPoint slides, please?
wait, sir. Now, sir.
Yes, sir. Can you please press F5? F5 key.
Okay.
F5,
Yes, sir.
not F5 key, doctor. In the footer, you can just see the minus percentage. There is a funnel symbol. Click on the funnel symbol.
I have pressed it, sir, but it's not working.
Just can you press here from beginning? F5 key, if you press, it will come and the presentation mode.
It's not working, sir.
Yeah, here you can just see 69% is there, right? In the footer, there you can see the funnel symbol. Click on the funnel symbol. Besides 69%.
Your screen is
Open the presentation. In the presentation, there is a percentage symbol in the footer, 69%. Can you see that? Beside that, there is a funnel kind of symbol. Just click on that. Right side, doctor, right side footer, 69%. Right side. Right side bottom. Right side bottom. Your screen is fine. Just press F5.
Screen is audible.
Press
Sir, is my screen audible now?
Yes, it is fine. Press F5 key. You are not listening to me. F5 key.
Hello, sir.
Can you hear me? Yeah, start presenting, doctor. Start presenting. Hello. Hello. Doctor, start presenting.
वीडियो तो ऑन करके देखो वीडियो ऑन करो
नहीं वो कनेक्ट हो रहा है
कैसा प्रेजेंटर है तू भी
वहाँ ऐसा कर रहा है यार एक बार वर्क नहीं कर रहा है देखें ये वर्क नहीं कर रहा है
मौसी चल रहा है योगर्ट को भी जा सकता है तो
Sir, is it audible now? Visible now?
Yeah, it's okay. You can start now. Yeah, you can start.
वर्क नहीं अब भी कर रहा वर्क है
उसे खचा खचा करने में
नहीं काम ही नहीं कर रहा
ये कर को एक बार कनेक्ट होता क्या देख
करा एक बार
बैक जाको
उसका रहा तो भी
मैसेज नहीं कर सकते क्या हमको कहीं में गूगल मीट है
इसमें जूम
कहीं जूम ये केस का वीडियो
जी यहाँ है
ये क्या भी
वो नहीं छोड़ो छोड़ो इसका जाना कौन से नहीं वो छोड़ के उठा है
Dr. Maza, can you hear me?
नहीं लो कनेक्ट चोरा नहीं हुआ
नेट है नहीं फिर इसमें
नेट है इसमें है तो नेट कनेक्ट करो नहीं
Hello, Dr. Shiro.
है कि नहीं क्या देखो सर ही नहीं दिन भर वीडियो सर
नहीं है तो कनेक्ट हुआ नहीं
कनेक्ट हुआ कहता है वो दिखना 50% से कम है तुम्हारा जमा को
Dr. Astos, can you hear me?
Yes, sir.
Can you start presenting yourself, please? I'll start with Mazhar.
Okay, sir.
Can you share your screen, please?
Okay, sir, I'm sharing. Sir,
Just a minute. You just share.
hello.
You just be ready to share.
Okay, sir.
Just ready to share.
Hello.
Mazhar, please. Yeah, Dr. Ashutosh.
Yes, sir.
Just double click on your full screen, like presentation, so that it will enable. Yeah, just press F5. F5 key you can press, doctor, directly, no problem. Yeah, slideshow. Click on the slideshow from beginning. Yes. Yeah, you can. The stage is yours now. You can proceed.
Okay, sir. Thank you. Good evening, everyone. My name is Ashutosh Kumar. I'm going to present in the international conference on physics and quantum physics. My topic is non-equilibrium heat engine with 1 and 2 qubit that operates between squeezed thermal bath. This work has been done with in a collaboration with Luchan Bhagrati, who is a scientist at Tata Steel in India. Saurav Leri, who is my supervisor at BIT Mishra, and Subhasis Banerjee, he is a professor at Indian Institute of Technology, Jodhpur, India. I'm audible, sir? Sir, I'm audible?
Yes.
Okay. These are my content where I basically started with the introduction of microscopic heat engine. Then I will go discuss about the schematic diagram of my model. Then I will talk about the squeezed bath, and then I will go to the model and theory of 1 and 2 qubit heat engines. After that, I will discuss about the calculation of thermodynamic quantities which I have used in our experiments, and then I will conclude the result, which is basically the comparison between the 1 and 2 qubit heat engines. Then I will summarize my work, and this is the references. So, introduction. Microscopic heat engines, both classical and quantum, has been a subject of interest in the last 1 and 2 decades or so. At this level, the thermal fluctuations become the important, which makes the difference, which makes the dynamic different from the microscopic heat engine. Basically, in a classical heat engine, generally Stirling engine or Carnot engine is used. In 1959, Skuld and Dubois so the 3-level masses can be used as a quantum heat engine, but it gives a quasi-static picture only. The only quantum in this experiment is that they have used the discrete energy levels of a working medium. So these microscopic heat engine, classical or quantum heat engine, both are used, are extremely useful in the medical industries, like for the delivery of drug. It can be used. It can be used as a delivery of drugs, or it can also be used as a diagnostic purpose. So in my model, there is a term called squeeze bath. So I'm going to explain what is the squeezing. It is a quantum optic phenomena where the fluctuation of one conjugate component is suppressed while enhanced in another one. So the squeezing is the stretch. That is means the stretching of a fluctuation in one of the quadrature, and the other quadrature is compressed. We can like example, we know the uncertainty principle, that is delta x delta px is is greater than equals to h cut by 2. So when we change the when the uncertainty of delta x is reduced, then that much amount of uncertainty is increased in momentum, that is delta p. So the product of delta x and delta p would satisfy the maximum, would satisfy the uncertainty principle given by the Heisenberg. So these are the excusing operator which is shown in the equations, where this R is the capital R is R e to the power I theta, where small r and theta are the excusing parameter. Throughout the experiments, we have found that theta does not contribute anything in our experiments. So we say, throughout the experiment, we set theta equal to 0, and for the excusing parameter, we only changing the R only. So after operating the excusing parameter in our system, the density operator for is given by the equation shown here. This is rho b excusing equals to SR rho b SR S dagger R, where rho b is a thermal density matrix and this rho b excusing is a non-thermal one. So and rho b is given by this equation, which is the e to the power beta HB. HB is a Hamiltonian and trace of e to the power beta H. So after when we use this excusing parameter, we have found that the temperature of the system, the temperature of system will enhance, which is given by the beta effective, which is B naught cos hyperbolic 2R, where B naught is a thermal, B naught is the that is inverse temperature of thermal bath. So finally, this is my model of quantum heat engine. Here we can see this figure. Here I have mentioned this this is an Otto cycle. So it has 4 strokes: stroke 1, stroke 2, stroke 3, stroke 4. So the stroke 1 and stroke 3 is a unitary strokes, which is adiabatic. Here the bath is decoupled from the system. So when we evolve rho A to rho B, there is no bath, only the frequency omega C changes to omega H. So the Hamiltonian changes from H omega C to H omega H, which is linearly changing with respect to time. Again, from stroke 3, we can see that omega H to omega C, and this is also linearly. I will give you the equation further in the further slides. So this stroke 1 and stroke 3 is a unitary stroke, and again at B we just coupled the bath, hot bath here, and the evolution is non-unitary. So the evolution is governed by the quantum master equation. Here also, yes sir. Any question? Okay. Okay. So now I'm going to discuss the model of the theory of model and theory of quantum heat. So I already discussed in the unitary steps, unitary stroke, the equation is governed by this equation. This is called a von Neumann equation, and here H omega is governed by the the omega is changing with respect to time with this equation in A to B stroke and C to D stroke, which is mentioned here. H omega t is given by the omega t by 2 sigma z, where sigma z is a Pauling matrix. Here we have taken h cut kb is goes to 1 for simplicity. And again, similarly, we can also see that for the non-unitary strokes, which is governed by this quantum master equation, which is shown. I'm not going get into detail of this equation. So here we can see that this equation, which is r equals to cos r sigma minus plus it's this sigma minus is a lowering operator, and r is a squeezing parameter, phi is also a squeezing parameter, and sigma plus is raising operator. And this NTH is NTH gives the number of photons emitted from the energy levels. So again, this is for the 2-qubit system, and the dynamics are same. Only changing is the Hamiltonian. So here we have used this Hamiltonian, which is which is in a dress state basis. So we have chosen the dress state basis for the simplicity. Here, this omega 1 and omega 2 are the energy spacing of bath 1 and 2. And this capital gamma 1, 2 is a dipole interaction strength of the 2 qubit. So it is dependent on the distance between the 2 qubits. And this is a non-intrusive part of the 2 qubit engine. So calculation of thermodynamic quantities. So only I have to calculate the density operator at the 4 corner of the our strokes, four strokes. That is the corner of the which is the diagram shown over in previous slides. Rho A, rho B, rho C, and rho D. And this can be calculated using the using this this formula, that is average energy is, that is trace of rho T alpha H alpha. That means rho T at alpha is at ABCD, at the 4 corners of the cycle, or HT is a Hamiltonian at that point. So if we get this rho density matrix at the end of the every strokes, then we can calculate the average energy. And if we will get the average energy, then we can calculate the this energy and heat and energy. So we can also get the power, work power, and efficiency. Here we can see that in the efficiency is not dependent on the any squeezing parameter. It is independent of squeezing parameter. It only depends upon the energy change in energy levels, which is omega C and omega H, which is shown here in this equation. So here we have this is the result part. Here we have shown that the power as a power versus the ratio of temperature for both the OQE and TQE. So figure A is for the OQE, that is 1 qubit engine, and B is for T qubit engine. This is for the different squeezing parameter, we can say there. So we can conclude from these 2 graphs that 2 qubit engine gives higher power with respect to the OQE. Power as a frequency ratio. So again, we have plotted the power as a ratio of frequencies. So in both the OQE and 2QE, and we here also we have we confirm that we get the confirmation that the power is getting more in 2 qubit engine than in 1 qubit engine. So now this figure shows the power versus frequency ratio at different temperature ratio. Here we have we have taken the different temperature ratio. This is TC by TH, and we get this non-monotonicity graph. From this graph we have taken out the maximum peak point in this family of curves from both the curves, and we have plotted the efficiency at maximum power, which I am showing in the next slides. This one. So in this figure, we have shown the efficiency at maximum power for the OQE and TQE. So and this is for the different squeezing parameter. So we can see that when RH is 0, the squeezing parameter in the hot bath is 0. Then this agrees with the Culligan L1 efficiency, which is the efficiency at maximum power given by the Culligan. So here we have some slight deviation from this black curves, which is the Culligan L1 efficiency. But in the 2 qubit region, we can see that this coincide perfectly. So this is because of some this is because of the decay of the energy levels is the decay rate is slower than the T qubit. So, okay. Now we have plotted here the population ratio population and the effective temperature for the O qubit to find out the effective temperature of the system. So what we have done here is we have just taken the ratio of rho E by rho GGG, which is like steady state by ground state, and we have just equated this ratio with the Boltzmann factor. So from this equation, we can get the beta TH effective is equals to 1 upon beta H effective, which is plotted here with respect to RH. And this is for the 2 qubit. So one more additional parameter is R12, which is the distance between the 2 qubit. This is for the only 2 qubit system. So we have that is the effect of independent and collective decoherence region, and this is only for the T qubit engine. This is absence in the 1 qubit region. So when the qubits are this parameter R12 shows that the distance between the 2 qubits. So when the 2 qubits are lesser than 1, this means it is an individual decoherence. And sorry, when R12 is greater than 1, then it is individual decoherence, and when R12 is less than 1, it is collective decoherence. So collective decoherence means the 2 qubit is the bath is the bath fills the 2 qubit at a collectively, and when it is greater than 1, then bath fills the 2 qubit independently. So we can see that when bath is in the collective region, so it has less power than the independent region, in both the case in T qubit and O qubit. And this is because in the independence decorum region, in the collective decoherence region, the decay channel reduces in comparison to the individual decoherence regions. So as the decay channel reduces, the power also get reduces. So the summary of my experiment, my work is here we have just taken the Lindblad master equation and was used to examine the 1 and 2 qubit auto engine in the presence of skews bath. We have found that T qubit gives the higher power than OQE, that is 1 qubit engine, and T qubit shows the better agreement with the Cullinan-Elbowing efficiency. These are my references. Thank you.
Thank you very much.
Thank you, sir.
Are there any questions from the participants? Okay, I see no questions. Okay, thank you very much for interesting talk.
Thank you, sir. Thank you, everyone.
Okay, I'll proceed to the next.
Should I stop my screen sharing?
Thank you. Okay, we will proceed to the next talk. Next talk is given by Gisela Anna Maria Sarajin. Could you prepare your presentation?
Yeah, of course. Can you see my screen?
Yes, go ahead, please.
Okay. Good afternoon. Thank you very much for the opportunity to be able to present in today's session the work entitled Comparison of Treatment planning techniques for a synchronous bilateral breast cancer patient in the setting of the hypofractionated approach. In this presentation, I will present a case report in which I compared different irradiation techniques in the case of bilateral breast cancer with hypofractionated dose. First of all, I want to start it with my presentation. I want to present myself. How you say it, my name is Gisela Ana Maria Sălăgean. I'm a medical physicist in radiotherapy department and a PhD student at Babeș-Bolyai University in Romania. My research interest is the breast cancer area and also bolus material. The agenda for this session, it will be the following: a short introduction, the presentation of the case, and I will describe the treatment planning techniques and short conclusions. I have no conflict of interest to disclose. Okay, as we well know, breast cancer is one of the most common malignancy in women. Approximately 3 million women suffer from breast cancer every year, according to statistics from the World Health Organization. For breast cancer, we have different types of treatment, from surgery, excision, hormone therapy, chemotherapy to radiotherapy. This combined correctly can lead to exceptional results. Our motivation and goal was to evaluate the most optimal way of irradiation in the case of bilateral breast cancer with conservative surgery. So in this case, we consider the case of a 66-year-old patient diagnosed with bilateral sectorectomized breast cancer with sentinel lymph nodes evacuated with the histopathological results of clinical T2 and T1, which means for the right side, it's stage 2, and for the left side is a stage 1 cancer. In this case, we decided to have hormonotherapy with neoadjuvant chemotherapy and adjuvant radiotherapy. For the planning calculation part, we have the following information. We used an Elekta Infinity linear medical accelerator for treatment delivery. This is equipped with 2 photon energy and 5 electron energy. As a characterization of the collimating system, it presents the Agility DMLC leaves, which have the thickness of 0.5 centimeter, and they have a speed of the movement of 32 millimeter per second. The machine is capable for realizing a dose rate of deliver a dose rate of 600 monitor units per minute. The plan were calculated using the Monaco 5.11 planning system. In the case of the radiotherapy treatment, the simultaneous irradiation of the 2 breasts was chosen with a hyperfractionated dose of 40.05 gray in 50 fraction. And the treatment plans was calculated using 3 different techniques: VMAT, IMRT, and 3D conformal. The patient was scanned in the supine position with her arms about her head on a breastboard position support. The contour of the patient's shape, what we can see with brown, was made. It was created by the auto-contouring tools from the treatment planning system, and one radiation oncologist performed the contour, the volume target and organ at risk contouring. The clinical target volume, which means the 2 tumor, was created according to the preoperative description of the lesion and pathology report, with the addition of the 0.7 margin to the tumoral bed. And the planning target volume was created with 0.5 centimeter margin from the CTV. The planning part. The 3D conformal plan was made according to the technique of separate isocenter because the planning system doesn't allow us otherwise. Using the collapse cone calculation algorithm, the arrangement of the field was made that they are tangential to the breast and to avoid their overlap on the sternum area. So in this part. 4 fields were used for each breast separately. In total, 8 fields per summation. To homogenize the plan, the field-in-field technique was used, as well as physical compensator were used. The protection of the organoid risk take place by covering them with the collimator system. We used 6 MeV energy for calculate the plan. From our statistics, we can see that the coverage of the PTV, right, it's 95.7%, and for the right breast, it's 94.75%. Also, we reached the maximum on summation of the almost, it's approximately 170%, which is a little bit more. So we go to the next planning technique, the IMRT, Dynamic Multi-Level Collimator Intensity Modulated Radiation Therapy. For calculation of the plan with IMRT technique, we used 12 irradiation field from which the internal fields have the same angulation of the gantry. So in this part, but they are for optimizing on individual tumor structure. We use the Monte Carlo algorithm as a calculation algorithm. The arrangement of the fields take place by establish the main tangential of the breast and ending 2 fields plus minus 10 degrees from the position of the main tangential. The isocenter was located in the center of the total PTV on the midline in the sternum area in this region. So we obtain a coverage of the target volume in proportion of 95%, which is the minimum coverage to accept the plan. And the maximum was 107.78%, which is acceptable also. The volumetric modulated arc therapy plan was calculated also with the Monte Carlo algorithm. To create the plan, we used 2 coplanar half arc. We can see with red and blue on this image. They are focused on each breast separately. In that way, we have the best possible coverage. The position of the collimator and the treatment table are in the original position at 0 degree. In this case, we can see that we obtain a good coverage. For the right PTV, we have 95.73%, but for the left part, it's only 94%. And also the hotspot, it's a little bit high, it's almost 112. The plan evaluation. The difference between the 3 techniques was performed statistically using as a reference the constraints given by the RT charm and the STAR trial, respectively the STAR AB trial. the dose distribution at the level of the target volume, at the level of the organ at risk, as well as the treatment time and possible error factors were compared in the plan evaluation process. The evaluation of the plans also took place by comparing the conformity and the homogeneity index. For calculating these indexes, we are using these two formula. In the attached image, we can see the comparison of the three plans and the arrangement of the fields, the irradiation fields. As can be seen from the point of view of the dose distribution in the transversal plan, the plans calculated with IMRT and VMAT technique have the best compliance, because in the 3D technique, we have those in the outside of the target volume, which means higher toxicity for the health part of the body. To evaluate the plan, we use the statistical table generated by the Monaco software, which seems a little bit complicated, even if I highlight some value here. But for understanding easier, I will simplify it a bit. So, how I said, all the irradiation techniques show that from the point of view of coverage of the target volume, we are approaching the desired coverage of the 95%. But if we are looking statistically, we have some differences, and these were observed in both of terms of homogeneity and conformity. And also evaluating the hotspot, as well as the risk of systemic error of position and overlapping, we consider that the 3D plan, it was suboptimal. So it remained the IMRT and VMAT plan for comparison. We can notice that the difference between IMRT and VMAT, it's not that high, but because we have some differences, and also because we have a better coverage in IMRT technique, we decided to have the IMRT plan. So as a conclusion, I can say that in our clinic, we consider the IMRT plan, it's more optimal in the case of simultaneous irradiation of both breasts, reducing the toxicity at the level of the treated tissue. And also it's more safe and the toxicity is lower for health tissue. As a future perspective for this study, we would be to realize a study where we will study more patients. We have more patients in the study, and we want to use the constraint by what is used in hypotrial in the randomized Danish breast cancer from the Danish breast cancer group. This is my bibliography, and thank you for your attention. If you have any question.
Yes, thank you very much. Any questions? No questions from the floor?
Okay, then, thank you.
Okay, thank you very much. Okay. Next talk is by Gloria Carrascal, Universidad de Atlántico, Colombia. Could you prepare your presentation?
Yes. Can you hear me?
Yes.
Okay, I will share my screen. Someone is sharing the screen, so I can share. Okay. Can you see my screen?
Yes.
Okay, let me. In this way. So I will talk about my research. This is the estimation of solar radiation in Colombia using the artificial neural network models. The aim of this model and this project is to bring a solution on the worldwide problem that is about the climate change and the energy transition. So photovoltaic energy, it's one of the most cost-effective options to help the societies in this transition. But so photovoltaic energy power depends on the variability of the solar irradiation, and then they need some model or some tools that helps to calculate the energy power. But it's better if these instruments or tools are easy to implement and with a low cost in order that help to accelerate this transition. And in these order of ideas, the artificial neural network models and machine learning models in general are able to help with this solution because they can predict, given a location, the solar variability with a high accuracy. So in this certain idea, the objective of the project is predicting the average daily solar radiation in the 6 geographic regions on Colombia based on open database applying artificial neural network models. The open database are brought by Copernicus Marine Service, and we will use them because the project gets support from the Expo Solar in Colombia. They will provide them to us the data in situ in the country. The methodology followed by the project is the exploratory data analysis. That is where we are right now. In order to identify the structural and relevant parameters to use. After that, if we understand the structural behavior of the data, we can apply the field propagation model. And after that, we can make the evaluation of the model performance with the training and tested data. And finally, we can predict new data, giving a time stamp and evaluate the radiation for the regions. So what we are measuring here, we are measuring the solar irradiance. And then this is the solar irradiation is the power per unit area received from the sun. And this is irradiation. It's given in the wavelength region visible light. So the measured units used in this project is International System of Units. And some of the main features or some of the main components of solar irradiation that will be used are the direct normal irradiance and the diffuse or horizontal irradiance that will use it like our features variables. And the global horizontal irradiance is our target variable, is the predicted variable. So the global horizontal irradiance is defined like a disciplinary equation, where coseno de theta, where cos is theta, what cos of theta of s is the angle measured between the air and the air zenith. This data provided is a tile data modeled, so Copernicus used treated the Earth like a big sphere, and they calculate the numerical process with the next equations. That is a simplified equation for solar irradiation in a given day, and they provide the public data with this type of numerical methods. So some of the results from our exploratory data analysis are the next. In the study area, Colombia, the geographic division of Colombia is the next. We are trying to make a similar map, identifying, but instead of this color will show the solar irradiation intensity in the different regions of Colombia. The distribution of the variables in the given variables is the next. We can see that these variables doesn't keep a normal distribution. It's more distributed about the left, about the right part. So we can scale these variables in a range between 0 and 1, and we don't need to normalize the variables. So we also made a bivariate analysis about the principal features, and we couldn't find the data. The behavior of the data is distributed between clusters, which giving some important insights about the structure of the solar irradiation. And then we made a correlation between we made a matrix of the correlation, between the variables. These are all the variables given by your data set, and we couldn't find that the total radiation on the top of the atmosphere is not significant in variable. Instead, this will overfitting our data. So we only select like a featured variables, being horizontal, diffuse horizontal, being normal irradiation, and our target variable that is global. Some of the conclusions given by our exploratory analysis are the next. We expect to make the exploratory analysis with the data in situ provided by the IDM, the Institute of the Hydrology, Meteorology, and Environmental Studies. And the data and the bivariate scatter plot, we can see that this clustered, and this cluster are fragmented in some steep. So this implies that we need to classify this. We need to classify this data. We need to identify the internal structure of the data, maybe by making a PCA analysis. This tail analysis helps to understand the internal structure of the data, because focus in the principal components of the data. And after that, we can understand how many clusters are formed between this, giving a time stat between the solar irradiation. And after that, we can identify what type of classification problem we had and implement the model. So also, it's important to make a regression analysis, the most basic predictive model, but it's important because we can compare it. Our model is truly improving this measurement, or we can do the calculation with basic model as well. And also, we are implementing some time series analysis between 3, 6, and 11 months to identify the trends of pattern between the global irradiation, in order to understand the inner structure, understanding the trends, and select the best activation function, how many hidden layers and neurons we need to implement in the creation of the model. So that is all the progress about the project. And thank you so much for your attention. Any questions?
Thank you very much for your poster presentation. Any questions from the floor? I see no question. Okay, thank you very much. So the next
Dr. Khalid Al-Hamad. Dr. Shiru, this is Victor, organizer. Yeah.
Hi. You can see?
Can
Hello?
you zoom in,
Hi.
doctor? Yeah, can you zoom in? Yeah.
Sorry, you can hear me?
Yeah, you can start.
Yeah, okay, thank you. Welcome, ladies and gentlemen. My name is Khalid Al-Hamad. I'm a lecturer in medical physics at the University of Hafr Batan, Saudi Arabia. I'm sorry, I'm not showing my full poster because I have, let's say, a technical issue in my laptop. So I'm currently doing this presentation through my phone. This poster or this research we have done in the University of Hafr Batan is a mental carrier simulation of a new configuration of a new type of gamma camera. A standard gamma camera used two parallel head gamma detectors with two parallel head detectors. While this configuration will be two curved detectors. When gamma emitting, it's the only photons that allowed to enter and be recorded as readings in the gamma camera. It's only the parallel to the collimator of the gamma camera. But in this experiment or in this research, we did a fully curved gamma camera to allow a more counts of photons to be detected. It's not working like a converge or diverge collimator, because the converge or diverge collimator will have a converge or diverge collimator, but the detecting area which will be flat. But in this configuration, both the collimator, detector, all the machines, both machines are curved. Only photon in parallel detectors, only perpendicular gamma photons will be readings. The rest of the photons will be considered as scattered because it's not in the collimator hole. The study aims to develop a fully curved gamma camera using a mental carrier simulation in GATE to investigate whether there's any advantages in this configuration in terms of sensitivity or resolution. I used GATE to develop a two gamma camera. I built two gamma camera, one flat, the standard gamma camera you found in every hospital, and now the other one is the new configured configuration, a curved spec head gamma camera with the same component, with the same thickness, but this one is curved, this one is flat. I did also a couple of simulations, a set of simulations. I used two phantoms with technetium technetium 99 and 99. Two phantoms. One I used a large phantom, and one I used the small one. In both small and large phantom, the curved gamma camera yielded a better count in terms of sensitivity. In terms of resolution, gamma camera and curved and flat has yielded approximately the same result, but in terms of sensitivity, curved has the upper hand when compared with a flat detector, when imaging a small object especially, and also when imaging a large objects like large phantoms. But in terms of resolution, it's pretty similar. There was a limitation in the simulation. I think if there is the computing power, it was a big limitation because I did it to a certain number of counts. So it was limited. I think it will reach its full capacity if I used a more computer with more computing power to reach its maximum potentials. Hopefully we'll do more work on this one because in terms of sensitivity, it was better. In terms of resolution, it was slightly better. but I think there was this difference will. I think we will yield a better difference when we have, let's say, better scanning time and with we're taking a more number of counts and more number of tests. That's the end of my presentation. Thank you, ladies and gentlemen. And I hope, please, if you have any question, please ask.
Thank you for your poster presentation. Any questions? No question. Okay, thank you very much.
Thank you.
Dr. Mazhar, can you start? Soraya will take time. She's trying to connect. Mazhar, can you present now? Dr. Mazhar Hussain. Dr. Mazhar, can you hear us? Can you please communicate whether can you able to hear?
Hello, sir. Okay, sir. Okay. Sir, please let me know whether my screen is available to you.
Yeah, okay. We can see you, your presentation.
Yes, sir.
So
Yes,
go
sir,
ahead,
sir.
please.
Is my screen available, sir?
Yes. Okay, go ahead,
Okay,
please.
sir. Okay, I will start now. Thank you, sir. So my name is Mazhar Hussain. So I have done a new research on the phenomena of photoelectric effect. So my name is Mazhar Hussain. I am from India. I have done a new research on the phenomena of photoelectric effect. So what basically is a photoelectric effect? When light shines on a metal surface, it will eject the electron from the metal surface. This phenomena is called photoelectric effect. See, it was Einstein who first explained the phenomena of photoelectric effect by using Planck's quantum theory. In one of his research papers, those research papers are called Annus Mirabilis. He explained the phenomena of photoelectric effect by using law of conservation of energy. Please note on this point, he uses law of conservation of energy. Law of conservation of energy and Planck's quantum theory. He uses Planck's quantum theory. So what basically is photoelectric effect is when light shines on the metal surface, it will eject the electron from the metal surface. This phenomena is called photoelectric effect. So according to Einstein, when light is made up of discrete units of elementary particles, those particles are called photons. When these photons falls on the metal surface, they eject the electron from the metal surface like this. When these photons falls on the metal surface, these photons eject the electron from the metal surface. This phenomena is called photoelectric effect. Hello, sir. Yes, sir. Okay, sir. Yes, sir. Yes, sir. Yes, sir. Okay, sir. Percentage symbol, sir. Okay, sir. Okay, sir. Funnel symbol. Okay, sir. Okay. Okay, sir. Okay, sir. Okay. Share screen. No. Funnel system. Okay, sir. Okay. Yes, sir. In share screen is there. Next, sir. Okay. Yes. Now it is correct, sir. Okay, sir. Now it is. Okay. Okay, sir. Thank you. Okay, okay, sir. See, according to Einstein, the light is made up of discrete units of elementary particles. Those particles are called photons. When these photons falls on the metal surface, they eject the electron from the metal surface. See, basically photoelectric effect happens like this. When these photons falls on the metal surface, they will eject the electron from the metal surface. Einstein's equation of photoelectric effect is given by this. H nu is the photon energy, phi naught is the work function, and after liberating from the metal surface, the electron will eject out with the maximum kinetic energy. And this kinetic energy of the electron gives rise to the electrical energy. If you rearrange this equation, H nu phi naught is nothing but the work function, H nu naught. If you rearrange this equation, you will get H nu minus H nu naught is equal to half MEV whole square. This is another form of the Einstein's equation of the photoelectric effect. See, according to Einstein, the energy absorbed by the electron, by the photon, by the electron is used in two ways. A part of this photon energy is used in liberating the electron from the metal surface, called the work function. After liberating from the metal surface, the electron will eject out with the maximum kinetic energy. So this was the basically explained by the Einstein. So my question is, can we explain the photoelectric effect by using the law of conservation of momentum? This was the question arrived in my mind. So let me explain the photoelectric effect, and we will get the very interesting equation that velocity of electron is 2 times the speed of light. So light is made up of discrete units of elementary particles called photon. According to me, this was what I observed. Okay, and the momentum of each single photon is given by h nu by phi according to de Broglie hypothesis. P is equal to h nu by phi. The whole momentum of the photon is absorbed by an electron during the collision. What the collision happens between the metal surface and the electron is absorbed by the electron. A part of this momentum is used in liberating the electron from the circumference of the orbit of the metal surface. It is called the threshold momentum, and it is denoted by phi. This is the threshold momentum. A minimum amount of momentum is required to eject out the electron from the metal surface, like this. A photon hits, a minimum momentum is electron. Momentum is required to eject the electron from the circumference of the orbit of the metal surface. This is called a threshold momentum. To just eject out the electron from the metal surface, this is called the threshold momentum. After ejection, what happens? After liberating, the electron will move with the maximum momentum called MEVE. where m is the mass of electron, v is the velocity of electron. This momentum of the electron is responsible for giving the photocurrent. Please note my points. Why I'm telling like this? By using the law of conservation of momentum, we have h nu by c is the initial momentum of the photon. This is h nu by c, the incoming momentum. A part of this momentum, h nu naught by c, called threshold momentum, is used to just eject out the electron from the circumference of the orbit of the metal surface. After that, that electron will move with the maximum momentum mev. Of course, the components I have not taken. I have taken it for a simple case. If I rearrange this equation, I will get h nu by c minus h nu naught by c is equal to meve. So this is the equation of photoelectric effect in terms of law of conservation of momentum. So the electron at rest only have the electric field. Please note, this is very, very, very important point. The electron at rest only have the electric field. The electron gets motion because of the momentum. Because of the momentum, the electron has the motion. Therefore, the electron gets motion because of the electric field. Therefore, the momentum of the electron is responsible for giving the photocurrent. The electron at rest only have the electric field. The motion, the momentum of the electron is responsible for giving the photocurrent. This one, MeV is there. The momentum of the electron is responsible for giving the photocurrent. The electron at rest only have the electric field. The motion of the electron is responsible for giving photocurrent. When the electron moves, it will give the electric current. In this case, it will give photocurrent. Next case, the energy of each single photon is given by h nu according to the Planck's quantum theory. A minimum energy is required to just eject out the electron from the metal surface. This is called the work function. Even Einstein has mentioned this. By using the equation of the photoelectric effect in terms of the law of conservation of momentum and taking the least common multiple of speed of light, we will get h nu by c minus h nu naught by c is equal to mev. This equation just now I have derived in above slide. If I take the least common multiple of c, I will get h nu minus h nu naught by c is equal to meve. If I cross multiply this equation, I will get h nu minus h nu naught is equal to mevec, where m is the mass of electron, v is the velocity of electron, c is the speed of light. H nu is the quantum energy of the photon, h nu naught is the work function, is equal to mevec is the kinetic energy of the ejected electron from the metal surface. Now you compare this equation with Einstein's equation of photoelectric effect. Now h I have taken outside, Planck's constant I have taken, nothing more difference. I have just written it in so beautiful form. Comparing Einstein's equation of the photoelectric effect with the new equation of the photoelectric effect. This equation in above slide I have just written here. I will compare this equation with Einstein's equation of photoelectric effect. This equation is Einstein's equation of photoelectric effect. H nu minus h nu naught is equal to half mev whole square. And this is the new equation of the photoelectric effect. Since left hand sides are same, so I can compare right hand side. H nu minus h nu naught is same and h nu minus h nu naught is same. Here Einstein has written the maximum kinetic energy half mev whole square. But I got mevec as the maximum kinetic energy. So therefore, the both can be comparable. So this is the new equation of the photoelectric effect in terms of law of conservation of energy. Please note. So comparing left hand side and right hand side of Einstein's equation of photoelectric effect and the new equation of the photoelectric effect, I have given it's a new equation. I have termed as a new equation of photoelectric effect. We will get half mev whole square must be equal to mevec. Please note these two equations on left hand side are same. That's why I'm comparing right hand side. So we will get mass of electron get cancelled. Velocity of electron whole square is there, get cancelled. We will get velocity of electron is 2 times the speed of light. How this is possible? Mathematically, but it is coming. That is very interesting thing here. So the next case, if you divide Einstein's equation, so please note here velocity of electron is 2 times the speed of light. Mathematically, it is coming. So very interesting case it is. So next, if you take Einstein's equation of photoelectric effect and divide it by speed of light, you will get h nu by c is the momentum of the photon minus h nu naught by c is the threshold momentum, which I got in my equation. On right hand side, you will get half mev whole square by c is the maximum kinetic energy of the ejected electron from the metal surface according to Einstein's equation. Now you take the new equation of the photoelectric effect, h nu minus h nu naught must be equal to MEVEC, where M is the mass of electron, V is the velocity of electron, and C is the speed of light. If you divide that equation with the speed of light, you will get h nu by C is the momentum of the photon, minus h nu naught by C is the threshold momentum, minus MEVE is the momentum of the electron, which is ejected from the metal surface. You will get h nu. Now you compare the Einstein's equation of the photoelectric effect in terms of law of conservation of momentum minus the new equation of the photoelectric effect. You will get, comparing the left hand side and the right hand side of Einstein's equation of photoelectric effect and the new equation of the photoelectric effect, you will get half MEVE whole square by C must be equal to MEVE. Mass of electron get cancelled. Velocity of electron whole square get cancelled. You will get velocity of electron is 2 times the speed of light again. So this was the very interesting case. Now atomic photoelectric effect. So can I continue, sir? Can I continue, sir, if you don't mind? Excuse me.
Yes, go ahead.
I think 20 minutes happens. So if you want, I will continue, sir. So this was up to here, my slides will be there. So I proved that velocity of electron is 2 times the speed of light. Here, up to here, my slides was there. So if you want, I will continue the atomic photoelectric effect. So the atomic photoelectric effect is photoelectric effect at atomic level by considering the Bohr's atomic model. So this is the basically Bohr's atomic model. I have taken the Bohr's atomic model, the momentum of the photon plus momentum of the electron before collision, and momentum of the photon plus momentum of the electron before collision, and momentum of the photon plus momentum of the electron after collision. If you take the momentum of the angular momentum is given by nh upon 2 pi r. Therefore, the linear momentum is given by nh upon 2 pi r. Momentum of the photon plus momentum of the electron before collision must be equal to momentum of the photon plus momentum of the electron before collision. So h nu by c is the momentum of the photon plus nh upon 2 pi r is the momentum of the electron plus h nu naught by c is the momentum of the photon after collision plus MEV is the momentum of the electron after collision. If you rearrange this equation, you will get h nu by c minus h nu naught by c is equal to minus nh upon 2 pi r plus MEVE. This is the equation. If you again rearrange this equation, you will get h nu by c minus h nu naught by c is equal to MEVE plus minus nh upon 2 pi r. Just rearranging this equation, for an electron which is free, which is not revolving around particular orbit, you will get minus nh upon 2 pi r is equal to 0. Why I'm telling like this is Bohr's atomic model is talking about discrete units of any particular orbits. It is not revolving around any fixed orbit. For example, n is equal to 1 is for a first orbit, second orbit, n is equal to 2 means second orbit, n is equal to 3 means third orbit. For a free electron, n is not fixed. Therefore, it becomes whole term becomes 0. Therefore, h nu by c minus h nu naught by c is equal to MEVE for a free electron which is revolving around the nucleus, which is surrounding on the metal surface. Therefore, this is the equation of the photoelectric effect in terms of law of conservation of momentum, which just we derived on the above slides. So this is the equation of the photoelectric effect in terms of law of conservation of momentum for an electron on the metal surface, which is moving freely, which is not fixed about any particular orbit. By taking the least common multiple of speed of light, we will again get h nu minus h nu naught is equal to MEVEC. So thank you. So this, please give your useful comments on these equations of photoelectric effect. So how was my work on the photoelectric effect? Please give your useful comment, or any doubts anybody have how I got this equation, how I compared my equations with Einstein's equation of photoelectric effect. Please comment on this. How I have proved V is equal to 2C. If anybody have any doubts or something else which you can prove me wrong to, please, anybody. So this is all about my work. So I really want to say David sir for giving me a beautiful opportunity for presenting my work. So this is how basically I compared Einstein's equation with the new equations of photoelectric effect in terms of law of conservation of momentum. You can see the work here. So thank you very much.
Okay, thank you. Any comments from the participants? questions, comments? Nothing? Okay, thank you very much. Okay, let's move to the final presentation. Final one is made by Soraya Berajes, Ahmad Teriji, University of Langout, Algeria. Could you prepare your
Any questions?
poster, please? No questions. So could you stop your file presentation? Okay, thank you.
If anybody have any questions, please tell me. I will try to answer the questions if anybody have.
Okay, Soraya, please share your poster.
Hello, everyone.
Okay, could you start now?
Is it clear on the screen, please? Hello?
Yes, please go ahead.
Okay, thank you very much. Okay, I'm going to present for you today our work about the structural, electronic, mechanical, and piezoelectric properties of the two polymorphs of the compound magnesium iodate, the monoclinic and the hexagonal polymorphs. And starting by the structural properties, we used the Abinit code with the approximation of LDA. So the results were as following. We have the calculated and the experimental parameters, cell parameters for the two compounds, the monoclinic phase and the hexagonal phase. And calculating the deviation, we found acceptable deviations except for the B parameter for the monoclinic one material and the C parameters for the hexagonal material, which were found to be bigger, having big values or deviations, may still acceptable. Then after the optimization of the cell parameters, we calculated first the electronic properties, and especially calculated the band gap energy. And the figure 1 represents the band structure for the hexagonal polymorph, while the second figure 2, represents the band structure for the monoclinic material. And the values extracted from these two figures are illustrated in this second table. And we find for both materials very close values of gap, electronic gap, 3.49 and 3.42 for the two polymorphs, and both have indirect band gap. And the values were the value for the monoclinic polymorph is somewhat bigger than the experimental value. Then in the second part, we calculated the elastic properties, starting with the elastic constant, and the found values are illustrated in this table. And we can say that the C33 parameter or constant is the most important elastic constant for the monoclinic polymorph, which indicates that this material is more resistant to compression along the C-axis. Then, still with the mechanical properties, we calculated the other mechanical properties, which are illustrated in this table, table 3. We have the compressibility modulus, the shear modulus, the Young modulus, the Poisson coefficient, and the B/G ratio. and the found values are as following. And from these values, we can say that shear modulus and Young modulus for the hexagonal polymorph are the most important, followed by the second polymorph, which is the monoclinic compound. And according to Fox criteria, we found that the monoclinic is ductile while the hexagonal is brittle. Also, that the monoclinic polymorphs has a covalent character, whereas the hexagonal one tends more towards the ionic character according to the sigma value. Then for the elastic anisotropy, we found a positive value for hexagonal material and a negative value for the monoclinic material. Next, we estimated also the piezoelectric coefficients for the two materials, and the values are illustrated in this table. And we can say that the hexagonal polymorph, all the coefficients, piezoelectric coefficients, are very low compared to the monoclinic isotope, except for the D34, which is relatively higher in the hexagonal phase. And the highest values are found to be 63.46, which is the D15 for the hexagonal material, and 76.78, which is D21 for the monoclinic material, which means that the monoclinic one is piezoelectrically better than the hexagonal one. Okay, and thank you for your attention. Any questions?
Okay, thank you very much. Any question from the participants? I see no question. Okay, thank you very much for your interesting talk.
Okay, thank you.
Okay.
Yes, thank you, Dr. Shiro. I thank all the participants attending the conference and hope you have enjoyed the sessions. I especially thank you, Dr. Shiro, for his chairing the session of the day 2, and hope everybody has enjoyed the sessions. And I request everybody to share their feedbacks as a testimony, which will enable us to improve for the next year conference, and we can increase the scope of the conference, and which will also publish in the website as a testimony of 2 lines or 3 lines of the content about your feedback. And I extend my warm invitation to join the next year's conference, which is in 2024, March at Valencia, Spain. Thank you. Have a great day.
Thank you very much.
Bye-bye.
Thank you very much.
Thank you very much.
Bye-bye. Thank you.
Bye.